If you're familiar with blockchain technologies, then you will know that there are many different concepts in computer science which you should be conversant with in order to fully understand how exactly blockchains as well as blockchain networks work. Creating blockchain networks requires the application of a number of different techniques, from hashing and digital signatures to data structures and distributed computing concepts. There are a wide variety of topics which one needs to understand in depth in order to fully grasp how blockchain networks work. Since the focus of this course is on working with the Ethereum blockchain network, you should have some idea of all of these concepts. But in addition, Ethereum introduces a whole new set of terms as well as technologies which will take some getting used to. During this course, I will introduce you to each of these terms and do my best in explaining them to you, and will also periodically repeat them in order to reinforce exactly what they mean. The first of these terms which we need to get used to is, of course, Ethereum. Ethereum can best be thought of as a decentralized, open source, public blockchain based platform which features the functionality of smart contracts. We will be digging deeper into what each of these terms means, but first, let us cover the concept of a smart contract. This can be thought of as a protocol which is used to digitally specify, verify, and also enforce the terms of a contract. Very simply put, you can think of a smart contract as a digital version of a regular contract. There will be many different smart contracts we will be creating during this learning path, which will give you a good idea of what is possible in smart contracts and what their limitations are. But we now move along to another term which we need to familiarize ourselves with when using Ethereum, and this is the concept of the Ethereum Virtual Machine, or EVM. This is pretty much the execution environment which is run by all Ethereum nodes. Those of you who are familiar with the Java programming language can think of this in terms of the Java virtual machine. So while a Java virtual machine is capable of executing any code which was written in the Java programming language, the Ethereum virtual machine is able to execute any smart contract code which was written in any of the languages supported by Ethereum. And another term which you should be familiar with right now is the fundamental technology on which Ethereum is built, and this is a blockchain. So you can think of a blockchain as simply a list of records which are stored across a sequence of blocks. These blocks happen to be chained together using the technique of cryptography. Before we delve into the details of Ethereum, let us revisit the concept of a blockchain, and we do that by breaking down this definition into its components. So a blockchain can be thought of as three things. Firstly, it is a list of records. These records are stored across a sequence of blocks, and these blocks are chained together. Out of these, we will first focus on the fact that a blockchain is a list of records. There are many different kinds of data which can be represented as a record, and on the screen in front of you, you have a collection of 9 different records. You can consider that it's not only the 9 records themselves which are important, but the sequence in which they are stored also matters. There are, of course, different ways in which this data can be stored. You could make use of a relational database where the records will be stored within a table. And in fact, you could also partition the table so that the records are distributed across them. However, in the case of a blockchain, these records will be distributed, but across a sequence of blocks. So moving back to our list of 9 records, if we were to split these across 3 different blocks, we can create 3 sets of 3 records each. So we have these 9 records split across 3 different blocks. And remember, it's not just the records themselves, but their sequence which also matters to us. So within each block, these records are stored in sequence. However, since they are spread across a number of blocks, it becomes necessary for us to sequence the blocks as well. And this is exactly where the concept of chaining these blocks together comes in. So moving back to our 3 blocks, to ensure a sequence from the left block to the right one, we can chain these together. So block number 1 precedes block number 2, and block 2 precedes number 3. So in this manner, we have managed to store a sequence of records where there is a sequence maintained within each block, and then also a sequence of the blocks themselves. This is precisely what a blockchain is. So what exactly are the characteristics of a blockchain? Well, for one, this is a chain which is continuously growing. The expectation is that the list of records is not static, but in fact, new records are continuously added, and these will need to be stored, which means that the blockchain itself needs to keep growing. Since the records which are maintained in a blockchain typically store some very important information, it is necessary that there is not a single point of failure, and the data which is stored on a blockchain should not be centralized, but should ideally be distributed across a number of machines, which is precisely why a blockchain is usually maintained by a network of nodes which can be scattered across multiple geographical regions. So while having data distributed across multiple machines does solve a lot of problems, it also creates one, specifically that all of the nodes which maintain the blockchain need to reach some kind of consensus on what the correct state of the blockchain should be. This is why blockchain networks have this concept of consensus algorithms, which at the time of recording is the proof of work algorithm for both Ethereum as well as Bitcoin. One important characteristic of a blockchain is that the records which have been written to them cannot be modified. That is, the records are immutable. This is, of course, a security feature of blockchains so that any change in the data can be detected by the nodes in the network. However, it also means that you need to be doubly careful when inserting any new records onto a blockchain in the first place. And finally, one more very important security feature in a blockchain is the fact that the records which are inserted into them can be verified. This can involve a lot of work. For example, in the case of Ethereum, you may need to compute every single block starting from the Genesis block in order to verify a transaction. However, this is something which can be done. We saw in the previous clip that a blockchain can be thought of as a list of records which are stored across a sequence of blocks which happen to be chained together using cryptography. Blockchains are the underlying technology on which a number of different platforms have been built, one of these being Ethereum. Ethereum is a decentralized, open source, and public blockchain network, and a powerful feature of Ethereum is that it supports the concept of smart contracts. So let us understand Ethereum by breaking down each of these terms. So Ethereum is decentralized, which means that the Ethereum blockchain is not just available on a single node, but is in fact distributed across multiple nodes all over the world. The code which makes Ethereum work is open source, and there is a strong developer community which is constantly updating the code in order to fix bugs or to add new features. For example, at the time of this recording, one of the major enhancements which is in the works is replacing the proof of work consensus algorithm with one called proof of stake. Another feature of the Ethereum network is that it is a public blockchain network. This means that anybody is free to join the network as long as you have the required hardware and software. There is no invitation necessary in order to join the network, and there are multiple mechanisms in place to ensure that one can work with a large number of untrusted nodes. This also means that all the records which are written to the Ethereum blockchain are publicly available and should not be used to store sensitive data in plain text. And finally, what really makes Ethereum tick is the fact that it supports the notion of smart contracts. As mentioned previously, these can be thought of as regular contracts, except they are in digital form. Being on a public network, smart contracts will be available for all to see, And once again, no sensitive data should be stored in a smart contract in a form which all can access it. So given all of this, let us summarize some of the characteristics of Ethereum. First of all, this is a platform whose underlying technology is the blockchain. All of the data which is stored on an Ethereum network is distributed across a sequence of blocks, and the data which is stored in these records are transactions. Ethereum is also open source, which means that there is a community of developers who are working on it in order to fix bugs and to bring in new features. The fact that it's a public blockchain means that anyone can join the network and then view all of the data which is stored on it. However, given that there is no pre-screening of the nodes, there have to be some mechanisms in place which allow one to work with other untrusted nodes. This includes the ability to arrive at a consensus on what the correct state of the Ethereum network should be, and mechanisms such as the proof of work algorithm accomplish exactly that. And given that one of the main features of Ethereum is the ability to define and execute smart contracts, many of the nodes participating in the network need to have the Ethereum virtual machine, which is required in order to execute the smart contract code. At this point, let us delve a little deeper into the concept of a smart contract. So, as we had covered previously, this can be defined as a protocol to digitally specify, verify, or enforce the terms of a contract. And all of this can be done by writing some code. Given all of that, let us break down what exactly a smart contract is. It is, in fact, a piece of executable code, and then this code will define the terms of the contract. Once a smart contract has been defined, in order to use it, one needs to deploy it to a blockchain network. And once that is done, this contract can be executed on its own, and even the terms of the contract can be self-enforcing. This means that any actions on the contract need not require human intervention, and you can in fact have other contracts trigger the code in a contract. And depending on what is defined in the contract, it is possible that you don't really need any human to check whether the terms are being enforced. One thing to keep in mind, however, that any action which changes the state of the contract or of the blockchain itself will invoke a transaction, which means that some transaction fees will need to be paid. Once a transaction has been invoked, there is a process which needs to be followed in order for it to be added to the blockchain, and this is known as mining. In the case of Ethereum, mining can be defined as the process of solving a complex mathematical puzzle, and the node which successfully solves that puzzle can win the privilege of adding a new block of transactions to the blockchain. All the mining nodes in an Ethereum network will be performing transaction verifications, and within the verification process itself, there are a number of steps. This includes verifying the identity of the entity which invoked the transaction. This can also involve several lookups of the account balances of the entities involved in the transaction. And within each block which is added to the Ethereum blockchain, there are several hundreds of transactions. As a consequence, mining requires significant amounts of compute resources. This is because it's not only transaction verification which the mining nodes need to perform, but when one of the miners claims that they have solved the proof of work puzzle, all of the other miners will need to verify the proof of work. In order to incentivize nodes to participate in the mining process, in spite of all of these use of resources, they need to be compensated in some manner. One of the ways in which miners are compensated is in that they can collect the transaction fees for every transaction which has been triggered, and the currency in which the transaction fees are paid is known as Ether. Ether can be thought of as the crypto fuel for the Ethereum network. So, Ether is simply another cryptocurrency, but this one is specific to the Ethereum network. Like with any regular currency, Ether can be broken up into subunits. For example, one Ether is made up of 10 to the power 18 Wei, or 10 to the power 9 gigaway. While there are other subunits which have been defined, such as kiloway, it is way and gigaway which are most commonly used. One thing to keep in mind is that Ether is in fact a currency, and just like with regular currencies or fiat currencies, it can be traded. For instance, at the time of this recording, one Ether could be purchased for 132 US dollars. So whenever you're invoking a transaction on the Ethereum network, you will have an idea of the transaction fee which you are paying, whether it is in US dollars or euros or whatever the currency in use in your country. However, if you are invoking a transaction on the Ethereum network, you will need to pay a fee which is defined in ethers to the miner. The specific amount of your transaction fee will be proportional to the complexity of the transaction which you have triggered. The greater the complexity, the more ethers which you end up paying. And how complex exactly is a transaction? Well, there is a measure for that as well, and this unit is known as gas. So far in this course, any storage of data on the blockchain which has been discussed has revolved around transaction data. However, there is also some state data which is stored in the Ethereum network, and in this clip, we will take a look at what needs to be stored before delving into how it is done. So let us begin. We have already covered the fact that a blockchain is meant to store transaction data. The transaction information is spread across a number of blocks which are arranged in a sequence by being chained together using cryptography. All the transaction data is immutable, and if you'd like to view the details of any specific transaction, Ethereum allows you to enter a transaction ID, and then the corresponding details will be retrieved from the blockchain. While the blockchain data structure alone is enough in order to store transaction-related information, some additional data is needed in order for a blockchain network to function effectively and also efficiently. So what is this additional data? To begin, the state of the accounts in a blockchain network is something which periodically needs to be checked by the nodes, especially during the mining operations. And since one of the primary features of Ethereum is the ability to store and then execute smart contracts, the information related to these contracts will also need to be stored. So while the transaction information in an Ethereum network is something which is immutable, the state of the accounts as well as the smart contract details can be subject to change. You may be aware of how transaction information is stored in an Ethereum network in the form of Merkle trees. However, how exactly is the state of the accounts in Ethereum as well as smart contract information stored? Before we get into the specifics of that, let us take a look at what exactly constitutes the account state and why exactly it is needed. So the state of accounts in a blockchain network, and especially in Ethereum, will be needed by the miners in order to verify transactions. Transaction verification steps can include, for example, checking the Ether balance of an account, especially in the case of Ether transfer transactions, but also with regular transactions in order to ensure that the transaction originator has enough Ether to see the transaction through. In addition, transaction verification also involves checking the account nonce, and this is something which is done in order to prevent replay attacks. The account nonce effectively represents the number of transactions which have been originated from a particular account, and the use of this nonce prevents old transactions from being thrown back into the transaction pool, since miners will be able to quickly check that the account nonce listed in the transaction is lower than the nonce currently associated with that account. This way, they will be able to detect an old transaction and potentially a replay attack. There is also other account related information which we won't get into yet. But we'll now move on to smart contract data. And we know that smart contracts are needed by the miners in order to run transactions. To do that, they will need access to the byte code of the contract, and this will be sent to the Ethereum virtual machine in order to be executed. And smart contracts can have a balance as well. This can be a token balance if they represent some tokens, but contracts in Ethereum are also capable of holding some ether. So we can see that a fair amount of information needs to be stored in order to represent accounts as well as smart contracts in Ethereum. And in order to do that, Ethereum has two different types of accounts. One of these will store the account state, and the other will store the smart contract details. An Ethereum account which stores the account state is referred to as an externally owned account, while those which store contract-related information are known as contract accounts. All the data which these accounts store are referred to as the account state in Ethereum. We move along now to the characteristics of each of these accounts, starting with externally owned accounts, which, as you expect, has an ether balance. These accounts also have the ability to invoke and send transactions to the transaction pool, which can then be mined. Externally owned accounts are defined by their private key, and any transaction which is originated from an account will be signed with this private key. There is no associated code with such an account. However, they do include an account nonce, which can be used to prevent replay attacks. Moving along now to contract accounts, these are also capable of having an ether balance, and they do have some code associated with it. The code which is stored in a contract account is in the form of the EVM byte code, and this is something which can be executed by any of the nodes in the Ethereum network. Given what is defined in the code of the smart contract, it is capable of modifying its own state. For example, the smart contract code may have some function in order to transfer the ether balance of the contract account over to some other account. Before we delve into the details of how account state in Ethereum is stored, let us quickly summarize what exactly represents the account state. As we have covered, there is a nonce associated with an account, and this applies more to externally owned accounts rather than contract accounts. Both types of Ethereum accounts do have an ether balance which needs to be stored. In addition, there is also a storage root which represents the root of the storage data structure used for the account state. And this is something we will get into in just a little bit. And finally, each account will also contain a code hash field. This will remain blank in the case of an externally owned account, but will represent the contract bytecode in the case of a contract account. So clearly, for both externally owned as well as contract accounts in Ethereum, a number of fields need to be stored. And the question arises, what data structure is actually used in order to store this detail? The answer to that is a Merkle-Patricia trie. This is essentially a tree data structure, and we will soon explore how exactly it can be used in order to represent the state of accounts. Do keep in mind that tries, spelled T-R-I-E-S, are slightly different from regular tree data structures, and given the name Merkle-Patricia trie, you may be wondering whether there is any relationship with the Merkle trees which are used in order to store Ethereum transaction data. And the short answer is yes, there is some relation. So before we get into the implementation of Merkle-Patricia tries, let us revisit what a Merkle tree exactly is. Generally speaking, a Merkle tree is one in which every leaf node is labeled with the hash of a data block, and every non-leaf node represents the cryptographic hash of its children. To see how exactly this can be used in order to store the transactions in an Ethereum network, consider that you have 4 different transactions, A, B, X, and Y, which all need to be stored within a single block of a blockchain. All of the transaction data will be used to generate the leaf nodes of the Merkle tree, and the leaves will simply be a cryptographic hash of each of these transactions. The leaves will then be grouped together in pairs, and then they will be combined in order to generate a hash of each pair. So we have the hash of A and B, and then the hash of X and Y, which in turn will be hashed together in order to produce a Merkle root. So using the data of 4 different transactions, we can come up with such a Merkle tree data structure. And if these represent all of the transactions to be added to a single block in the blockchain, then it is the Merkle root, which represents the transaction hash, which will be included in the block input. In the previous clip, we covered the fact that the state of an Ethereum account, whether it is an externally owned account or a contract account, is stored using a Merkle-Patricia trie data structure. This is a form of tree data structure, but to understand how exactly it is used to store information, we will begin now by examining a trie data structure. This is spelled TRIE, and I have heard some users pronounce it tree, but most users refer to it as a trie structure just to distinguish it from a regular tree structure. And this is the practice I'm going to adopt for this course. So a trie structure is also known as a prefix tree. This is a form of a structured tree, and its specific purpose is to store associative array data. Specifically, associative arrays where the keys are of type string. Associative arrays effectively represent a collection of key and value pairs, and map data structures or dictionaries are examples of such associative arrays. To understand exactly how a trie data structure will store associative arrays, let us take a look at an example. So consider that we have these 6 key and value pairs. This is an associative array, and it represents the counts of various words in some text. You will observe that all of these words begin with D, and some of them share the same prefix. We need the trie data structure to store all of these keys and their corresponding values. So how exactly can we do that? Well, let us begin with the first word in our associative array. This is the word do, and it contains 2 letters, and there is a corresponding value of 265. To represent this in a trie data structure, we begin with the first alphabet, which is D, and represent this as a node of the trie. The next letter in the word, which is O, becomes a child of this node, and both of these nodes together represent the key do. So following that, we need to store a corresponding value, and this will be stored within the node, which represents the end of a particular word. So in the node corresponding to the letter O, we store the value 265. So in order to store the count of the word do, we need to make use of 2 nodes, one for each alphabet, starting with the first alphabet in the word, and the node representing the last letter in the word will store the corresponding value. To illustrate this, we move along now to the next word in our list, which is den. And to store this, we don't create an entirely new trie structure, but we make use of the existing one. Since both of the words so far have the same first alphabet, we can make use of the node for D and then branch off to represent the word den. Once again, as we move along the letters representing the word, we create new child nodes. So we have 3 nodes over here to represent den, the last of which will store the value corresponding to den, which is 12. So here we have represented 2 key and value pairs using this trie structure. And even though the combined number of letters in both the words is 5, we have been able to represent them using a total of just 4 nodes, given that they share a common prefix of D. Moving along now to the third word in our associative array, and this is deer. And you will notice here that this shares the first 2 letters with the word den. So here we can make use of the nodes D and E, which we used for den, and then add the nodes A and R, and then the value of 15 will be stored along with the R node. Moving along now to the word deal, given this shares the first 3 letters with the word deer, we reuse those 3 nodes and then create an additional node representing L, which will also store the value of 4 corresponding to deal. So for all of the words stored in this try data structure so far, the values have been represented in leaf nodes. However, what if we introduce a fifth word into this list, which is dealer? And you will notice that the word deal is entirely a prefix for the word dealer. So to represent this new word, we will once again simply add new nodes for the letters E and R, and then store the value of 9 in the same node as R. However, the node which stores the alphabet L, in this case serves as a branch node as well for the word dealer, in addition to being a terminal node in order to represent the word deal. There is still one word which we need to store in our associative array, and this is the word dull, which has a value of 29. And given that there is only a single alphabet which is in common with the other words, we will reuse the node D and then add additional nodes for U and the two Ls. So with that, the 6 key and value pairs which make up our associative array have been represented using this try data structure. Words which have a common prefix will share a common path in this try structure until the point where the words branch off. As a result, in order to store these 6 words, which have a combined total of 23 letters, we've only used a total of 13 nodes. And with that, you now know exactly what a try data structure is. So as we have discussed, this is referred to as a prefix tree, and this is used in order to store associative array data where the keys are represented as strings. So what are the benefits of storing data in the form of a try? For one, lookups in a try structure are reasonably efficient. The search complexity will be big O of m, where m is the length of the string being searched. This performance can be superior to a hash table search in the worst case. While hash tables can also be used to store key and value pairs, in case the hash function maps all the keys to the same hash bucket, then the search operation effectively becomes a big O of n operation, where n represents the number of key value pairs stored in the hash table. If you're storing several thousands of words, this will deliver rather poor performance, and this is mitigated to a great degree by a try structure, where the time taken for a search is proportional to the length of the string itself. An additional feature of a try structure is that there are no collisions of different keys. While words which share a prefix will have to some degree a common path in the try, they will eventually branch out to different leaves. And in the case we saw of the words dealer and deal, where the word deal represents a word itself and also the prefix to dealer, we saw how a node can be used to serve as a terminal node storing a value, as well as a branch node. So try data structures do have a number of benefits. However, there are a few drawbacks as well. Specifically, very long words will produce rather long chains, and looking these up in the try structure will be rather inefficient. In addition, if there are not too many words which share prefixes, then the storage requirements of a try structure will increase. The worst case scenario is where we end up with a single node for every single letter. To mitigate this, we come up with a Patricia try structure, which is in effect a space optimized version of a try structure. This space optimization is achieved by combining every non-leaf node which has just a single child with that child. Patricia tries are also referred to as Radix Trees, and we will now take a look at how exactly they will work. So we saw how our 6 key and value pairs can be stored using a try data structure. And if this data were to be represented using a Patricia try, we first need to identify those non-leaf nodes which have just a single child. So these two nodes highlighted in orange fit this criterion, and we can now optimize the tree by combining these nodes with their respective children. So each of these nodes now represents 2 letters, and they also store a value representing the word which ends at these nodes. So already, our trie data structure has reduced from a total of 13 nodes to 11. However, this is not where we stop. We continue looking for any nodes which are not leaves and contain just a single child, and this node representing U fulfills that criterion. So we will merge that node with its child in order to produce a node which now represents 3 letters and a value. So we're down from 13 nodes in a trie structure to 10 in a Patricia trie. And this is exactly why a Patricia trie is considered to be a space-optimized version of a trie data structure. We have previously covered that we need some data structure in order to store the state of the accounts in an Ethereum network. The accounts can be either externally owned accounts or contract accounts. And we covered the fact that this data can be stored as a collection of key and value pairs or an associative array. There are a few data structures available to store such data, and a trie data structure is one of them. We then took a look at a Patricia trie, which is a space-optimized version of the trie data structure. In this clip, we will take a look at the Merkle-Patricia trie, which is what is used in order to store the state information in Ethereum. To begin, let us take a look at what exactly the state of an Ethereum account may look like. If you consider a highly simplified version of the state, consider that we only need to store 4 different account addresses and their corresponding Ether balances. The account addresses will serve as the keys which need to be stored in our data structure, and the Ether balances will serve as the corresponding values. Each of our keys in this case is a 7-character long string, and our values are the Ether balances, which are numbers. So we will be making use of a Merkle-Patricia trie in order to store all this information, which in essence is a modified version of a Patricia trie. So how exactly do Merkle-Patricia tries work? Well, it makes use of 3 different types of nodes. One of these is an extension node, which you can think of as representing a prefix just before any branching can occur. In order to represent the branching, there are branch nodes in Merkle-Patricia tries, and this is where the trie will branch off along different paths. And then there are nodes which represent the terminating points in a Merkle-Patricia trie and will also store the corresponding values, and these are the leaf nodes. So given all of this, what exactly does a Merkle-Patricia trie look like? Well, this is an example which we will use in order to represent the account state which we had taken a look at just a little earlier. So here we have 3 different types of nodes: extension, branch, and leaf nodes. Let us take a closer look first at the extension node. So these nodes will be used to represent a common prefix just before the point of branching out. And within a Merkle-Patricia trie, the extension nodes will store a single non-empty key representing the common prefix value and will contain a single child, which will be a branch node. In fact, an extension node can be thought of as some form of compaction of all of the redundant branch nodes. Zooming in on the extension node in the Merkle-Patricia trie, we see that it contains a total of 3 fields, starting with a prefix number. This number represents the type of node this is, and a value of 0 means that this is an extension node. Following that, there is a field called shared nibbles, which simply represents the value of the shared prefix. And finally, there is a field called next node, which represents the hash value of the next node in the Merkle-Patricia trie. So, in order to understand exactly how this works, let us take a look once more at the state of our network. So we have these 4 key and value pairs representing 4 account addresses and their corresponding Ether balances. We notice that all of these 4 account addresses share a common prefix. They all begin with the characters C and 5, and it is this common prefix which can be stored in an extension node. So when we map this account state to our extension node, the value of the shared nibble will become C5. We notice that for these 4 accounts, there are 3 different values for the next character, and this is precisely where we need a branch node. So the next node from this extension node is going to be a branch node. And moving back to our Merkle-Patricia trie, we see that this branch node will create 3 separate branches in our trie structure. So what exactly is a branch node? Well, this is something which is used at points in the Merkle-Patricia trie where at least 2 of the keys diverge. Since the keys in a Merkle-Patricia trie are represented using hexadecimal notation, each individual character can take 16 possible values ranging from 0 through F. It is for this reason that a branch node will contain 16 slots representing each of the possible characters it can branch out into. When a trie data structure is used to represent keys of varying lengths, it is possible that the prefix for some of the keys represents the terminating point for another. It is for this reason that branch nodes can also contain a value if this is the point at which a particular key terminates. Moving along now to the use of a branch node in order to represent the state of our own Ethereum network. We see that the branch includes 16 slots for the potential branching out values for the keys, and then a single field for a value if this is the point at which a particular key terminates. So for our account state, we already saw that an extension node was used previously in order to represent the shared prefix of C5, and then the point at which the branching out occurs is in the third character. So we now have 3 possible values here, 1, 3, and A. So we now branch out in these 3 different directions from our branch node. Zooming out now to our Merkle-Patricia trie, we can see that from this branch node, there is a single extension node and there are 2 leaf nodes as well. The extension node, as we know, is used to represent a shared prefix. And moving back to our account state, we see that there are 2 accounts which have the common prefix of 03. So the branch from A goes out to this extension node, which represents the shared nibble of 03. The next node from this extension node will be a branch node, which will generate 2 different branches, and these will go out from the slots for the characters 3 and E. From there, we will need leaf nodes to represent the last characters for each of these account keys, which are 1 and 7. So far, we have taken a look at 2 of the 3 types of nodes which can make up a Merkle-Patricia trie. So we have examined extension nodes as well as branch nodes, and we covered that extension nodes are used to represent a shared prefix, whereas branch nodes are used to represent the points at which the trees will branch out in different directions. This brings us to the last type of node in our structure, which is a leaf node. So what exactly are leaf nodes in a Merkle-Patricia trie? Well, you can think of these as being similar to extension nodes, especially in that they have 3 different fields. However, rather than referencing a next node, which is typically a branch node, a leaf node will store a certain value. These will be the values corresponding to the keys in the account state. And another feature of leaf nodes is that unlike extension nodes, they do not have children. So let us now zoom in on the leaf nodes which have been generated for our own Merkle-Patricia trie to store our account state. So these 2 leaf nodes here have a common value in the prefix field, and this is a value of 2, which represents a leaf node with an even number of nibbles. These nibbles are stored in the key end field, and you can see that each of these leaf nodes contains a total of 4 nibbles. There is also a value field which stores the value corresponding to the keys which terminate at these leaf nodes. So these leaf nodes represent these two accounts in our account state. We have covered that the first three characters or nibbles have been represented by using an extension node and a branch node previously, and it is the final four nibbles which are represented within these leaf nodes. And of course, the ether balance values of 67 and 0.1 are also stored here. So this covers 2 out of the 4 leaf nodes in our Merkle-Patricia tree. And we now move on to the last 2 leaf nodes. We saw previously that an extension node was created out of the first branch node, and then following that, there is another branch node to represent the 2 further branches in our account state. And when we take a closer look at each of these leaf nodes, we see that once again they contain 3 fields, starting with the prefix field, and a value of 3 over here indicates that this is a leaf node which represents an odd number of nibbles. There is just a single nibble for each of these leaf nodes, which correspond to the key end field over here and represent values of 1 and 7. Each of these leaves, of course, also stores a value which represents the ether balances for each of the accounts, and these are the values of 13 and 4.06. With that done, let us now quickly summarize what we have learned. In Ethereum, there is information regarding the state of the network, which needs to be stored as the account state, and there are 2 types of accounts which are available in Ethereum. The first of these represents externally owned accounts, and these are the ones from which transactions can be originated. The other type of accounts available in Ethereum are those which represent smart contracts, and these are referred to as contract accounts. Contract accounts can also contain an ether balance and also contain the bytecode representation of the smart contract. Both of these accounts can be represented as a common account state, and these include fields such as the nonce, which is more relevant for an externally owned account. Both of the accounts will contain an ether balance. The storage root represents the storage of a smart contract, and then there is also the code hash field, which will be blank or null in the case of an externally owned account, but will contain the hash of the bytecode in the case of a contract account. So all of this data needs to be stored, and the question which we needed to answer previously was, how exactly is this done? Well, we saw that if such a data structure represents a rather simplified state of our network, where we have a collection of key and value pairs, then we can represent this in the form of a Merkle-Patricia tree. This uses a combination of extension nodes, branch nodes, and leaf nodes in order to represent the state of all of the accounts in our Ethereum network. In this exercise, you will first list down some of the characteristics of the Ethereum network. Ethereum is one of the most popular blockchain-based platforms out there, and there are several reasons for its widespread use. You will need to recall some of those. Next, you will identify some of the fields which are stored within an Ethereum account state. We have covered during this course that there are 2 different types of accounts in Ethereum, but they are stored in a similar manner. You will need to identify what the specific fields are for these account states. And finally, you will list down the different types of nodes which can be used in Ethereum's Merkle-Patricia tree. The account state in Ethereum is stored in a data structure which is a modified Merkle-Patricia tree. There are 3 different types of nodes within this tree data structure, and each of these serves its own unique purpose. You will need to recall what those are. All of these topics were covered during this course, so please pause this video and then take some time to perform these tasks on your own. For the first task in the exercise, you needed to identify some of the characteristics of the Ethereum network, which makes it such a widely adopted technology. So first of all, Ethereum is a blockchain-based platform. This of course means that Ethereum is used to store a ledger of records which have been distributed along multiple blocks which have been chained together into a sequence. The specific records which are stored in the ledger are Ethereum transactions, and these transactions are both immutable and verifiable. Another feature about the Ethereum network is that it is a public blockchain network. This means that joining the network does not really require any invitation as long as you fulfill certain criteria in terms of having the required hardware and software. You can join the Ethereum network and then participate in its activities, which include invoking transactions, mining, and so on. The code for Ethereum also happens to be open source, and there is a strong community of developers who maintain the code. This, of course, means that there is a lot of transparency around any changes which have been introduced to the Ethereum network. And the fact that Ethereum is both a public network and open source truly means that there is no change which can occur on Ethereum without people knowing about it. One side effect of being a public blockchain network which anyone can join is that not every participant who becomes a node in the network can be trusted. As a consequence, there needs to be some mechanism in place which will ensure that individual participants or small groups of them will not be able to hijack the network, and that there is almost no incentive for nodes to break the rules set by Ethereum. This is precisely what is achieved by the implementation of the proof of work algorithm for consensus. And one of the most important features of Ethereum, which distinguishes it from many of the other blockchain based platforms, is its support for smart contracts. Smart contracts are effectively contracts in digital form where all of the clauses of the contract can be defined in code. Given the fact that Ethereum is a public network, all contracts will be available for anyone to view, and this ensures a great degree of transparency around any Ethereum transactions. However, the account addresses which are involved in the transactions do remain private, and the accounts can't be traced down to the individuals or entities which control them unless they either choose to do so or they reveal it accidentally. For the next task, you needed to identify the different fields which make up the state of an Ethereum account. We covered during this course that there are two different types of accounts in Ethereum. These are externally owned accounts and contract accounts. Both of these accounts are stored in a similar manner, and there are four different fields which you can find within them. There is a nonce, which you will be familiar with in the context of an externally owned account. And this effectively serves as a count of the number of transactions which have been originated from the account. This field plays a crucial role in preventing replay attacks, where an old transaction can be inserted back into the transaction pool, and the use of the nonce will ensure that such a transaction will be identified as one which has been previously processed. In the case of contract accounts, the nonce value represents the number of contracts created by that account. The next field stored in the Ethereum account state is the Ether balance of the account. This applies to both externally owned as well as contract accounts, since both are capable of storing Ether. A third field in the Ethereum account is the code hash, and this, of course, is only applicable for contract accounts and remains blank for externally owned ones. And the fourth field in the account state is the storage root of the storage for a contract. The storage for a smart contract will be stored as a modified Merkle-Patricia trie, and it is the root of that trie structure which is available here. And speaking of Merkle-Patricia tries, we now come along to the last task in this exercise, where you needed to identify the three different types of nodes which can be used in such a trie data structure. The first of these which we covered was an extension node, which is used to represent a shared prefix of characters or nibbles. Following an extension node, you'll typically have a branch node which represents the point at which the trie data structure branches out along different paths. There are 16 different slots available in a branch node, which translates to one slot for each of the hexadecimal characters which the trie structure can branch out to. And there is also a 17th slot within the branch node in order to store a value. And the final type of node in a trie structure like this is, of course, a leaf node. This will store the last few nibbles of the string corresponding to that leaf node, and of course, a value which it maps to. In this clip, we will take a look at the concept of test networks in Ethereum, which provides an environment in which you can execute your smart contract code without having to incur real transaction fees. So before we delve into what Ethereum test networks are, let us take a look at what an Ethereum network is. The Ethereum network is the distributed network which maintains the Ethereum blockchain. To understand what exactly that means, we will start off with the concept of a centralized ledger. So if you have a number of different entities or nodes which need access to a ledger of transactions, a centralized ledger is one where a single node maintains the copy of the ledger itself, and then all of the nodes which need access to the data within that ledger will need to establish a connection to the central node. This, of course, has its benefit in the simplicity. However, one of the major drawbacks of this approach is the fact that the central ledger represents a single point of failure. If that node were to be taken down for some reason, then the data on that central ledger will simply not be available to anyone. Another issue with the centralized approach is that if all of the nodes which are accessing the central ledger are geographically dispersed, then communicating with the central ledger could take a really long time. The solution to this, of course, is to have a ledger which is distributed across multiple nodes in the network. And in order to ensure the consistency of the ledger, all of the nodes should be able to talk to each other to verify the ledger state. They also need some process in place so that all of the nodes can agree what the correct state of the ledger should be. And this is in fact exactly what a blockchain network is. So in its simplest form, a blockchain network can be thought of as a distributed ledger which is maintained by all of the nodes of the blockchain network. The ledger in such a case is of course in the form of a blockchain. At this point, let us take a look at some of the characteristics of a blockchain network. Each network maintains just a single blockchain. This means that all of the nodes which make up a single blockchain network are responsible for maintaining a single ledger. The blockchains themselves are immutable, and when people refer to the Ethereum blockchain, the one they are talking about is what is called the main network. The main network of Ethereum can be thought of as a production environment where all of the transactions are final. And given the immutability of blockchains and the fact that Ethereum is a public network, any mistakes made when invoking a transaction, perhaps even due to a bug in the code of a smart contract, will be permanent and will be available for all to see. Given all of this, it is important that any smart contract which has been deployed to the Ethereum main network is bug-free. So it becomes important then that once you have developed the code for your smart contract, you are able to deploy it to an environment where it can be tested. One option, of course, is to simply deploy your contract straight to the main Ethereum network. So once you have built your contract, you simply run your deployment process, and the contract will be available on the main network. Following that, you can invoke each of the contract methods which are in your smart contract and ensure that the output is exactly what you expect. If you happen to find a bug in your smart contract code, you can simply fix it and then redeploy the smart contract on the main network and then run your tests once more. You can repeat this process until you're satisfied with the code in your contract and only then share it with the users. This method, of course, has several drawbacks. First of all, many of the functions which you have defined in your smart contract may be changing the state of the contract itself or may be writing to the blockchain, in which case they will trigger transactions. Transactions, of course, involve a fee in terms of Ether, And the more complex your transaction, the more Ether you will need to shell out. And if your smart contract happens to have multiple use cases and also several features, then you will need a very large number of tests in order to make sure that everything works. Having multiple tests, of course, will trigger multiple transactions, and the testing process can turn out to be very expensive. As a result, deploying onto the main Ethereum network and then carrying out your tests over there is not exactly a feasible solution. In fact, this is the same as performing your testing in production. And just as with any regular application development, what we really need is a different environment in which we can test out our smart contracts. So this environment should be something which is very similar to the main Ethereum network and simulates many of its features. This includes having multiple nodes, a consensus algorithm, and so on. Once we are done with contract development, we would like to deploy the contract onto that network, and then following it, we would like to interact with our contract exactly as we would as though it were on the main network. And very importantly, we would like to be able to call different methods in the contract and invoke transactions without having to spend any real Ether. So similar to having a testing environment for any regular application development, what we need is a testing environment for smart contracts. A separate blockchain network for testing will help us confirm the logic defined in our smart contracts. So we could write a number of tests in order to do this, and these tests will be executed once we have deployed our contract to this test network. To understand exactly how a contract would work on the main Ethereum network, it is important for this test network to have an environment which is similar to Ethereum main. And when invoking transactions during our tests, we don't want to spend any real Ether. It is exactly to satisfy these requirements that Ethereum has provided for us 3 different Ethereum test networks. These are the Ropsten network, there's another network called Kovan, and the third network, which we will use during the labs in this learning path, is called Rinkaby. Let us take a look at each of these in a little more detail, starting with the Ropsten test network. So this is very similar to the main Ethereum network, and just like the main network, it uses the proof of work algorithm to achieve consensus among the nodes. A new block is added to the Ropsten network every 30 seconds, and this contrasts with the 15-second frequency for the main network. In order to connect to any test network, you will need to make use of an Ethereum client, and Ropsten is supported by both Geth as well as Parity. These are among the 2 most popular Ethereum clients out there. Moving along now to the Kovan test network. Unlike Ropsten and Ethereum main, this uses the proof of authority algorithm for consensus. Running transactions on Kovan does not require any real Ether. However, there is some fake Ether which is in use on this network, and in order to receive that, you will need to turn on a faucet, and that can only be done once your existence has been proven to Kovan. You also don't need to worry about running out of the fake Ether, as this is mined as well as distributed on demand. Kovan is not as widely supported as the Ropsten network, as it is only supported by the Parity Client. Which brings us to the final test network, which is called Rinkaby, and this also uses the proof of authority algorithm for consensus. Just like with Kovan, a faucet needs to be turned on in order to receive Ether, and this can be done only when your existence is proven using a social media post. At the time of recording, Rinkaby is only supported by the Geth Ethereum client. And with that, we head to the summary of test Ethereum networks. These networks allow us to test code before deploying them to the main Ethereum network. And very importantly, they allow us to play with fake Ether so that we don't incur any real costs during testing. This is why most developers of distributed applications use the test networks for their alpha and beta releases. Once the performance of the contract on these test networks is deemed satisfactory, it can be deployed to the main network. In this clip, we will take a look at one of the other components which makes Ethereum work, and this is the Ethereum Virtual Machine, or EVM. The EVM is a software which is capable of running the instructions of a smart contract. If you're familiar with the Java programming language, you can think of this as being similar to the Java virtual machine. So just as the JVM is able to execute code which was written in the Java language and then compiled to Java bytecode, the Ethereum virtual machine can execute Ethereum bytecode. The Ethereum virtual machine can execute Ethereum bytecode. So that brings us to the topic of what exactly is the Ethereum bytecode? Well, this is simply a binary representation of a smart contract. Ethereum smart contracts are typically written in a high-level programming language, the most popular one being Solidity, and once that code has been compiled, it produces a binary version of that smart contract, which is the Ethereum bytecode. While the bytecode alone can be used in order to execute a smart contract, it can be useful to know that the bytecode itself can be broken down into multiple opcodes. Each individual opcode in Ethereum translates to an action. So just to summarize, any smart contract for Ethereum can be written in a high-level programming language like Solidity. This can be compiled to a binary version called Ethereum bytecode, and the bytecode itself can be broken down into a number of opcodes. However, it is only the bytecode which is required in order to execute a smart contract, and in order to do that, we can use the Ethereum virtual machine. Let us see exactly how that works in practice. So here, we have a simple hello world program written in the Solidity programming language. I won't get into the details of exactly what this code does, but it is enough for you to know that it generates a contract called hello world, which includes a function called print hello world, which returns a string hello world. Once this has been compiled using a Solidity compiler, it will generate some bytecode. While this bytecode will not make any sense to us when we take a look at it, given it's a binary representation, this is something which can be understood by the Ethereum virtual machine. The bytecode itself is in fact made up of a number of different opcodes, and each opcode translates to an individual action. If you have done any assembly language programming, you can see that the opcodes over here are very similar to what you might find in some machine languages. In order to execute a smart contract, we simply need to feed in the Ethereum bytecode to the Ethereum virtual machine, and then this will be able to translate the instructions and then execute them. So the opcodes aren't directly necessary in order to execute a smart contract. So what exactly is the purpose of having opcodes? Well, from taking a look at the opcode for a hello world contract, let us zoom in on the first few opcodes. So you can see here that there are two push instructions at the very top. These are used to push data onto a stack. The next opcode of mstore will store 1 byte of data into memory, while the call value opcode is used to retrieve the value which was passed during a transaction. What is evident here is that each of these opcodes translates to a rather granular operation. Each of these works on a few bytes of data at most, and you require several opcodes to define even a simple hello world contract. So what exactly are these opcodes useful for? Well, even though all of these opcodes are rather granular, each of them may have varying degrees of complexity. And as touched upon previously, complexity in the world of Ethereum is measured in terms of gas. For instance, each of the push instructions here consumes 3 units of gas, as does the mstore instruction. The call value instruction, however, only consumes 2 gas units, whereas the dupe1 once again consumes 3. So while each of these opcodes maps to a certain value of complexity, when you sum them all up for a particular transaction invoked from a smart contract, what you end up with is the total complexity of the transaction itself. The transaction fee, which is paid by anyone who invokes a transaction, to the miner who ultimately adds it to the blockchain is proportional to the complexity of the transaction, and this complexity is calculated by summing up the gas prices for each of the opcodes which make up the transaction. Ethereum has defined a number of different opcodes, each of which has a gas price associated with it. And for a full list of these EVM opcodes and their corresponding gas prices, you can visit this particular website. This is github.com/trailofbits/EVM-opcodes. We saw in the previous clip that any smart contract which is written in a high-level programming language like Solidity can be fed into a compiler in order to generate bytecode. This bytecode, in fact, translates to a number of opcodes, and this is also something which is produced by the compiler. As an example, we had taken a look at a simple Hello World program written in Solidity. And following that, we saw that this is in fact translated to these lines of bytecode. In case you're wondering, this is in fact the actual bytecode of the Solidity code which you see in front of you. So once we have the bytecode for a particular smart contract, this can be used with an EVM in order to run the contract code. However, if someone were to only give us the bytecode of a smart contract, and in fact, this is exactly what is saved on the blockchain network, you can see that it is not possible for us to decipher exactly what this contract represents by merely looking at the bytecode. So if there was a method in the smart contract which we wanted to invoke, we can't really tell what methods it contains in the first place. This bytecode includes a function called print hello world, but there are no interfaces available here in order for us to invoke it directly. The same can be said with the opcodes as well, and while this is definitely a lot more human readable than the bytecode, it still doesn't give us any information about what methods are contained within this contract code. So, if we were to know the location of a smart contract on the blockchain network, this will give us access to the bytecode of that contract. While the bytecode itself can be executed, smart contracts are only useful if we can pick the specific methods which we would like to invoke, and the bytecode alone does not allow us to decipher these methods. So, if you would like to execute specific methods which are defined within a smart contract, what we really need are some details about those methods and some interfaces in order to access them. And what can provide this information to us? Well, an application binary interface is one such structure. This is in fact simply a JSON file, and within it, it includes descriptions of the contract itself and each of the functions which are defined within it. The description will include the function parameters as well as the return types. Given these descriptions, we have all the necessary information in order to call the functions from a smart contract. To understand exactly what an application binary interface or ABI looks like, let us go back to our Hello World program in the Solidity language. You can see, for example, that this includes a function called print hello world, which takes in no arguments, but it returns a string value. And the ABI file for this contract, well, this is what it looks like. You can clearly see that this is a JSON definition and that the name of the function which is defined here is print hello world. The inputs field shows that this does not take in any arguments, and the outputs field confirms that there is just a single value which is returned, and this is of type string. So this is all very useful, but how exactly is an ABI file generated? Well, this is also an output of a smart contract compiler. So along with the bytecode of a contract, which enables the contract code to be executed, and the opcodes, which allow us to calculate the complexity of operations in a contract, a compiler can also generate an ABI file. What we really need are simply the ABI and the bytecode. So the ABI file, as we have seen, includes a description of the contract. However, this is something which cannot be executed on its own. The bytecode, on the other hand, can be executed, but does not really include any context of the contract. So we don't really know, for example, what methods are included within the contract. However, a combination of the ABI and the bytecode does give us all of the necessary information in order to invoke and then execute specific methods in the smart contract. So if you happen to have a rather large contract with a number of different functions defined within it, you will probably call just a single function at any given time in order to invoke a transaction. And the way to do this is by a combination of the bytecode and the ABI for the contract. Once you have the two of these, it is possible for you to call specific methods in a smart contract and then invoke the transactions which you need. In this clip, we will be taking a look at Ethereum Clients. These are essentially pieces of software which allow your machines to connect as nodes to the Ethereum network. But before we delve into the details of Ethereum Clients, let us first take a look at the different types of nodes which are supported in Ethereum. The most sophisticated of the nodes are the full nodes, which store the entire blockchain and can also participate in activities such as mining. This may involve too many resources for a lot of participants in the Ethereum network, which is why Ethereum also supports the concept of light nodes. These do not need to participate in the mining process or even store the entire blockchain, but they will have the ability to originate transactions. And finally, there are also archive nodes which store the various intermediate states throughout the life cycle of the blockchain network. Let us now examine each of these nodes in greater detail, starting with the full Ethereum nodes. These nodes should be able to verify transactions as well as entire blocks, and before they start working, they need to download a copy of the entire blockchain, and the size of the Ethereum blockchain is now in terabytes. So this requires a lot of storage space. So in addition to storing all of the transaction data in the blockchain, full nodes are also tasked with the responsibility of storing and then maintaining the blockchain state. This includes all of the state related to externally owned as well as contract accounts. You can see here that full nodes are tasked with a lot of responsibility in an Ethereum network, and these are the ones which essentially make Ethereum work. However, all of this work which they need to perform will involve significant use of resources, whether it is storage space in order to store the blockchain and the state, or processing power and memory usage, which is needed in order to verify transactions and blocks. So there must be some way in which full nodes can be compensated for all the responsibility they have taken up. And this is done by allowing these nodes to participate in the mining process. If they successfully mine blocks on the Ethereum network, they will be credited with the mining rewards, which includes the transaction fees associated with all the transactions which are added to a block, as well as newly minted Ether. It is the privilege of participating in the mining process and potentially reaping its rewards, which serve as the incentive for nodes to participate as full nodes in the Ethereum network. But within full nodes as well, there is a further categorization. Full nodes can sync up to the Ethereum network using a full sync, and this is where they will retrieve all of the data related to the Ethereum blockchain starting from the Genesis block. They will then need to verify each and every block independently, and as you can imagine, this is going to be a rather slow and painstaking process which can take in the order of a few days. The benefit of doing a full sync, however, is the increased security which comes with verifying every single transaction in every single block, so that you know for sure that you're working with a copy of the blockchain which has not been tampered with in any way. So while every single transaction since inception will be downloaded and then verified by a full sync, when it comes to storing the state of the Ethereum network, a full node will only store the most recent state. That is, they will not store any of the intermediate states during the life cycle of the blockchain network. So a full Ethereum node, which is running in the full sync mode, will perform a comprehensive verification of the transactions. This is in contrast to a full node which is running in the mode of fast sync, where only the most recent blocks will be retrieved rather than all the blocks starting from the genesis block. And even with these most recent blocks, it is not necessary for a node running in the fast sync mode to verify every single transaction in those blocks, but it simply needs to verify the proof of work for those blocks, which is a much more efficient operation. This is precisely why a fast sync takes a lot less time than a full sync. However, once the fast sync has been performed, this node needs to function as a full node which performs a full sync. That is, it needs to verify every single transaction and block which comes after the point of syncing. The node can also be tasked with storing all of the intermediate states after the sync has been performed. So with that, we come to the end of the description of full nodes in an Ethereum network, and we can now move along to light nodes. And in this case, the nodes do not need to store all of the transactions by storing the blockchain or even the state of the blockchain network. They do not have any responsibility when it comes to verifying transactions either. So, given that they don't participate in any of the responsible work in Ethereum, they do not have the privilege of reaping any of the rewards associated with mining. It is possible to originate transactions from light nodes. To do that, however, they need to be able to connect to full Ethereum nodes or mining pools. It is those full nodes which will try to process the transaction by mining them. The benefit of using light nodes, of course, is the fact that the resource requirements are rather low. It is possible, for instance, to run a light node out of a mobile device. And with that, we now move along to the last type of node in Ethereum, which is the archive node. And these are nodes which contain the same data as full nodes. That is, they contain all of the blockchain data starting from the genesis block and will also contain the most recent state data. However, how they differ from full nodes is that in addition to the most recent state data, they will also contain all of the intermediate states at each individual block. As you can imagine, the storage requirements for an archive node will be huge. However, the benefit of having such nodes is that looking up of historical states can be very quick. So rather than building up a state up to a certain point by replaying every single transaction since inception, you simply need to look up the corresponding state at a particular block. So now that we know the three different types of nodes which are supported in Ethereum, the question now is, what are the hardware and software requirements in order to run an Ethereum node, whether it is a full node, a light node, or an archive node? So if we wish to participate in the Ethereum network and we wish to run a light node, then we know that there is not much resource utilization required for this. In fact, it is possible for us to run a light node from a mobile device, and we can originate new transactions from these devices. However, we will need to connect our node to a full node or a mining pool so that our transactions can be mined and processed. In order to run as a full node on Ethereum, it is important to know that you do not need a lot of CPU or memory. However, as long as Ethereum uses the proof of work algorithm for consensus, having more CPU and memory will increase the chances of becoming a successful miner of a block and thus reaping the mining rewards. However, what is needed in order to become a full node is the ability to store the entire blockchain as well as the blockchain state. And for this, we have seen that the disk requirements are very high. The main Ethereum blockchain now occupies a few terabytes of space, and it will be much more efficient if this can be stored on a solid state device rather than on a magnetic disk. This is especially the case when it comes to syncing up your full node, where the sync process can end up taking several days if the data is written to a magnetic disk. So the requirements for an archive node are similar to that for a full node, And now that we know the hardware requirements in order to participate as a node in the Ethereum network, we also need to make use of some software which will allow our machines to perform all of the functions which are required of an Ethereum node. This will include syncing up the node, mining, and even transaction verification in the case of full nodes, and the ability to connect to full nodes or mining pools and then invoke transactions, which will be required of light nodes as well. So a software which is able to perform all of these operations is an Ethereum client. In the next clip, we will get down into the details of what exactly an Ethereum client needs to do. In the previous clip, we learned that an Ethereum client allows a particular machine to function as a node in the Ethereum network. We have seen that whatever the type of node one connects as, whether it is a full node, a light node, or even an archive node, there are many different functions which need to be carried out. So what are these functions which an Ethereum client will perform? So first of all, you need to connect to the Ethereum network, and this needs to be done regardless of the type of node you're running. Following that, the client software can help you deploy and then execute smart contracts. This is especially required in the case of full Ethereum nodes. And in order to run smart contracts, one may need to invoke transactions. And this is also an operation which an Ethereum client will need to do. If you're running as a full Ethereum node and you wish to reap the rewards which come with that, then you need the ability to mine new blocks. And once again, it is the Ethereum client which should allow you to do this. Other functions of Ethereum clients include the ability to sync your nodes to the Ethereum network. So when you're running as a full node, you may need to perform either a full sync or a fast sync. And once a sync has been performed, you will need to maintain the state of the blockchain. Once again, this is something which the Ethereum client will do for you. Many Ethereum clients will also provide some kind of user interface. This could be a command line interface or even a graphical one, which will allow you to interact with the Ethereum network. And finally, Ethereum clients should ensure that you're making the best use of the available resources. So if you're performing mining operations, for example, this should make the best use of the available CPU, memory, and disk resources. So given all of these responsibilities, what are the different types of Ethereum clients which are available for us? The most widely used client is known as Get, and this has been written in the Go programming language. The next most popular client is known as Parity, and this is written in Rust. There is also a C++ client available, which is known as CPP Ethereum. If you wish to use a Python-based client, there is one known as PyEthap, which you can use. And there is also a Java client, which is currently available, and this is known as Harmony or Ethereum J. But out of all of these clients, there are just two which are most widely used, and pretty much all of the documentation which you will find online will be for these clients as of March 2019. So these are the Get client and the Parity client. Let us now take a look at each of these in a little more detail, starting with Get. So this is in fact the official reference implementation of an Ethereum client. As discussed earlier, this has been written in the Golang programming language, and it has support for full, light, as well as archive nodes in Ethereum. Moving along to the Parity client, this is a third-party implementation and is not the official Ethereum client. This is written in the Rust programming language, and one of the biggest benefits of using Parity over Get as of March 2019 is that Parity allows full nodes to prune some of the historical data. This significantly reduces the amount of storage required in order to run a node, and it is possible for you to set a limit on the size of data which is stored. This is not the case with Get, however, where the storage requirements keep growing along with the size of the blockchain. So all of these are examples of an Ethereum client, which, as we have discussed, is an application which will allow any machine to perform the functions of an Ethereum node. So we have discussed some of the basic Ethereum clients so far, but there are a few which are built on top of these. The first one we will explore is the Ethereum Wallet application. So this is in fact a GUI client. So you can interact with an Ethereum network using a very simple GUI rather than having to type commands which you would if using get directly. However, just because there is no CLI for you to work with does not mean that get is not present at all. And this is because Ethereum Wallet simply runs on top of get. So just as get is the official Ethereum client, Ethereum Wallet is the official Ethereum Wallet and UI client. The Ethereum Wallet application is very closely linked with the Mist browser, and in fact, it is hard to separate the two at the moment. The wallet application, as the name suggests, works as a wallet of Ethereum accounts. A wallet in the world of blockchains refers to some kind of software or hardware where you can store all of the private as well as public keys corresponding to your accounts. In the case of Ethereum Wallet, all of the keys corresponding to your Ethereum accounts will be available, and it will also allow you to access all of the Ether which is stored in those accounts. So once you have access to your Ethereum Wallet, there are interfaces available which will allow you to work with Ethereum distributed applications. These include the ability to interact with smart contracts. So with this in mind, let us take a look at some of the applications of Ethereum wallets. There are interfaces available which will allow you to define the code for your smart contracts and then deploy them. And once smart contracts have been deployed, you can invoke transactions from those smart contracts and also on other smart contracts which have already been deployed to the network. In order to interact with already deployed smart contracts, you will need to make use of the address of the smart contract, and along with that, you will also need to provide an interface file such as an application binary interface or ABI. With the contents of the ABI file, the Ethereum wallet applications will know what functions are present in your smart contract and what their parameters and return types are. This will allow you to invoke transactions on that smart contract. And then in order to run that smart contract itself, the bytecode will be available at the contract address. If you have multiple accounts in your Ethereum wallet, then you have the ability to select which of them will be used when you're invoking transactions. And as we have discussed, all of this is necessary in order for your wallet to work with Ethereum distributed applications. So with all of this, we now have an understanding of what exactly Ethereum clients offer. We have seen that there are different types of Ethereum nodes, such as light nodes, full nodes, as well as archive nodes, each of which serves a different purpose. Full nodes require very large disks in order to store the entire blockchain, as well as maintain the state, but the hardware requirements for light nodes are not that high. However, all nodes will require some kind of client software, and this is exactly what Ethereum clients are. Get and Parity are the two most widely used Ethereum clients, and they both provide a nice command line interface in order for us to work with the Ethereum network. Then there is the Ethereum Wallet application, which is a UI-based client which is built on top of Get. This not only serves as a wallet where you can store all of the private as well as public keys for your Ethereum accounts, but it also contains a rather intuitive GUI to interact with contracts as well as user accounts. In this clip, we will take a look at one of the most popular Ethereum clients, which is available as a simple browser extension, and this is known as Metamask. Before we get into the details of what Metamask is, let us take a look at some of the history of Ethereum. When the Ethereum network first came out, if you wanted to define a smart contract and then invoke transactions on that contract, you'll first need to deploy that contract onto a full Ethereum node in the network. You can then invoke the contract code using an Ethereum client such as Get, and this requires a fair degree of familiarity using a command line interface and also Get specific knowledge. On top of all of that, it was the responsibility of the user to install, configure, and maintain an Ethereum node from which they are invoking transactions. Every Ethereum node back in the day used to be a full node. And as you can imagine, running full Ethereum nodes involves a lot of overhead. Not only do you need to set up, configure, and then maintain all of the hardware and the software needed to run a full node, you also need the ability to scale your infrastructure according to the requirements. As the Ethereum blockchain keeps growing in size, depending on the client which you are using, you will need to scale up the amount of disk space which you have on your system, and over a long period of time, this can incur significant costs. This is clearly not a requirement for many different users who simply want the ability to invoke transactions and are quite happy to pay a small transaction fee in order for someone else to take care of all of the work around mining and then maintaining the infrastructure for a full node. In addition, running a full Ethereum node is not possible from mobile devices. And if you want mobile applications to have the ability to originate blockchain transactions, then we need to do away with the requirement that you need a full node in order to create them. So, what is really required in order to work with Ethereum without having to run a full node is a light client. This is a client which has the ability to interact with smart contracts which have already been deployed to the Ethereum network. And very importantly, this client should also have the ability to serve as a wallet. That is, it can securely store any Ethereum account related information, including the private keys which belong to them. Such a lightweight client should have the ability to invoke transactions from one of the accounts in the Ethereum wallet. And once these transactions have been created, they will need to be relayed to a full node where the transaction can actually be mined. So, what we really need then is a lightweight client which is able to interact with the Ethereum network through a full Ethereum node. And this is precisely what Metamask is. Metamask is a rather lightweight browser extension which is available for both the Chrome as well as Firefox browsers. This has the ability to execute distributed applications without having to run a full Ethereum node. It allows one to connect to any of the Ethereum networks, including the main network and the test networks. We know that light Ethereum nodes cannot connect directly to the network and will need to go through a full node. And Metamask does exactly that by relaying any transactions which originate in it over to a service known as Infura. Infura is a company which maintains a collection of full Ethereum nodes, and though this is not visible to you, Metamask will relay all of the transactions over to Infura. It is on an Infura node where the processing of a transaction will actually begin. Metamask not only submits your transactions over to Infura and hence to the Ethereum network, it also manages an Ethereum wallet. So all of the details related to your accounts, including your keys, can be managed using Metamask. While it's not possible for you to invoke transactions from a smart contract directly from Metamask, there is a specific type of transaction which you can originate from here, and this is the transfer of Ether. So while users of the Metamask client will be interacting with its interface directly, what goes on behind the scenes is that any interaction which starts off in Metamask is relayed over to Infura. So what purpose does Infura serve? Well, from Metamask, you can send over your signed transactions to Infura, and then Infura in turn will relay these transactions to the Ethereum network for mining. In order to do that, Infura will need to run a number of full Ethereum nodes, and it will completely take care of the installation of whatever infrastructure is necessary for that. The configuration as well as the maintenance of the full nodes will be taken care of by Infura, and they will ensure that their services are both reliable as well as scalable. So as more and more requests come in from more and more Metamask users, it is up to Infura to ensure that they have the ability to process all of those requests. So just to summarize what exactly Metamask is capable of, this provides us with the ability to link an Ethereum wallet with the Ethereum network. So we can pick the account from which we wish to originate transactions and then relay them over to the Ethereum network. And this does not happen directly, but using an intermediary service known as Infura. So we have discussed the ability of Metamask to originate transactions which are relayed over to the Ethereum network. But consider the case now where you have a distributed application which is running on some website, and you wish to invoke a transaction on that distributed application by using one of the accounts which is present in your Metamask wallet. Well, Metamask will allow you to do exactly that by using a process known as a Web3 injection. Since Metamask runs as an extension in your browser, it will insert a Web3 interface into every single web page which you visit. If that web page happens to be running a distributed application, then it can use that Web3 interface in order to sync up with the accounts which are listed in Metamask, and any transactions which you invoke from that distributed application will go via Metamask. So with this in mind, let us take a look at what exactly this Web3 object is. So Web3 is an interface which allows one to interact with the Ethereum network. All of the interactions happen via JSON RPC calls, which are completely abstracted from the user. The user only needs to interact with the distributed application itself using whatever interface is provided there. If a transaction is invoked from the distributed application, it will need to make use of one of the accounts which is defined in Metamask, and these account details can be accessed using the Web3 object. If you have multiple accounts in your Metamask wallet, then you can pick which one of those you wish to use for that specific transaction. However, all of this is possible only if the distributed application which you're accessing can make use of injected Web3. Any Ethereum-enabled application will need to look for this injected Web3 object before it can invoke any transactions which will be sent over to the Ethereum network. So just to summarize all of the steps when working with a distributed application, if a transaction needs to be invoked from that application, the code for that transaction will look for an injected Web3 object, and the injection of that Web3 object is done by a client such as Metamask. This transaction will then go through Metamask, where you can pick the account within your Metamask wallet which will be used for that transaction. That transaction will then be submitted to Infura, which in turn will submit it to the Ethereum network for mining. In this clip, we will be focusing on all of the tools which are needed in order to both develop as well as execute smart contracts on the Ethereum network. We begin though by first taking a look at what exactly we need in order to run smart contracts once the coding for that has been completed. So once we have the code for the contract, we need to be able to compile this to the Ethereum virtual machine bytecode. While the bytecode can be executed, in order for us to meaningfully interact with the smart contract, we will need to know what functions it contains and what the parameters for each of those functions are. This information will be available in an interface file, and the application binary interface or ABI is an example of such a file. While the ABI file and the bytecode will allow us to interact with our contract, we also need to be able to calculate the gas consumed by the operations, and for that we'll need to make use of the opcodes of a smart contract. And before that, we will need to develop our smart contract and define all of the contractual clauses using a high-level programming language. There are a number of different smart contract languages which can be compiled to Ethereum bytecode. And these include the Solidity programming language, which is by far the most mature and the most widely used language to develop Ethereum smart contracts. In addition, there is also a language known as Serpent, and from the name, you may have guessed that this has some similarity with the Python programming language. There is also a smart contract language known as LLL, which stands for Low Level Lisp. This has a syntax which is very similar to the Lisp programming language. And given the popularity of Python these days, there is one more smart contract language which is very similar to Python, and this is known as Viper. We will now focus a little more attention on just one of these languages, specifically the Solidity programming language, which is the most widely used one. So as mentioned, this is a high-level programming language, which is also object-oriented. In fact, Solidity has been strongly influenced by C++, Python, as well as JavaScript, and the syntax is in fact very similar to the JavaScript language. A few things to keep in mind before using the Solidity language include the fact that it is statically typed. This means that each of the variables which you use need to have a type associated with them. This means that the type checking phase occurs at compile time rather than at runtime. Given it is an object-oriented language, Solidity supports user-defined types, and the concept of inheritance is also supported. A smart contract in Solidity can reference other smart contracts. This is similar to other object-oriented languages where you can have some types reference other types. So once you have coded up your smart contract using Solidity, how exactly can you compile it and then run the Solidity contracts? Well, there are a few different options available for us, but let us focus on two of these tools. One of these is Solc.js, and another very popular tool available out there is the Remix IDE. Let us focus first on Solc.js. These are in fact JavaScript bindings for the Solidity compiler. Solc.js includes a CLI as well as a high-level API in order to compile and then execute your smart contract code. And this is something which can be downloaded using the Node Package Manager or NPM. Since Solc.js is a tool which you can install onto your own laptop, it is something which allows you to compile and then work with your smart contracts even while you are offline. This is in contrast to the Remix IDE, which is an online IDE for the Solidity programming language. This IDE is entirely cloud-based, which means that there is no installation necessary on your part. All you need is a web browser and an internet connection. The Remix IDE is a distributed application and it can integrate with the Metamask client. This means that once you have coded up your smart contract, if you wish to deploy it to an Ethereum network and then test out its functionality, you can trigger all of the necessary transactions for that to happen through the Metamask client. This is because the Remix IDE can be configured to look for an injected Web3 object in order to connect to an Ethereum network. And this Web3 injection is something which a client like Metamask will be able to do. And finally, the URL at which the Remix IDE can be accessed is right here. So this is available at remix.ethereum.org. If you're building an Ethereum-enabled application, which are commonly referred to as distributed applications or dApps, there are a few options available for you to build, test, and then deploy your applications. We will now focus on one of these sets of tools, and this is known as the Truffle Suite. So let us first examine what exactly we require when we are developing a smart contract. First of all, we need access to a compiler which is able to transform our contract code, which is written in a high-level language like Solidity, into Ethereum Byte code which can be executed. Once that has been done, we'll want to deploy that bytecode into one of the available Ethereum networks. This could either be the main network or one of the test networks such as Ropsten, Kovan, or Rinkaby, or even a private Ethereum network. Following the contract deployment, we will want the ability to execute the code which has been written in that contract, and this will need to be done in order for us to test out all of the features which have been defined in the contract. There are two tools which we have already discussed which allow us to do these tasks, and these include Solc.js as well as the Remix IDE. So while these allow us to build, test, and then deploy our contract code, following which we can execute the code in order to test them. There are several other techniques which can be adopted in order to simplify the development of these contracts and then speed up certain tasks. For example, if we had a predefined structure for each of our contracts and then some way to enforce it, then this will simplify the development as well as maintenance of our code. In addition, automated testing for each of the features in our smart contract will also greatly speed up our development. If we define test cases for every single feature, as the contract gets more and more features added to it, all of the older features will be tested automatically each time we perform a deployment. This will greatly reduce the need for manual testing of the features in our contracts, and hence it will greatly speed up contract development as well. Another useful feature will be the integration with the Ethereum main as well as test networks. This will help us deploy applications to the test networks, perform the automated tests, and if those tests pass, we can define a script to automatically perform a deployment to Ethereum main. And another useful feature, which will especially come into play during the development phase of our smart contract, will be the ability to set up and integrate with private Ethereum networks. Even though the use of Ethereum test networks does not involve the use of real Ether in order to perform our tests, there is still some overhead involved in procuring the fake Ether for those tests. In the case of the Rinkaby network, for example, we need to turn on a faucet, which can be done by using a social media post. During the development phase, where we need quick feedback for any code changes which we have performed, this may be too much overhead, and deploying to a private network may be the most efficient way to test out our code. So what we really need is a development framework for smart contracts in Ethereum, and this is precisely where the Truffle Suite comes into the picture. This is in fact the most popular development framework for Ethereum. So what are the features offered in the Truffle Suite which greatly help speed up development? Well, for one, it provides us with a standardized file and directory structure which will ease the deployment as well as testing of our application. There are also tools available to automate contract testing using the Mocha as well as Chai testing frameworks. In order to perform alpha or beta testing, we have the ability to deploy our smart contracts to the test networks of Rinkaby, Kovan, or Ropsten. And once that testing has passed, we can also deploy our app to the main Ethereum network using the Truffle Suite. And during the development phase, for quick feedback on any of our code changes, we could also choose to deploy our smart contract to a private network which has been provisioned using the Ganache Framework. So while all of these will allow us to very quickly perform development and then building, testing, and deploying our applications, if we wish to develop user interfaces for our distributed applications, then there are tools available in the Truffle Suite to help us with that as well. So the Drizzle tool in the Truffle Suite provides us with a number of standard libraries which can be used for UI development for distributed applications. So let us quickly summarize the different tools which are available within the Truffle Suite. First of all, there is the Truffle framework, which simplifies a lot of the tasks related to building, testing, and then deploying our smart contracts. There is Ganache, which will very quickly provision a private Ethereum network to which we can deploy our applications. And then there are also a number of different accounts available for us to use, which have been loaded with Ether. And finally, there is Drizzle, which includes a number of different libraries which can be used for UI development for our distributed applications. Let us now focus on each of these in a little more detail, starting with the Truffle framework. This provides various tools for smart contract lifecycle management, and this of course includes building, testing, and deployment. In the case of testing out our smart contracts, the Truffle framework allows integration with the Mocha as well as Chai testing frameworks, which allow you to programmatically define exactly which tests you need to run, and this will greatly speed up the testing by simply automating it. And it's not just testing which can be automated using the Truffle framework. It also allows you to write out a script in order to deploy your application and potentially define a script for migration of your app as well. We move along now to the Ganache Framework, which will very quickly provision a private Ethereum network. And this network includes not just a blockchain, but also a number of different accounts which have been loaded with Ether. The blockchain network which Ganache has provisioned can be configured, and this can be done so that there is no mining necessary. Some of the Ethereum test networks add a new block to the blockchain only once every 30 seconds or so. And this is something which you can do away with in a private network so that you get much quicker feedback for your changes. Once your transactions have been processed by this private network, you may wish to see how exactly it looks within the blocks of the blockchain. And Ganache includes a built-in block explorer which allows you to do exactly that. In case you wish to view the logs which have been generated by your contract, Ganache includes an interface which allows you to view the logging data as well. And this brings us to the final piece in the Truffle Suite, which is Drizzle. As mentioned earlier, this includes various libraries for UI development of your distributed application. And Drizzle also includes various React components which you can use in your dApp. Since these libraries make use of JavaScript, you can access all contract and account related data using the Web3 interface. So with that covered, let us quickly summarize what exactly the Truffle Suite offers. We have seen that development of smart contracts involves many different tasks, and these tasks can be simplified by using a framework. The Truffle Suite includes a number of different tools, and these are called the Truffle Framework, the Ganache Framework, and Drizzle. The Truffle Framework is used for contract lifecycle management. This includes building, testing, and deploying smart contracts. The second tool in the Truffle Suite is the Ganache Framework, which allows you to very quickly provision a private blockchain network. And this network also includes a number of accounts which are loaded with 100 Ether each. And then finally, there is Drizzle, which includes a number of different libraries to speed up UI development for distributed applications. In this exercise, you will first list down the 3 different test Ethereum networks. The equivalent of a testing environment in the case of Ethereum smart contracts are the 3 different test networks which are used by contract developers for alpha and beta testing of what they have built. These test networks do a pretty good job of simulating the environment of the main Ethereum network and do not require the use of real Ether in order to invoke transactions. You will need to identify what each of these test Ethereum networks are and also some of their features. Next, you will identify some of the characteristics of full nodes in Ethereum. When using an Ethereum client such as Get, you can choose to join the Ethereum network as 3 different types of nodes. These are full nodes, light nodes, and archive nodes. And out of these, you will need to list down the specific properties of the full nodes. For the next task, you will list down some of the Ethereum clients which you can use in order to interact with Ethereum networks. There are multiple Ethereum clients available, out of which the Get client is the most popular and which is what we used during the labs of this course. For this exercise, you will need to recall some of the other clients available. And for the final task, you will note down the 3 tools which are available in the Truffle Suite and what each of their specific functions are. The Truffle Suite includes a number of different tools which not only speed up smart contract development, but also allow you to build contracts which are easy to test and maintain, thus maintaining a certain standard of quality. The Truffle Suite achieves this by offering 3 different types of tools, and you will need to recollect what exactly these are. Each of these topics were discussed during this course, so please pause this video and then take some time to perform these tasks on your own. For the first task in the exercise, you needed to recall what the 3 different Ethereum test networks are. The first of the networks which we discussed was the Ropsten test network, and this is one which very closely resembles the main Ethereum network, especially in that it uses the same proof of work algorithm for consensus. The Ropsten test network is also widely supported since it can be used with both the GET as well as the Parity clients. A second test network for Ethereum is the Kovan network, and unlike Ropsten, this uses a proof of authority algorithm in order to achieve consensus among the participating nodes. This network is supported by the Parity client. A third Ethereum test network, and the one which we will be using in the labs of this learning path, is the Rinkaby test network. Like Kovan, this also uses the proof of authority algorithm for consensus, and this is only supported by the Geth Ethereum client. Both the Kovan and the Rinkaby test networks do provide Ether for free. However, the availability of this fake Ether is not unrestricted and needs to be obtained by turning on a faucet. In the case of the Rinkaby test network, for example, the faucet can be turned on and your account loaded with Ether if you make a social media post with your account address. For the next task in the exercise, you needed to recollect some of the characteristics of full nodes in Ethereum. Ethereum full nodes are the ones which carry most of the responsibility of the Ethereum network. Their responsible work includes verifying the transactions as well as the blocks which are added to the Ethereum blockchain. In addition to this, they are also tasked with the responsibility of storing and maintaining the blockchain state. All of this work, of course, does come at a cost, and in order to incentivize nodes to participate in the network as full nodes, it is only these kinds of nodes which have the privilege of participating in the mining process. If one of these nodes were to successfully mine a block and add it to the blockchain, then they get to keep all of the transaction fees associated with the transactions which were included in the block they just mined. On top of those rewards, Ethereum also issues newly minted Ether to the successful miner of a block. One thing to keep in mind for anyone who participates in Ethereum as a full node, however, is that such nodes have very high disk requirements. Depending on the type of client being used, full nodes may be required to store the entire Ethereum blockchain, which at the time of this recording is a few terabytes in size. For the next task in the exercise, you needed to list down some of the Ethereum clients which are available. We have already mentioned the Get Ethereum client, which is the official client available, and this has been implemented using the Go programming language. We also touched upon the Parity client, which has been written in Rust, and both of these are the most popular clients in use right now. There is also a C++ client available, and this is known as CPP Ethereum. PyEthap is a Python-based client, and there is also one written in Java, which is known as Harmony or Ethereum J. And finally, you needed to list down the 3 different tools which make up the Truffle Suite and what each of their individual functions are. The Truffle Suite is a suite of tools which greatly speeds up smart contract development. Out of these, the Truffle Framework is one which is used for contract lifecycle management. That is, it can be used in order to build, test, and deploy a smart contract to different networks. And this includes a number of different features. For example, integration with the Mocha and Chai testing frameworks in order to automate your testing. And it also includes contract generators in order for your smart contract apps to have similar structures. Then there is the Ganache tool, which helps you quickly spin up a private Ethereum network. During the development phase of your smart contract, you may not want to deploy it to one of the test networks, given that it does involve a little bit of overhead and that the availability of the fake Ether is not quite unrestricted. With a Ganache network, on the other hand, a new Ethereum network is spun up each time you open the Ganache tool, and this network will include 10 different accounts, each of which has been loaded with 100 Ether. This will allow you to quickly deploy your contract and perform a number of tests, and get very quick feedback on your implementation. After the development work has been performed, you can then deploy your contract to one of the test networks in order to perform alpha and beta testing. The third tool which makes up the Truffle Suite is Drizzle, and this includes a number of different libraries which can be used to build the user interface for your distributed applications. All of these three tools of the Truffle Suite put together will provide you with a number of reusable processes, tools, as well as libraries, which will speed up the development of your smart contract and distributed applications. We will now take a look at how we can install and work with Metamask, which is a browser extension meant to access Ethereum-enabled applications from your browser. The extension is available for both the Chrome as well as Firefox browsers, but in this demo, we will take a look at how we can set up Metamask for Chrome. For that, you will need to download Metamask from the Chrome Web Store, and to access that, you can just Google for Chrome Web Store, and then from the search results, the first result should point you to chrome.google.com/webstore. Clicking on that link will take you to the Chrome Web Store homepage. From here, you can make use of the search feature in order to search for Metamask, and in the results, you should see Metamask identified by this Fox logo available. From here, you can click on Add to Chrome so that the extension is added to your browser, and then you can confirm that this extension can indeed be added. And following that, towards the top right of your window, you should be able to see the Fox logo for Metamask. This means that Metamask has now been installed, and you can confirm that by clicking on this, in which case you will see a message which confirms that you can access Metamask by clicking on the logo or through a keyboard shortcut. So now that Metamask has been installed on our browser, it is time for us to set it up and begin using it. So I'm going to close out of this message, and this directs me to the Metamask setup. The message here confirms that Metamask serves as a bridge between us and decentralized applications on the Ethereum network. So we can just hit continue over here, and then following that, you will be prompted to enter a password. This is a password which maps to your Metamask account, and do make note of it once you have created this password. Following that, there will be an image which will be generated in order to identify your account. And then if you move along, there will be the licensing agreement, which you can just scroll down and then hit accept. Following that, there will be the privacy notice, so I'm going to accept that and do the same with the phishing warning as well. And this is where we get to the important part of our Metamask account creation. And this is where there will be a 12-word phrase which will be generated for your account. And this is something which you need to make a note of in order for you to access the Ethereum accounts which will be generated by Metamask on your behalf. So while the password you created just a few moments ago will help you log into Metamask from your current installation in your browser, if you do wish to access your Ethereum accounts from another installation of Metamask or through some other means, then you will need to provide this 12-word phrase. This phrase is deliberately hidden in this view, and this is to emphasize that this is something which needs to be kept secret. However, I do not plan to use the accounts which I'm going to create in this demo, which is why I'll now reveal this particular phrase, and you should see something similar to what I have on my screen right now. This phrase is referred to as a seed phrase or a seed recovery phrase, or even a mnemonic code. And when this is used in conjunction with the BIP39 standard, it will map to a specific set of key pairs. These key pairs correspond to Ethereum accounts. So once you have memorized or saved this particular phrase, you will be able to access your Ethereum accounts from anywhere. We can now proceed by hitting next. And then following that, you will be prompted to enter the key phrase. So all the words which make up your phrase appear at the bottom, and you need to click on them one by one in the order in which they appear in your seed phrase. I'm now going to fast forward until the full phrase has been entered, and following that, hit confirm. And now our Ethereum accounts have been set up and can be accessed from Metamask. we will be given the option to deposit Ether into the account which has just been created. And you can do so by either directly depositing Ether from some other account which you have. Alternatively, you could purchase some Ether from Coinbase, which is an online digital currency exchange where you can purchase Ether, Bitcoin, and other cryptocurrencies. Shapeshift is another option available in order to load your accounts with Ether, but we will be skipping all of these and can just close out of this message. And this will take us into our Metamask account. From this page, we can see that a few things have been set up for us automatically. Starting on the left, you can see that one of the generated accounts has been labeled account 1, and in the top right, you can see the Ethereum network which you have been connected to. In my case, this is the main Ethereum network. The address of the externally owned account which Metamask is currently using is available here. And in order to copy the entire account address to your clipboard, you can simply click on this. We currently see that there is a balance of 0 Ether in this account, and there are no transactions as of yet. Ethereum also has the concept of tokens, and these tokens represent particular assets which can be purchased for Ether. There are no tokens which are mapped to this account as of yet. You can think of tokens in Ethereum as being similar to tokens handed out in many amusement parks. Those tokens can be purchased for regular currencies, but are only valid within the context of the amusement park. Similarly, tokens in Ethereum can be purchased for Ether, but may only be valid in the context of a particular smart contract. We can now continue exploring the MetaMask interface. So I'm going to click on the Fox logo once more, and then from the little window which pops up, click on the menu. Following that, we will get a summary once more of what we saw in the browser page. And once more, there is a confirmation that there are no tokens available for this account. But since tokens are typically defined within smart contracts, if you were to add a token to map onto your Ethereum account, you can do so using this interface by simply clicking on Add Token. We won't get into the details of tokens in this particular demo, but we will see the interface which is available in order to add tokens to an Ethereum account. So clicking on Add Token will give us the option to search for tokens. Alternatively, if you'd like to map a custom token to your Ethereum account, you can switch over to the Custom Token tab and then specify the address of the contract which includes the definition of your token. So we can now cancel out of this since we won't be adding any tokens in this demo. And then following that, we will see how we can switch Ethereum networks. So by default, MetaMask will connect us to the main Ethereum network. However, by clicking on this drop down, you will see all of the other options which are available. The Ethereum test networks of Ropsten, Kovan, and Rinkaby are all available for us to connect to. And alternatively, we can also connect MetaMask to a private Ethereum network. We can do that by using the custom RPC option, where we'll need to define a URL endpoint where the network can be connected to. Continuing along with our exploration of this MetaMask interface, clicking on this button in the top right, we can see various details regarding our MetaMask installation. For one, we can see that account number 1 is the default account for now, and this also happens to be the only account which we have currently configured. We can create and import additional accounts using this interface and also define some of the settings for our MetaMask installation. If you would like to view information regarding account number 1, we can click on these 3 dots over here, and then expanding this will show us a few options available in order for us to see additional details for this account. I'm going to select the one to view the account information on Etherscan, which will show to us all the publicly available information for an Ethereum account on the etherscan.io website. So clicking on this brings up a web page which corresponds to this particular account on etherscan.io. And here we can view some information, including the trading price of Ether on the market. Other available details include the full account address and also details such as the Ether balance in this account, as well as the transactions which originated from it. There are none to speak of course, which you can see in this transaction section below. And there are also options to communicate with the owner of a particular account using this common section over here. So we have now covered many of the options available using the Metamask interface, as well as the details for an account available on etherscan.io. So we can head back to the transactions tab here, which confirms that there are no transactions yet. And I'm going to end this particular demo by closing out this tab. In the previous clip, we saw how we can set up Metamask with our browsers and also saw the options available using the user interface of the Metamask tool. One thing we covered when creating our Metamask account was the fact that there was a key phrase or a seed phrase which was generated, which we were asked to store. That seed phrase maps to a particular set of Ethereum account addresses, and if you were to forget the account addresses or lose the keys which map to them, you can recover them by making use of that seed phrase. Before we do that, do note here that my particular account, which is labeled account 1, maps to an account address which begins with E824. So now I'm going to open up a new tab and then navigate to a website which will help recover the Ethereum account addresses from the seed phrase. This website is called iancoleman.io, and when you navigate to it, you'll see that there are a number of different tools available, but the one we are interested in is the one right at the top. This is the BIP39 mnemonic code converter, and this will be able to map our seed phrase to a set of Ethereum account addresses and their respective private and public key pairs. This mapping of a mnemonic code or a seed phrase to an account address and key pairs is something which is defined in the BIP39 standard. So we will see how this works by navigating to this site. And when we enter this mnemonic code converter page, we have the option to generate a new mnemonic code which will map to a new set of Ethereum account addresses. And this mnemonic can be in multiple languages and need not only be English. However, in order to recover the account addresses as well as the key pairs corresponding to our own Ethereum wallet, in this particular field, we can enter the 12 words which were generated when we created our Ethereum wallet using Metamask. So once that has been entered, the BIP39 seed will be generated here, and also the QR code which maps to our Ethereum wallet will be visible when you hover over this field. The mnemonic also maps to a BIP32 root key, which we won't get into the details of. But what does matter to us is the type of wallet which this particular seed phrase maps onto. So by default, this particular page has selected Bitcoin, and this is because this BIP39 standard is also adopted by Bitcoin. And when we click on this particular dropdown, we get to see the full list of digital currencies which have wallets which make use of this BIP39 standard. You will also see the 3 or 4 character codes representing each of these currencies, and the one we are interested in is ETH, which represents Ethereum. Once this has been selected, we can continue scrolling further down on this page, and then we will see some more details regarding this derivation path, which is again something we won't get into the details of, and we'll continue scrolling down until we get to the derived addresses section. This is where we can see all the different account addresses as well as their private and public keys which map to this particular mnemonic phrase which we entered. You can confirm that this corresponds to your own wallet by looking at the first account address here and then switching back to Metamask, where you will see that this is exactly the same as the account address listed here. So heading back to the Ian Coleman page, we can see the full list of addresses as well as their private and public keys. So if you ever happen to lose your account addresses as well as the keys which correspond to them, you can simply recover them by going to this iancoleman.io website and then typing in the seed phrase or mnemonic phrase which was generated when you created your Ethereum wallet. Heading back now to Metamask, we can see that this particular account does not have any Ether, and for us to be able to use this account to invoke transactions, we will need to load it with some Ether, whether on the main network or on the test networks. The Rinkaby test network allows us to generate some Ether to be used on that network alone, and this can be done by turning on a faucet, and that can be done by making a social media post. So I'm now opening up a new tab and I'm logged into my Google account over here. I will now switch over to the Google account which I will use in order to make a post on the Google Plus social network. The Rinkaby network allows you to generate Ether by making posts on either Google Plus, Facebook, or Twitter. The post needs to include the Ethereum account address which needs to be loaded with Ether. And now let us move along and see exactly how that can be done. So after selecting my Google account, I will now navigate to Google Plus by expanding all of the applications available on Google and then clicking on Google Plus. So from my Google Plus homepage, I'm going to make a post by clicking on this button in the bottom right. And in the form which pops up, we will need to include our Ethereum account address. So switching back to Metamask and then clicking on this particular account, which will copy the full account address to the clipboard, we can head back to Google Plus, and my post is only going to include the account address. So once I click on post, this particular post is now visible on my Google Plus dashboard, but I'm now going to expand this in order to retrieve the URL for the post. So in order to notify the Rinkaby network that we have made a post on a social network, we will need this URL. So once this has been copied over, we can now navigate to faucet.rinkaby.io, which will turn on the faucet, which will load our Ethereum account with Ether for the Rinkaby network. So on the Rinkaby faucet homepage, there is a field to enter the URL of the social media post which you made, which includes the account address to be loaded with Ether. And following that, you can click on this drop down which says Give me Ether to define the rate at which Ether will flow into your account from this faucet. I'm going to choose the option of 3 Ethers every 8 hours. And then following that, you should get a confirmation that your funding request has been accepted. Meanwhile, some Ether will be flowing into your account, but within a few seconds, you will see that your account has been fully funded. And you can confirm that by navigating to Metamask. And then from here, you may need to switch over to the Rinkaby test network if that has not been selected. So I'm now going to switch from main to Rinkaby. And immediately, I can see that this particular account address on the Rinkaby network has 3 Ethers. So one observation you can make over here is that the same account address can map to multiple Ethereum networks. We saw that this account has 0 Ether on the main network, but now has 3 Ethers on Rinkaby. Metamask also gives you the information that these 3 Ethers now correspond to $414 at the prevailing market rate. You will most likely see a very different number. However, you do have Ethers to play with on the Rinkaby test network. That is exactly what we will be doing in the following demos. However, for now, we can close out this tab which represents the Rinkaby faucet and also the Google Plus page. And then finally, we are in the Metamask interface, which confirms that we now have 3 Ethers to play with. In the previous demo, we saw how we can set up Metamask in our browser, and we also explored how we can create an Ethereum wallet which can be accessed from Metamask, and then how we can recover the contents of that wallet by using the seed phrase or mnemonic. We also loaded one of our Ethereum accounts with Ether on the Rinkaby test network. But before we begin to use Metamask in order to invoke transactions, we will explore the use of one more Ethereum wallet application, which is the official Ethereum wallet. To do that, we will need to download some software. So I'll open up a new tab in my browser and then navigate to ethereum.org. From the home page over here, we just need to scroll all the way down and you should see the link to download the installer for the Ethereum Wallet app for your specific operating system. So I'm now going to click on this download link, which will download the installer. But before that, you'll be prompted about some security warnings. So I'm now going to scroll all the way down and then click that I understand and agree to the terms. And then following that, you can save this installer somewhere on your own file system. And once that is done, you can bring it up in order to begin the installation of the Ethereum Wallet app. Do note here that if you're on Windows or some other operating system which is not a Mac, your installation procedure is likely to be different. However, in my case, In order to complete the installation, I'm being asked to drag this particular icon to my applications folder. And then following that, the installation is complete. I'm now going to bring up the application by first bringing up Launchpad and then clicking on Ethereum Wallet. Since this is the first time I'm bringing up this application, there is a warning, and I'm just going to say that this application can be trusted. And now the Ethereum Wallet application is up, and this shows that I'm starting off on a clean slate. There are no accounts which are mapped to this wallet yet. But before we begin using it, we can explore the interface just a little bit. There is a tab labeled Send, which we can use in order to transfer Ether to another account. And this particular section here gives us details about the Ethereum network we are connected to, and also the latest blocks which have been mined. So we are not connected to any Ethereum network yet, which is why we don't see any information here. Any smart contracts which we have created or we have access to will be available using this Contracts tab. And we can see here that there is 0 Ether available within this wallet. We will now define the Ethereum network we want this wallet to be connected to, for which we navigate to Develop, and then from there to the Network section, and then we will select the Rinkaby test network. So once we have set that, we will notice in the top here that we are connected to the Rinkaby test network and to 4 peers on that network. We also get notification about the blocks on that network. So there are a total of nearly 4 million blocks which have been mined. And we also get a notification of the time since the last block was mined on that network. Moving along now to the Send tab, and we see that there is nothing available here, and this is because we do not have any accounts which are mapped to this wallet just yet. We now head back to the Wallet section, and then from here, let us access the Contracts page to see if there is anything visible here. So there are no contracts yet. However, there are options available for us to deploy a new contract to the Rinkaby test network. And we can also watch an existing contract. That is, we can connect to it and then even invoke transactions. In addition to these, there are also custom tokens which we can map to our wallet. And then heading back up on this page, we see that we still have a balance of 0 Ether, once again because we don't have any accounts yet. We will now address that by navigating to Wallets and then click Add Account. Just as with Metamask, we will be prompted to enter a password for our account. So I'm now going to create one over here. And I'm now going to show you the password because this is something we will use later on in this learning path. So this is a rather simple one, which is ABCD1234. Whatever the password is, do make a note of it because it will be required later on. So now we can hit OK and proceed with the account creation, for which we will be prompted to re-enter the password. And once that is complete, we will be notified that a key store file has been created, which includes all of the keys corresponding to this account. This is something which we need to keep securely, just in case we happen to lose the key store file and we need to recover our original Ethereum account. So once you hit OK over here, the Ethereum account has been successfully created. You can see that this contains a new account address and it also has 0 Ether at the moment. There are no contracts which are mapped to this account just yet. But now let us explore more details about this account by clicking on it. And this will navigate us to the account page, where once again we see some additional details. And from this interface, we have a few options. We can transfer Ether or tokens to another account from here. And if you'd like to copy the full address, there is also a button for that. At this point, let us take a look at the key store files which have been generated when we provision this account. And for that, we can navigate to File, and then from there select Backup, and then choose the option Accounts. So this will show us the location on our file system where the key store files have been created. And in my case, this is in my home directory. And within that, there is a directory called Library, within which there is another directory called Ethereum. And within that, there are a number of subdirectories. There is one for the Get client. And this includes some chain data, which we can expand and take a look at the files which it includes. There is one corresponding to this particular Ethereum node. And then there is also a collection of transactions. There is also a directory which contains all of the key store files for our wallet. But since we created our account after we connected to the Rinkaby network, in order to access the key store corresponding to our account, we head over to the Rinkaby directory, and there is a get directory over here as well, but the key store directory here includes the details for the account which we have just created. The file name itself includes the account address for our Ethereum account, and within that there is JSON data which defines our account. And just to confirm that this represents the account we created on Ethereum Wallet, make a note of this account address in the file name. And heading back to our application, we can see this is exactly the same as the account we generated. At this point, we now have two Ethereum accounts. One was created using Metamask, and that contains 3 Ether on the Rinkaby test network. We then made use of the Ethereum Wallet application in order to create one more Ethereum account, and this currently has no Ether. Since both of these are now connected to the Rinkaby network, we will see how we can transfer Ether from the account created in Metamask to the one created in the Ethereum Wallet app. So I'm currently in the Ethereum Wallet application, which is connected to the Rinkaby network, and there are 3 peers it is currently connected to. In this demo, we will be transferring Ether to this account, and for that to happen, we will need access to this account address, and we can copy it to our clipboard using this interface. So once the account has been copied over, we may be issued a warning. So I'm just going to say that this copy can happen in any case. And once this copying has occurred, it is now time for us to initiate this transfer. And since we will be transferring money from the Metamask account to the Ethereum Wallet account, the transaction needs to be invoked from Metamask. So we now switch over to Metamask and confirm that we are on the Rinkaby test network. And on that network, this particular account has a total of 3 Ether as balance. Now, in order to send some Ether from this account to our Ethereum Wallet account, we can hit the send button over here. And doing that will bring up a form which needs to be populated with the details of the transaction we are invoking. So first of all, the account from which the Ether is being transferred, and this is our account 1. And then in the to field, we will now paste the address which we copied over, and this corresponds to our account on the Ethereum wallet. The amount of Ether to be transferred is also mentioned over here, and in our case, we can transfer a total of 1 Ether. And then following that, we can set the transaction fee which we are willing to pay in order for this transfer to take place. The higher the transaction fee, the greater the likelihood of a miner picking up the transaction, and the sooner it will be processed. We can see here that in order for the transaction to be processed quickly, we need to pay 6 times as much as for a slow processing speed. So what exactly does this processing speed imply? For that, we can click on the advanced options, and we can see here that this fast processing will mean that this transaction will be processed in less than 32 seconds. This transaction fee of 0.00042 Ether corresponds to a gas price of 20 gigaway. The higher the gas price, the more likely that a particular miner will pick up the transaction for processing, and the sooner it will be added to the blockchain. We can also define a hard upper limit on the amount of gas to be used in order for this transaction to take place, and this we set to a value of 21,000 gas units. Here we can also view a graph which can help us decide the gas price to set in order for this transaction to occur. This visualization gives us the estimated transaction processing time for various gas prices. Right at the bottom is a summary of this transfer of Ether, which shows us the amount of Ether being transferred as well as the transaction fee. Now, if you have some flexibility with regards to the transaction processing time and it's not that urgent, you can simply hover over this visualization over here in order to get an estimate of the transaction processing time versus the gas price. For example, if we specify a gas price of about 5.89, this transaction could take about 738 seconds in order to finally go through. And of course, if we specify a higher gas price, the transaction is likely to be added to the blockchain a lot sooner. We will now see how we can adjust the gas price here. So we can up the value from 20 to 21, And we immediately see that the transaction fee value gets updated here. This is also visible in the transaction summary below. And if we up the gas price further to 22, the transaction fee value is updated once more. But since I'm in a hurry for this transaction to go through, I'm going to up it to 24 and then even further to 25. And at this point, I'm happy with the total transaction fee value here. And now it is time to save these details. And now that our transaction fee has been set, which comes to a total of 7 cents in terms of US dollars, it is now time for us to move along with this transfer by hitting next. So here we get the summary that we are transferring money from this account 1, which is in Metamask, over to this account address, which corresponds to our account which we created on Ethereum Wallet. We are transferring a total of 1 Ether, and the total gas fee or transaction fee is 0.00525 Ether, which translates to 7 cents in US dollar terms at the time of this recording. The total value of Ether which will be deducted from this Metamask account is the transfer value plus the gas fee. And before we proceed with this transaction, I'd like to point out that the Metamask logo over here for this Chrome extension indicates that there is a notification. And when we click on it, we see the exact details which we have in our browser tab. So we can go ahead with this transaction either over here or back in our browser tab. So I'm now going to switch over to the browser tab and click confirm in order for this Ether transfer to go through. At this point, we can see that this transfer is now pending, and it will take at least a few seconds in order for it to be added to the blockchain. We can now navigate to the Ethereum Wallet application and check whether the account reflects the transfer of Ether to it. So this shows that there is still 0 Ether in this account, and this indicates that the transfer has not yet gone through. But switching back to MetaMask now, I can see that Ether has been deducted from this account, and soon enough, the status of this transaction shows up as confirmed. So we can see now that the transaction has gone through and that Ether has been deducted from this account. The final confirmation, though, is to switch over to our Ethereum Wallet application, and then this single Ether which was transferred is now visible here. So we have now successfully initiated a transfer of Ether from one Ethereum account to another. We have also seen how MetaMask makes it very easy to invoke such a transfer, and that we can also specify values such as the gas price and the gas limit for a transaction. So we have now seen how we can transfer Ether from a MetaMask account to an Ethereum Wallet account by making use of the MetaMask user interface. In this demo, we will take a look at how we can deploy a smart contract to the Rinkaby test network on Ethereum, and for that, we will make use of our Ethereum Wallet application. So within Ethereum Wallet, we currently have one account which has about 1 Ether in it. Before we use this to deploy a smart contract, we will take a look at the interface available in Ethereum Wallet in order to transfer Ether to another account. For that, we navigate to the Send tab, and then over here, in an interface which is similar to MetaMask, we can specify the account from which Ether needs to be transferred. There is also a destination account address, and the amount which needs to be transferred over can also be specified. Scrolling further down on this page, we can also specify details such as how much we're willing to pay for this transaction to go through. And you will notice that there is not as much detail we can specify here as we could in MetaMask. So you could test a transfer from your Ethereum Wallet account to your MetaMask account. However, we will not be doing that in this demo. Instead, we will proceed to the deployment of a smart contract for which we will make use of our Ethereum Wallet application. We'll head over to the Contracts tab in the app, and you'll see right at the top here, there is an option to deploy a new contract. This is what we will be using. But before we proceed, let us take a further look at the options available in this tab. Rather than deploying our own contract, if you'd like to interact with an already deployed contract, you'll need to make use of this Watch Contract feature, where you'll need to specify the contract address along with a JSON formatted interface definition for the contract. This could be an ABI file. That is something we will be doing later on in this learning path. There is also the option to watch custom tokens, and these once again will be mapped to a smart contract. We now move along though, and then create a new contract which we will deploy. So when we click on this Deploy New Contract button here, we will be directed to a page where we need to specify some of the details of the contract we wish to deploy. Firstly, we will need to specify the account which will be used in order to deploy the contract. Any contract deployment will invoke a transaction which will require some Ether. So you'll need to make use of an account which has a non-zero Ether balance here. Since we are connected to the Rinkaby test network, we have a balance of 1 Ether in the specific account, which means that a contract deployment will occur on Rinkaby. We can also deposit some Ether into the contract account, but we will leave that value as 0 for now. And following that, we can define the code of our contract in this field here. There is the option available to define the contract using the Solidity programming language, and alternatively, we can also supply the byte code of a contract which has already been compiled. By default, some Solidity code appears over here, and we will need to modify it before we deploy our own contract. Further down, you can see that since the contract deployment invokes a transaction, we can specify a transaction fee. Once again, there is a slider in place rather than us being able to explicitly define a value, but this should suffice for many purposes. We will now go ahead and define our own contract terms, and this will be a rather simple contract. If you're unfamiliar with the Solidity programming language, I won't get into the details just yet. Only note that this pragma directive on the first line implies the compiler version which needs to be used in order to compile this code, and we specify a range of values. The compiler version should be greater than or equal to 0.4.22 and less than 0.6.0. This contract represents our own custom token, and it is called my token, and it includes just a single field. This is of type mapping, which is similar to a Java hash map or a Python dictionary, and the key type is going to be an address and the value a number. This will be used to store the balance in a particular Ethereum account, and this balance can be for any asset which we choose and is not necessarily Ether. So once we have defined our contract, we can use this drop down over here in order to select the contract which we wish to deploy. We only have one contract in place over here, and this is called my token. And notice how the words my and token appear separated with a space over here. In the contract definition, we have specified the name using Pascal case, and Ethereum Wallet has separated each of the individual words in that Pascal case name. So once we have decided which contract to deploy, we can set the transaction fee for this deployment, and this can be done by using this slider here. However, to ensure that this contract deployment goes through quickly, I'm going to slide it a little further to the right, and then go ahead and click Deploy. Following that, you'll be prompted to confirm the transaction, during which you'll be provided with a summary. So we can see that our Ethereum Wallet account, which begins with D634, will be used in order to create a new contract, and no Ether is being transferred to this contract account in the process. We can see the fee consumption as well as the gas price which has been defined. The raw data for this particular transaction is also available here. But in order to ensure that this transaction goes through, we will need to enter the password which we set when we created this Ethereum account. So in my case, that was ABCD1234. So I'm just going to use that and then hit Send Transaction. The transaction has now been submitted to the Ethereum network, which is the Rinkaby test network, and we will have to wait for a few seconds at least in order for this deployment to be confirmed. Now initiated a transaction in order to deploy a smart contract onto the Rinkaby test network, and we're waiting for the confirmations to come through before the contract is finally deployed. While waiting though, we can click on this link in order to monitor the deployment status, and we can see, for example, that this transaction has an ID which is given here, and also the time when this transaction was initiated is available. So there are 0 confirmations right now, which means that it hasn't yet been added to a single block. Since certain blocks can be rolled back after they've been written by some of the nodes in the network, we will need to wait for a few iterations for multiple blocks to be added along with the block including our deployment transaction in order for Ethereum Wallet to say that this transaction is now confirmed. The summary of our transaction is also available here. However, moving along now, we can close out of this particular window and then head over to the contract section. So even though all the required confirmations are not available yet, it is still possible for us to interact with this contract. We will not do this yet. Instead, we will head back to the Wallets tab and then monitor the status of our deployment transaction. At this point, 2 out of the 12 required confirmations have been obtained. This goes up to 3 in just a little bit. And now I'm going to fast forward until I have more confirmations. So going all the way up to 9 confirmations, I'm now going to click on this link once more and then monitor the transactions from this particular page. So this shows that this deployment transaction was invoked about 2 minutes ago and 9 confirmations have been obtained out of the 12 which are required. Wait a little more and 10 confirmations have been obtained. And then heading back out, we can continue to wait until all 12 confirmations have come in. But once that is done, it means that a contract has been successfully deployed and the transaction which deployed it will not be rolled back. It is now possible for us to interact with this contract, for which we head over to the Contracts tab, and then this contract which has been deployed, we can click on it, and we can view, among other details, the contract address. Contract accounts in Ethereum can also have an Ether balance, and this account has none. We can also copy over the address or transfer Ether from the contract account to another account. We won't be doing any of that. However, we can see that interaction with the account is possible when we scroll further down, and we can see that the single field which is stored in that contract, which is called balance off, is available here. So we can specify an account address and the corresponding balance which has been stored in the account will be available here. So in this manner, the Ethereum Wallet application has provided us with an interface in order to access the fields of a deployed smart contract. Before we use this, however, let us head back to the Wallets tab, and then from here, we can see the balance of our Ethereum account. And in spite of spending some Ether in order to deploy the contract, we can see here that the Ether balance still shows up as 1. This is because this value has been rounded to 2 decimal places, and if we wish to see the entire Ether balance, then we can click on this account here, and you can see the actual balance is about 0.99989 Ether. So the smart contract which we just deployed contains a mapping field, and this mapping stores the account address as a key, and the value represents a balance amount. As I had mentioned previously, that value does not represent an Ether balance, but can represent any asset which we choose. We haven't specified any balance value for that yet. However, in order to see how we can interact with a smart contract, we will copy over this account address, and then we will proceed in spite of the warning. And once the account address has been copied over to the clipboard, we head back to the Contracts tab, click on the contract, and moving further down, when we enter this account address in this field here, the corresponding value appears, which is 0. This is because we haven't really loaded any data into that mapping object, and that is something we will do in the next demo. In the previous demo, we deployed a smart contract to the Ethereum test network Rinkaby, and we saw how we can make use of the Ethereum Wallet application in order to both deploy and also interact with that contract. A smart contract contained just a single mapping field. However, there was no value which we loaded into it. In this demo, we will take a look at how we can load a value into that mapping object at the time of contract creation. To do that, we will be creating a brand new smart contract. So from the Contracts tab of Ethereum Wallet, we will click on Deploy New Contract. On the page which appears, we will scroll down to the section where we specify the Solidity code for our contract. And on this occasion, we define the mapping field within our myToken contract. And in addition to that, we specify a constructor. A constructor in Solidity can be defined by the keyword constructor. And then within that, we will initialize our mapping object, which is called balance of, with a key and value pair. The key will be the address of the account which deployed the contract in the first place, and the corresponding value is going to be 10. Those who are familiar with associative arrays or Python dictionaries will be familiar with the syntax which we specify here. The message.sender field includes the address of the account which invoked the transaction. That is how we get the key of the key value pair we are loading, and the value which represents the balance in a particular asset is 10. So once we have defined the smart contract, which includes a constructor, we can now go ahead and deploy it. So we first select this myToken contract, which needs to be deployed. Following that, we can set the ether, which we are willing to pay in order for this transaction to occur. And then following that, we just go ahead and hit deploy. We will once again be prompted to enter our account password. But once that is done, a new transaction will be invoked, and we will need to wait for a few confirmations until this transaction is finalized. However, it is possible for us to interact with this contract even before all of the 12 confirmations have come through. To demonstrate that, we can head over to the Contracts tab, and we can see that this newly deployed contract is available for us to work with. So when we click on it, we can head to the bottom, and we can see here that this balance of mapping object can be accessed from here. Because it is a mapping object, we can specify the key in this interface, and then the value will be returned. The key, of course, is an address, and the only key which has been loaded into this mapping object represents our externally owned account, which was created in Ethereum Wallet. However, let us first try an experiment. Let us see if this gives us a balance value for a contract account. So when we click on copy address over here, this will copy over the address of this contract which has been deployed. Just as before, we choose to disregard the warning. And then once this address has been loaded into the clipboard, we paste it into this field over here, and we are promptly returned a value of 0. This is because there is no data which represents this particular address available in our balance of mapping object. This is similar to when we specified our own externally owned account's address in the previous demo and got a balance of 0. On this occasion, however, since it is our externally owned account which invoked the transaction which deployed the contract, the constructor should have loaded a key corresponding to that account address along with the corresponding value of 10 into this balance of mapping object. To test that the data was properly loaded, we will now need to copy over the address of our externally owned account. So we switch over to wallets and then click on this account here and then copy the address of this account. With that address copied over to the clipboard, we can head back to the Contracts tab. And even though all the confirmations haven't come through, we can still interact with our newly deployed contract. We click on it, and within this field for balance of, we paste in the address of our externally owned account, and we are promptly returned a value of 10. This is exactly what we had loaded into this balance of mapping object in the constructor. So we have now seen how we can deploy a smart contract with a constructor using Ethereum Wallet, and then made use of the interface available in this wallet application in order to examine the contents of one of the fields defined in our smart contract. In the previous demo, we saw how we can deploy a smart contract to the Rinkaby test network on Ethereum, and within our contract, we had defined a constructor in order to initialize one of the fields in our contract with a key and value pair. In that case, however, we had hard-coded the key and value pair which was loaded into that mapping object. And in this demo, we will see how we can specify an argument which can be passed to a constructor and then make use of the Ethereum Wallet interface in order to pass in a value for that argument at the time of contract deployment. So once again, we will need to create a new smart contract for this. So we head over to contracts and then click on deploy new contract. So this contract deployment will occur from our externally owned account, which we have created in Ethereum Wallet. And then we will move ahead to the source code of our Solidity contract. So I'm going to clear out this default code over here and then enter our own smart contract code. And this is similar to what we had previously, except this time a constructor accepts an argument, which is an integer called initial balance. So whereas previously we had set a key and value pair where the key represented the account address of the account which was used to deploy the contract and the value was hard-coded to 10, on this occasion we make it possible for the one deploying the contract to specify an initial value corresponding to that account address. So once this code has been defined, we can choose the contract to deploy, which is called myToken. On this occasion though, we will be prompted to enter an initial balance value. Ethereum Wallet has been smart enough to detect that the constructor of a contract needs an initial value in the form of an integer of 256 bits, and it gives us a field in which to define this value. So whereas previously we had set a hard-coded value of 10, on this occasion we will explicitly set the value of 10 as the initial balance of the account which deployed this contract. So scrolling further down, we can set the fee we paid for this transaction and then hit deploy. And once again, we will be prompted to enter the password in order for this contract deployment to take place. So once we do that and hit send transaction, a contract deployment will have begun. So at this stage, no confirmations have come through. So I'm going to fast forward a little bit until there are 2 confirmations available. And then we can click on this in order to view more details. But in order to work with this contract, I'm now going to switch over to this contracts tab. And as expected, there are 3 contracts listed here. It is the first of these which represents the one which has been most recently deployed. So I'm going to click on that. And then scrolling over to the bottom, I'm going to enter the address of my account here in order to view the balance. And as expected, this shows a value of 10. In the contracts which we have deployed so far, we have stored a mapping object, and this is supposed to store a set of key and value pairs where the keys are account addresses and the values represent the balance of a particular asset. So this in fact can represent a token balance in an Ethereum account, where the token represents a currency which is specific to a particular contract. In this demo, we will load that mapping object with multiple key and value pairs representing the balances of multiple accounts in terms of tokens. We will also code a function which will allow us to transfer tokens from one account to another. We will also make use of Ethereum Wallet in order to call that function and enable the token transfer. Let us begin. We head over to the Contracts tab and we will deploy a new contract once more. And then scrolling down to the Solidity code section, let us begin the definition of our new contract. So in addition to what we had previously, where we define the mapping field and also include the constructor, which is initialized with a balance value, we will include on this occasion a function called transfer. This function needs to be invoked from an Ethereum account, and it will transfer a certain value of tokens, which is represented by the second parameter here called _value, from the account of the transaction initiator to the account which is specified in the first parameter of this function, that is an address which is called _2. So just to summarize, this transfer function will be invoked by someone who wishes to transfer a certain value of tokens to a destination, and the arguments to this function include the address to which tokens need to be transferred and the total value of tokens which need to be transferred. The source account for the token transfer will be the account of the initiator of this transaction. We also set this function to be publicly available. And within the function, there are 2 steps which we execute. Firstly, the one who invokes this transaction will have tokens subtracted from their own account, and then the recipient of this transfer will have the same number of tokens added to their balance. So with that, we have finished defining the code for our contract. We can now go ahead and deploy this. So I'm going to select this my token contract, which needs to be deployed. And following that, we will need to specify an argument for the constructor. On this occasion, I will set a value of 15 so that a total of 15 tokens will be credited to the account of the one who initiates this transaction. Once that is done, we can set the total transaction fee which you're willing to pay and then hit deploy. We enter the account password once more in order to initiate this transaction. And once we hit send transaction, the deployment of this contract to the Rinkaby test network will have begun. We can now click on this transaction in order to monitor its status. So we can see its transaction ID as well as the summary for the transaction. We may get a notification that no data is currently deployed to the contract address, but once that disappears, it means that we can now interact with this contract. And to do that, let us first copy over the account address of the account we created in Ethereum Wallet. So clicking on the account, we can head over to the right and click copy address. We will choose to proceed in spite of the warning. And once our address has been copied over, we will now head over to the contracts tab. And then the newly deployed contract is the second one for me. So I'm going to click on that. And then I will check the balance in this particular address. So on this occasion, we had passed along 15 as the initial balance in the constructor. And that is exactly the value which is returned when we check the value of tokens in this address. You will notice though that on this occasion, we have a function selector on the right of this field. This is because we have included a transfer function in our smart contract, and we can use this Ethereum wallet interface in order to interact with it and then call that function. We will be doing that in just a little bit, but before doing so, let us head back to the Wallets tab, where we can see that this particular transaction has not been confirmed yet. Now, before we invoke the transfer function, we need another account address to which we can transfer the tokens. We will be creating an additional account in Ethereum Wallet. But before that, let us take a look at our file systems. So in my case, I had shown you where the key stores were generated for each of the accounts which were created on Ethereum Wallet. In my case, there was just a single account which was created once I had connected to the Rinkaby test network. So within my home directory on my file system, under library/Ethereum/Rinkaby/keystore, there is a keystore file which corresponds to the only account which I have in my Ethereum wallet. We will now see what happens when we create another account in the same wallet. So heading back to the wallet now, we can click on add account, and then we will be prompted for another password. So I'm going to enter a value over here, which is going to be the same as the password for my previous account, which is ABCD1234, just to keep things simple. So I'm going to hit OK, and then retype the same password, and the new account has now been created. This notification confirms that a keystore file has been created in the keystore directory. So once this second account has been created, let us navigate back to the file system, and within that same keystore directory, there is an additional file. And from the file name, you can confirm that this belongs to the second account we have just provisioned. We can now make use of the transfer function in our smart contract in order to transfer tokens from account 1 to account 2. So now that we have two accounts in our Ethereum wallet, it is possible for us to transfer tokens using our smart contract from one account to another. So let us now copy over the address of the second account, because that is one of the arguments which we need to provide when invoking the transfer function in our contract. So clicking on the account number 2, we click copy address. Once we confirm that the address has been copied over to the clipboard, we can head over to the contracts tab and then click on the newly deployed contract. Once within the contract page, we will scroll down first and then first check the balance in tokens corresponding to this newly created account. As expected, the value is 0. And now we will head over to the function interface here and then pick the function which we wish to invoke. So there is just one function in our smart contract which is called transfer. So we pick that. and then we will be prompted to enter the two arguments of this transfer function. The first one is the destination address to which tokens are being transferred, and the second is the total value of tokens which needs to be sent. Following that, we specify the account which will be invoking this transaction, and this is the account from which the tokens will be subtracted. So once we have picked our first Ethereum wallet account as this source account, we can go ahead and hit execute. This will be invoking a transaction because the state of the contract will be changing. So while we were able to examine the contents of our balance of map without invoking a transaction, when we run execute this time, we will be prompted to enter a password just as when we deploy this contract to the blockchain. So once we enter this password, we hit send transaction. And now we have seen a transaction sent notification. And we can now monitor this transaction by heading over to wallets and then viewing this contract execution transaction, which needs 12 confirmations, exactly as a contract deployment transaction requires. You will notice that for me, the contract deployment has still not obtained the required 12 confirmations. However, I'm now going to hit fast forward so that the contract deployment is confirmed, and some confirmations have also come through for our latest transaction. So following that, we head over to the contracts tab and then to the page corresponding to our latest contract. We first check the balance of our first Ethereum wallet account, and on this occasion, this has dropped from 15 to 10. So the subtraction of tokens from the first account has taken place successfully. And as the sanity check, let us check the balance of tokens in the second Ethereum account. And as expected, this shows up as 5. We will now initiate one more transfer, but confirm first that the first Ethereum account which we have has 10 tokens in total. So we now head over to this drop down and select the transfer function once more. And when we do that, the arguments need to be specified. So the destination address will once again be the second Ethereum account. And then this time, we will transfer a total of 20 tokens. Since our source account contains just 10 tokens, this should result in a negative balance for this first account. However, let us see what happens when we execute this transaction. So we just hit execute, and when prompted, we enter the password. And once the transaction has been submitted, we can in fact just wait here in order to view the balances in each account. And automatically, the balance of the first account has been refreshed here. And what it shows is a rather large integer. And this is because the balance value is supposed to be an unsigned 256-bit integer. When 20 tokens were subtracted from the balance of 10 for this account, an overflow has resulted, which is why you see this rather large number here. Let us now confirm whether the correct number of tokens have been added to the second account. So we copy over the address of that account and then paste it in this balance of field. And this number is correct. A total of 25 tokens exist in the second account. We have now been able to view the updated token balances for each of the accounts immediately. And there surely has not been enough time for there to be 12 confirmations for this particular transaction. In order to see how many confirmations there are, we head back to wallets. And then from the transactions page, we can see that just 2 confirmations have come in so far. In the previous demo, we wrote a transfer function in order to allow transfer of tokens from one Ethereum account to another. Our implementation of this transfer function, however, was a little naive, where we did not account for there not being enough tokens in an account's address in order to fully fund the transfer. In this demo, we will take a look at how we can specify conditions in a smart contract in order to ensure that there are enough funds available in order to make a transfer happen. To do that, we will once again need to create a new smart contract, for which we navigate to the Contracts tab and then click on Deploy New Contract. We can also view the Ether balance in our account over here. In my case, this is just a shade under 1 Ether. We go further down in this page, however, and then write out a smart contract. So just as previously in our token contract, there is a mapping field, as well as a constructor which loads this mapping object with an initial key and value pair. Following that, there is the transfer function, which has the same signature as what we had previously, but on this occasion, we apply conditions to our transfer by making use of the require keyword. So what are the requirements when tokens are being transferred from one account to another? Well, first of all, the sender account needs to have the tokens which are being transferred. So the first require statement here ensures that the sender has enough of a balance in order to initiate the transfer. And then secondly, we add another require clause to ensure that the recipient's account balance will be greater than or equal to the previous balance before the transfer was initiated. Each of these require clauses effectively prevents an overflow. Only if each of these require clauses are satisfied will the execution of code proceed in this contract. So when those two conditions are met, we proceed with the code as we did previously. The token value is subtracted from the sender account and then added to the recipient's account. On this occasion though, we also include a return boolean value to indicate whether the transfer operation was a success or a failure. So once we have defined our code, let us go ahead and deploy this contract. So we select this my token contract, and when specifying the initial balance of our sender account, we set it to 15, just as we did previously. We then set the transaction fee which we're willing to pay, and then when we're happy with the terms, we just hit deploy. So once the password has been entered, we can initiate the transaction, and then following that, our transaction is now being added to the blockchain. And while we monitor the status of this and wait for a few confirmations to come in, we may get a notification that the contract has been created. So this means that the contract will be accessible, and do make note of the first 4 characters of the contract address. In my case, this is B68D. So heading over to the contracts tab, I can see this particular contract created over here. So we can now test the new and improved transfer function of this contract. So we click into it, and then heading over into the bottom, we check the token balance of our first Ethereum account, which is 15. One thing to keep in mind here is that each time we redeploy our smart contract, a brand new contract is created on Ethereum. There is no link with the previous contract, which is why the token balances in each of these contracts are independent of each other. So we had initialized this account to have a token balance of 15, and then we check the balance for the second account, and since this was not initialized in any case, this has a token balance of 0. It is now time for us to test the transfer function. So we head over to this dropdown, select the transfer method, and then once more we specify that the recipient of this transfer will be the second Ethereum account, and then we will transfer a total of 20 tokens this time. So the balance in the sender account is just 15 tokens. So on this occasion, we expect that the logic which we have implemented with the use of the require clause will ensure that this transfer does not happen. So let us put that to the test by hitting execute. You may see in the transaction summary that the total gas consumption could not be calculated exactly. The reason for this is because of the use of the require clause. If either of the conditions specified in the require clause were to fail, then the code execution will stop at that point. If not, the execution will proceed and the transfer of tokens from one account to the other will be initiated. Since the outcome of the require clause is not known at this point, it is not clear how much of the contract code will actually be executed. As a result, it is not possible to come up with an exact gas consumption number, and an estimate needs to be made. This is exactly what we see in the field for estimated fee consumption. Moving further along, we can confirm the arguments which have been passed to this function, and then enter our password, and then hit send transaction. So the transaction has now been invoked, and at least the require clauses will be executed. But will the fund transfer actually take place? Well, for that, we first head over to the Wallets tab and then confirm that the transaction has been initiated. We can then head back to the Contracts tab, and then clicking on this new contract, we will head down and then check the Ether balance in the first account. So this is still 15, which indicates that the transfer may not have gotten through. Let us confirm the balance in the second account, and the balance of 0 confirms that the transfer did not actually take place, which means that our require clauses actually worked. When we were trying to transfer more tokens than were available in the sender account, the transfer failed. So we have been able to confirm that the token transfer does not occur when the require clauses fail. Let us try the converse operation where the require clauses pass and make sure that tokens are transferred from the first account to the second. So we initiate one more transfer this time. The sender and the recipient will be the same as before, and the value of tokens transferred this time will be less than the balance in the sender account. So 12 tokens out of the 15 available will be transferred over. So we run execute and then confirm the contents of the transaction, enter our password and hit send transaction. And then we will refresh this page. So to do that, we can head to the wallets tab and then back to contracts and then click on our new contract. We now check the balance in the first account, and this has a total of 3 tokens in it. So this is exactly what we expect. 12 out of the 15 tokens which were present in this account initially have made their way out. As a final confirmation that the transfer did indeed take place, let us confirm that 12 tokens have made their way into the second address, and we now have that confirmation as well. So we have now learned how we can make use of the require clause in a smart contract in order to enforce certain conditions. So far, we have created multiple smart contracts and then deployed them to the Rinkaby test network using Ethereum Wallet. You can imagine that during the process of contract development, there will be multiple iterations which you go through, in which case multiple versions of your contract will exist in your Ethereum Wallet app. Most of these contracts will not really be needed, and at some point you will need to perform a cleanup. In this demo, we will show exactly how that can be done, and it's not something which you can do purely using the user interface. Since the Ethereum wallet is in effect a web browser, we can access one of the JavaScript objects which stores all the custom contracts which we created, and then remove the contracts which we don't need from there. To access all the custom contracts though, we will need to make use of the console for our web page, and this can be accessed in Chrome using either Command Alt and I on a Mac or Control Alt and I on Windows. This will bring up the Chrome developer tools, which should appear as a frame on your web browser. It has appeared on the right of my screen, and then within that, we can access various elements on the web page and then also access the console. First though, we need to ensure that we are in the Contracts tab of our Ethereum Wallet app. So we click on Contracts, and then following that, we head over to the Console section in the Developer Tools frame. So after clicking on Console, you will see a lot of the messages which are popped up over there. But what we need to do is to access the Custom Contracts object. All of the contracts which we have defined can be retrieved by running customcontracts.find.fetch. So once you have typed that in, you can confirm that there are 5 contracts which are visible on the left, and then hit enter on the console, and what is returned is an array containing 5 objects, one object for each of our custom contracts. Let us expand the first of these contracts, and what we see is an entire object definition. There is a contract address, there is also a balance associated with the contract, and there are a few other fields available here as well. But what we really need in order to delete this particular contract is the contract ID, which is accessed using the underscore ID field. So just copy over that ID for the contract, and then in order to delete this contract, we will make use of the remove method in the custom contracts object. So the argument to the remove method is the contract ID. So when we call custom contracts.remove, you can keep an eye out on the left to see whether the contracts disappear, and then hit enter on the console. And we are now down from 5 to 4 contract objects. So we have now successfully cleaned up one smart contract from our Ethereum wallet. Let us go ahead and delete one more. So the second contract, which was returned in the original array, is the one whose contract address begins with 180, and this is the first contract in the list on the left. So I'm now going to copy over the ID for that contract, and once more invoke the custom contracts.remove method and pass along the ID of this contract as argument. And upon hitting enter in the console, we are now down to 3 contracts. We can now go ahead and pick one more contract to delete. So this is going to be the one with the address C6D04, which on the left is the contract at the bottom. So I'm going to copy over the ID for that contract, and then for the third time invoke custom contracts.remove. And that contract has disappeared as well. If we decide that we only want one contract to linger on in our Ethereum Wallet app, we can go ahead and pick which one of the remaining needs to go. So I'm picking the one with the contract address starting with 6019, copy over the ID for that, and invoke the custom contracts.remove method once more. Alright, so we're down to one version of the contract. So we have now seen how we can get rid of contracts from the Ethereum Wallet application. However, it will also be useful to get rid of certain accounts if you have only created those for test purposes. So in order to delete an account, we first head over to the Wallets tab where the accounts will be visible. And there are 2 accounts which are available for us here. Out of these, let us say that we only require the first one and we want to get rid of account 2. Well, on this occasion, we don't really need to make use of the console, but instead, we can head over to the file system and then navigate to the key store file which was generated for this account when we provisioned it in the first place. You can either head there directly from your file system browser or from the Ethereum Wallet app, head to File, Backup, and Accounts. So within the Accounts directory, we can head over to the Rinkaby directory, which includes the key store file for both of our accounts. Within that, there is the key store subdirectory, and from the 2 key store files, pick the one corresponding to account 2 and then just delete it. So I'm just going to right click and then move this file to the trash. And once it disappears from this file system directory, we can head back to Ethereum Wallet. And this time, account 1 is the only one which is visible. We have now seen how we can perform a cleanup of our Ethereum Wallet application. And if you're running the Mist browser, it works pretty much the same way. We made use of custom contracts in order to get rid of contracts which we no longer require. And then in order to delete accounts which we don't need, we can simply get rid of the corresponding key store file from our file system. In this exercise, you will identify the purpose of the mnemonic phrase of a digital wallet. We saw during this course that when we were setting up our Metamask account, we were given this 12-word mnemonic phrase and we were asked to memorize it or store it somewhere safely. You will need to recall the purpose of this mnemonic phrase and why exactly it needs to be stored safely. Next, you will list down the features which are offered by the Ethereum Wallet application in order to work with smart contracts. We made significant use of Ethereum Wallet during this course, and it allows us to do a number of different things, including setting up new accounts, transfer Ether from one of our Ethereum Wallet accounts to another account, and it also allows us to connect to different Ethereum networks. We made use of the Rinkaby test network during this course. However, you will need to recall exactly what smart contract related features are offered by the Ethereum Wallet app. And finally, you will need to recollect how exactly we can perform a cleanup of our Ethereum wallet. Once we have generated many smart contracts and created many different accounts to play with in Ethereum Wallet, this can make the Ethereum Wallet interface rather crowded and difficult for us to identify the specific contracts and accounts which we wish to work with. So you will now need to remember exactly how we can remove certain contracts and accounts from the Ethereum Wallet interface. All of these topics were covered during this course, so please pause this video and then take some time to perform these tasks on your own. For the first task in the exercise, you needed to identify the purpose of the mnemonic phrase which is associated with a digital wallet. So the mnemonic phrase is also known as a mnemonic passphrase or a seed phrase. Such a phrase consists of a sequence of 12 words which are picked out of a total of 2048 words defined in the BIP39 standard word list. Once the sequence of 12 words is obtained, it is converted to a number, and then following that, the derived number serves as a seed which is used to generate a collection of key pairs in a deterministic manner. So just to summarize, the sequence of 12 words which make up the mnemonic phrase map to a specific set of key pairs. So if you happen to lose the key pairs associated with your wallet accounts, well, you can simply make use of the mnemonic phrase in order to recover all of the account information. This is exactly why such a mnemonic phrase is used in a number of different digital wallets, including Ethereum wallets as well as Bitcoin. For the next task, you needed to list down some of the operations which are allowed with smart contracts when using Ethereum Wallet. Well, first of all, we saw that Ethereum Wallet allows us to deploy new smart contracts, and we can do this by either writing down the Solidity code for a smart contract or even entering the Byte code for a contract if that is all we have available. If it's not a new contract which we wish to deploy, and we simply wish to work with one which is already deployed to a network, well, we can make use of the watch contract option, where we specify some of the details related to an already deployed contract in order to work with it. And how exactly do we work with deployed contracts? For that, Ethereum Wallet provides us with an interface to interact with them, and these interactions can be categorized into two broad operations. The first of these are read operations, where no transaction is triggered, and we can perform read operations on fields within the smart contract as well as invoking read functions. And then there are write operations. This typically involves calling functions which alter the state of the smart contract, and such operations do invoke transactions. And for the final task, you needed to recollect how exactly you can clean up your Ethereum wallet by deleting smart contracts as well as accounts which you no longer require. When it comes to removing smart contracts from your wallet, you will need to access the JavaScript console, and once you do that, you can simply execute custom contracts.remove, and the argument to this method is the ID of the smart contract which you wish to get rid of. When it comes to removing accounts from your Ethereum wallet, you can go to File, Backup, and Accounts, which will bring up your File System Explorer and direct you to the location in your file system where all of your account information is stored in files. You can also navigate to this location without having to go through Ethereum Wallet, but once you are there, you will need to navigate to the key store directory, and then within that, you'll have to get rid of the key store file corresponding to the account which you wish to remove from your Ethereum wallet. In this demo, and some of the subsequent ones in this course, we will be setting up our private Ethereum network using the Geth client. Geth is an Ethereum client application written in the Go programming language, and it allows us to set up and then run an Ethereum node in a network. We can choose to run our node in one of the publicly available Ethereum networks or even set up a private one. And in order to demonstrate the functionality of Geth, we will be setting up a private network. However, before we can install Geth, we first need to ensure that we have a package manager which has been set up to download the Geth binaries from the Ethereum repository. So I'm going to be using Brew in order to install Geth on my Mac. So if you have the same operating system, you can follow my lead in this particular demo in order to set up Geth. Or if you already have Ethereum Wallet installed on your system or the Mist browser, you should have Geth already. However, in order to use brew to install get, we first navigate to brew.sh, and right at the top, my OS has been detected and it suggests the use of Ruby in order to install brew. This is exactly what we will be doing. But if you'd like to take a look at how exactly you can use brew, you can scroll further down in this page in order to view some examples. Well, let us head back to the top of the page and then copy over this Ruby command in order to install Homebrew. And then I'm going to open up a new terminal session and then run that command as was instructed on the brew web page. So once this is executed, there will be a few minutes which may elapse before brew is installed. And you may also be prompted to confirm that the installation must proceed. However, you should soon see the installation successful message. So once brew has been installed, it is now time to set up brew to work with the Ethereum repo from which it can download the get binaries. While brew is already set up with a number of different repositories from which you can download a lot of standard tools, it is not synced up with the Ethereum repo by default. So the way to add a third-party repo to brew is to make use of the brew tap command, and the argument to this includes the user of the repo as well as the name of the repo itself. So the Ethereum repo is available at Ethereum/Ethereum. So once you run this tap command, you can install the get client by running brew install Ethereum. If you'd like to make use of the C++ client, which is available on Ethereum, so this is called CPP Ethereum, you will run brew install CPP-Ethereum. On the other hand, if you have already done some of the labs in the previous courses in this learning path, you will have installed Ethereum Wallet, which comes with get packaged within. In that case, we can simply run the get command straight from the command line, which is exactly what I'm going to do now by running get-help. And this returns an output which confirms that get has been successfully installed on my system, and the version which I have is 1.8.22. So once get has been successfully installed on your system, either using brew or the specific steps for the operating system which you are running, you can confirm that the installation has been successful by running this get help command. And once that is done, we can begin with the meat of this demo. And for that, we will first create a new project directory. This one we will call get-demo. And then once this directory has been created, I'm going to cd into it. And the first thing we will do here is to create our own private Ethereum network. And one of the steps involved is to create our own Genesis block. For that, we can define the Genesis block in a genesis.json file. And I'm making use of the Nano text editor in order to create this. You can use any text editor of your choice for this purpose. What is important to us is the contents of this genesis.json file. So this is included as part of your course materials, and there are various resources online which will give you an example genesis.json file. Out of the various fields which are defined within this JSON file though, 4 of these are necessary. One is the config field, which you see right at the top. There is also the alloc field, where you can allocate an ether balance to various accounts on this private Ethereum network. We currently leave this as blank. However, the field itself must be present. The difficulty property will also need to be present, and this determines the mining difficulty level. The gas limit field should also be present in this genesis.json file, which sets a limit of the gas cost per block. This effectively places a cap on the total transactions which are included in the block, not merely by the number of transactions, but by their total aggregate complexity. So once the genesis.json file has been defined, make sure that you include a chain ID. I won't get into the details for why this is required, but this is something to protect you against replay attacks. So once the genesis.json is defined, we can save its contents. And then when we head back to our shell, we can run an ls just to confirm that the file exists. And now with this genesis.json file, what we have is the definition of the Genesis block of our private Ethereum blockchain. The next step for us is to initialize our blockchain using this Genesis block definition, and then to also create a database where all the data for the blockchain will be stored. This database will include information about the various accounts in the network, among other details. So how exactly do we initialize this database? Well, we run the get init command, and the arguments to this include the genesis.json file itself, and we also make use of the datadir parameter in order to specify the directory in which this database will be created. So this is going to be a subdirectory called datadir_node_0 within our current working directory. As the name implies, this will represent node 0 in our private Ethereum network. So when we run this get command, we get the notification that the Genesis block has now been successfully initialized and that a database has also been created out of it. So at this point, let us run an ls in this directory, and we observe that in addition to the Genesis block definition in the genesis.json file, there is also the data directory for node 0 which has been created. It is now time for us to explore the contents of this directory, and for that you can use any file explorer which you choose, which could also be your command line. However, I'm going to bring up the file system explorer on my Mac and then navigate to this get demo directory where I see the genesis.json file and this datadir directory as well. And within this datadir node 0 directory, there are two subdirectories. One is called get and the other is called keystore. This database represents all the data which is needed for an Ethereum node, and within the get directory, we can see not only the full chain data in the chain data directory, but in case you wish to run this as a light node, then the data will be stored in the light chain data directory. We head over now to the keystore directory, and this is currently empty. This is because we have not configured any accounts to map onto this particular Ethereum node. Once we create an account for this node, then the keystore files for that account will be stored over here. We will see exactly how that works just a little later in this course. In the previous demo, we created our first private blockchain network, and we initialized it using a Genesis block, and then also defined a node which includes a database in order to store the chain data as well as account information. However, there is no account available yet for which information can be stored, and we can in fact confirm that by running a get command from the command line. So if we execute get account list, what we get in return is nothing except a log message. So we can run one more get command in order to create a new account, but one of the arguments which we will need to pass along is a file which includes the password of the account we are about to create. So let us now go ahead and create that password file, which we will call password. So I bring it up in the Nano text editor, and then following that, I just write down the password in here. So this is going to be ABCD1234. I'm now going to save this file down. And once that is done, the command to execute in order to create a new Ethereum account using get is get account new. There is a parameter named password which we pass along here, and the value of that parameter will be the location of the password file. Since I'm already in the directory where the password file has been created, I can specify a relative path to the file. So once we execute this, a new account should be created. In fact, we can see the account address in the output over here. As a sanity check, we will once again execute get account list. And on this occasion, we not only get the log message, but we also get the account details. So this is account number 0. We can see the account address here, as well as the location of the keystore file which has now been generated for this account. You will notice that the keystore file has been created in the user's home directory /library/ethereum/keystore. Do make note here that the account address ends in 6C21. To view the generated keystore file, we can make use of a File System Explorer app. So I have brought up the Finder application on my macOS, and then navigating to the Ethereum directory, we can see a number of subdirectories within this. Earlier on in this learning path, I had created an account using Metamask, and this account key store is available in the Rinkaby directory. So going into Rinkaby/keystore, there is a keystore file representing the account which was created from Metamask. However, to access the keystore file corresponding to the account which we just created using get, we take a look at the keystore directory within the Ethereum directory itself, and we can see here that this particular keystore file, whose name ends in 6C21, is the one which represents the account which we just generated. Do note, however, that this particular account does not belong to the private Ethereum network we created just a little earlier. So once you have created an Ethereum account, what if you want to change some of its properties? Specifically, what if you would like to change the password associated with an Ethereum account? Well, we can make use of the get account update command, and the argument to this is going to be the address of the account whose details you would like to update. So adding the address of our newly created Ethereum account here, we will first be prompted to enter the password for this account. In my case, this is ABCD1234, which I had noted down in the password file which was used to create this account. So once you type in the password for your account, you'll be prompted to enter a new password. So I'm going to keep this even simpler than the previous one. I'm just going to set this password to 123. You will then be asked to re-enter the passphrase, and then once that is done, the password for your account has now been updated. So now that we have a node set up, as well as a new blockchain and an account to play with, let us begin interacting with the Get JavaScript console. This will allow us to access the various JavaScript management APIs which are available for us in order to interact with the Ethereum network. The command to execute for this is get console, and in order for get to know which Ethereum network we wish to connect to, we pass along the data directory of one of the nodes in our network. This is the node 0 which we just created earlier on in this course. So when we run this command, we get the notification that the console has now been brought up. So once the console is up and running, we can begin accessing the various APIs available to us, starting with Web3. So we type Web3 and hit enter, and what we get is a massive JSON output. So scrolling all the way to the top, we can see some information over here, including an ID and the IP address of the node from which the get console has been brought up. Following that, we can also view some of the peers of this node, and we also have access to various fields and functions which are available for us in Get in order to interact with the network. So the Web3 object which we have just accessed is a member of the Web3 class, which is in fact a wrapper for a number of Ethereum related modules. These modules can also be accessed directly from the console here, and one of these is the ETH module. So if we run ETH from this console here, we get a JSON as output, and this includes a number of properties as well as functions which allows us to interact with an Ethereum blockchain as well as smart contracts. There is also the net module, which gives us details about the node in the network. For example, the listening property tells us whether the node is actively listening for network connections, which in this case is true, and it also gives the peer count for the nodes. Since there are no peers for this node in the network, given it's the only one, the peer count is 0. There is also the admin module, which allows us to access various methods to manage, control, or monitor an Ethereum node. You can see various node-related details here, including the fact that this node is listening on port 30303. We can also view the status of the blockchain on this node. So the genesis block is the same as the head block in this case, given there are no additional blocks. We now move along to exploring one more module, and this one is called personal. From the JSON output, you can view that this includes a lot of details related to accounts. So this provides us with the APIs in order for us to view accounts as well as create new accounts and modify them. And if you happen to be running a full Ethereum node, you will need it to perform some mining operations, and all of those methods are available from the miner API. So now that we have brought up the Get console, you can see how we can interact with our blockchain network by making use of the various APIs available through this. Now that we have taken a look at the various APIs available for us from the Get console, let us begin using them in order to interact with our Ethereum network. To start off, we will make use of the ETH or ETH API and specifically the get block method in order to retrieve the genesis block in our blockchain. So we pass along the value of 0 as the argument to get block, and this returns the block at index 0 in our blockchain. And this genesis block also happens to be the only block in our blockchain at the moment. So you can see the various details related to this block. We now move along and then take a look at the accounts which are available on the private blockchain we have just created. So we can access the accounts by running eth.accounts, and this returns to us an empty list. So there are no accounts which have been created on our private network just yet. The previous account which we created was not connected to any Ethereum network. On this occasion, however, we have brought up the Get console by specifying a value for the data directory. We have set that to be the home directory of the first node in our network, and this network has been initialized using the genesis block which we defined previously. So when we create a new Ethereum account on this occasion, it will be created within the data directory which we specified when bringing up the Get console. Since this data directory represents the home directory of a node on our Ethereum network, this account will be linked to that private Ethereum network. So the way to create a new account from the Get console is to make use of the personal library and specifically the new account method within it. The argument to this is the password of the new Ethereum account which needs to be created. So when we run this, the output shows us the account address of the newly created Ethereum account. Do note here that the last few characters of this Ethereum account address are F102. To confirm where this account key store has been created, we can head back to our file system, and we see that there is a key store directory within the data directory, that is the directory of our node. And within this key store directory, there is a key store file, and the last 4 characters, which are F102, confirm that this corresponds to the newly created Ethereum account. So we head back to our console, and now let us take a look at the balance for this newly created account. So for that, we make use of the ETH module once more, and specifically the getBalance method. The argument here is the address of the account for which we want to get the balance, and this can be accessed from the eth.accounts array. This only contains one element so far at index 0 corresponding to our newly created account. So when we run this, we get a total ether balance of 0. So we need to figure out a way to load ether into this. But before we do that, let us take a look at one more property which is available, which is eth.blockNumber. This will return the index of the latest block in our blockchain, and unsurprisingly, this is 0 given that it only contains a single genesis block. So one way to generate ether is to mine more blocks and add them to the blockchain. And in fact, the way to do that is to access the miner API and specifically its start method. The argument to this method represents the number of parallel threads we want running, and for now we're satisfied with a single thread. So I'm now going to hit enter in order to begin the mining process. Now, once blocks have been mined and added to the blockchain, where exactly do the mining rewards end up? Well, given that there is just a single node in our private blockchain network so far, they should flow into this particular node. And given that there is just one account which is currently available in this node, we can see from the third log statement in this output here that Etherbase has automatically configured the account which we just provisioned, with the last 4 characters ending in F102. This means that all the mining rewards will be credited to that account. So once we let this run for a few seconds, we will see that new blocks have been mined and then added to the blockchain. And then we let this run for a few extra seconds. And we will need to stop the mining process at some point. And we can do that by running miner.stop. So it is a little complicated to do when the log statements keep piling in. So I tried once, but more log statements make their way in. However, I'm now going to copy and paste the entire command and then hit enter. And by this time, 8 new blocks have been added to the blockchain, but the mining process has now stopped. We can confirm the number of blocks which have been written down by checking the value of eth.block number, and the value of 7 which is returned confirms that there are now 8 blocks in our private blockchain. Let us now check the balance in our account once more, and a total of 35 ether has been credited to this account. Note that this balance is represented in the units of Wei, where 1 ether is equal to 10 to the power 18 Wei. Let us now go ahead and create one more account. So once again, we run personal.new account, and this account will also have a password of 123. So once we execute this, we get the account address of the newly created account, which ends in 796F. We can head over to the file system, and within our data directory and within the keystore subdirectory, we can see that there is a keystore file which has been created for the second account. To view all the accounts which are accessible to us, we access the accounts array in ETH, and this gives us an array of 2 Ethereum account addresses. So now that we have 2 Ethereum accounts and one of them has a fair number of ether, the next thing for us to do is to transfer ether from one account to the other. Any operation involving the transfer of ether will invoke a transaction, and for that we can call the send transaction method available within the ETH module. The argument to this is a JSON data structure which includes all the details of the ether transfer. This includes a from address, a to address, as well as the value of ether to be transferred, and this needs to be represented in the units of Wei. In order to transfer 1 ether, we can either specify 1 followed by 18 zeros, or to make things easier, we can make use of the two-way method which is available in the Web3 API. The arguments to that include the value which needs to be represented as Wei, as well as the units. So here we convert 1 unit to Wei. When we execute this method, however, we are notified that we need authentication in order for this transaction to proceed. There are 2 ways to do this. We either need to explicitly specify a password when invoking the transaction, or we can unlock our account before we invoke it. Let us try the second of those options. So for that, we can run personal.unlock account. The arguments to this include the address of the account which needs to be unlocked along with its password. So once we specify that, the account is now unlocked, and now we can run the send transaction method once more. On this occasion, the transaction seems to have been submitted, and we get a transaction ID as well. So let us view the effects of running this send transaction method by checking the balance of ether in each of our accounts. When we check the ether balance in the first account, we still see 35 ether present here. And let us just check the balance in the second account to see if 1 ether has made its way there. In fact, the balance over here is 0. The reason for this is that our transaction has been submitted and has been put into the transaction pool. In order for that transaction to be processed and then added to the blockchain, it needs to be picked up by a miner. And currently, the only node which is present in our Ethereum network has stopped its mining process. So let us restart the mining now. So we run miner.start, and we can see from the output that something seems to have been picked up from the transaction pool. Let us wait now for at least a couple of blocks to be mined successfully, and then run miner.stop in order to cease the mining process. Once that is done, let us take a look at the balance of our first Ethereum account, and this has in fact increased. This is because in spite of the exit of 1 Ether from this account, new mining rewards have accrued over here, which is why we have a total of 59 Ether in this account. But now, in order to ensure that the transfer has gone through, let us check the balance of the second account. And yes, 1 Ether has made its way into this account. So we have now successfully invoked our first transaction using the GET client. We can now take a look at the details of the transaction, for which we can navigate further up and then copy over the ID of the transaction we just invoked. We then make use of the eth.getTransaction method in order to get the details of this transaction, and the argument, of course, is this transaction ID. And we get a JSON output, and this includes various details of the transaction, including the block number to which it belongs. The address of the account which invoked the transaction is available in the from field. The gas price as well as the total gas consumption of the transaction is available here. And we also have the hash of the block to which this transaction has been written. In order to view the details for that block, let us copy over this block hash here. And then we can run eth.getBlock and pass along this block hash. And this returns to us a JSON object representing that particular block. You can see various details related to this block, including who the miner of the block was, the nonce which was calculated, as well as the transactions which are included in this block, which is available as an array a little further down in the output. With that done, we have now come to the end of this demo, and we can now exit out of this get console by simply typing exit. From the output, you can see that various processes have been stopped, but you have successfully exited the get console and have returned to your shell. So far in this course, we have created a private Ethereum network using get. We created it by defining a genesis block, and then later on, we initialized it along with one node for the network. We then made use of the get console, and we saw the different ways in which we can use the APIs available in order to interact with the Ethereum network. In this demo, we will see how we can add an additional node to that Ethereum network, and we will do that by once again using the get client. So we will now once again bring up the get console by running the get console command, and on this occasion we specify two parameters. The data directory represents the node from which we want to bring up the console, so this is going to be node 0, and then following that we specify a network identifier which represents the ID of the network we wish to connect to. In the case of our private network, this needs to be the same as the chain ID value which we specified in our Genesis block definition. So that value is 9999. So we connect to the console by specifying that network ID, and now the console has come up. In order to view information about the node which we have currently brought up the console from, we can make use of the admin API, and this allows us to perform various operations related to the node. In order to view information about the node, we access the node info property, and then this gives us a JSON output which includes a node ID, and among other details includes the port on which this node is currently listening. In my case, this is port 30303, and do make note of this port number because once we initialize the second node to add to our Ethereum network, we need to make sure that it doesn't conflict with this one. So now that we have details about the first node, which is node 0 in our Ethereum network, let us go ahead and provision a second one. To do that, I'm now going to open up a new terminal session. So I navigate to Shell and then to New Window, and then from there select the option to open up a new window with a basic profile. Alternatively, you can also hit Command N on a Mac terminal. So once this new window is up, we can cd into the workspace directory which we created for our get demo. So in my case, this is called get-demo within my home directory. And then following that, do an ls. And we can see that there are three different files over here. One representing the data directory for node 0. There is also the Genesis block definition and a password file which we used previously in order to provision a new account. Let us now view the contents of the Genesis block, because when we provision the new node, we will need to make use of this genesis.json once more. So this is the Genesis block here, and we can see within the config definition that we have set a value of 9999 for the chain ID. So now let us go ahead and create this new node which will be added to our network. And just as we did with the first node, we run get init and we specify the genesis.json file as argument. And we also specify a data directory, which is going to be data_dir_node_1 on this occasion. So with that, the new node has now been defined. However, in order to bring it up, we will need to bring up the console from that node. And for that, we once again run get console, but note the new parameters here. We specify the data_dir to be this new data_dir directory which we provisioned. We specify the network ID parameter. And then to ensure that there is no conflict with the already existing node, we make sure that it runs on a different port. The other node is running on port 30303, so we set this to run on 30308. By specifying the node discover flag, we are telling get that the peer addition for this node should be done manually and it need not take care of this automatically. So once we run this command, the console has been brought up and our second node has now been initialized. So let us view the details for this node by running admin.nodeinfo. And the details here are similar to what we saw for the previous node, except of course, the node identifier is different, as is the port on which it is running. Now in order to add this node as a peer of the previous node which we had created, we will need to make use of the node URI, which is available as the value of this enode property. So just copy it over and keep it somewhere safe. And then following that, we can just confirm the listen address for this particular node. And at this point, let us head back to the console for the first node. We can check for the peer nodes of this particular node by checking the value of admin.peers, which returns an empty array. So we will now manually add a peer to this particular node, and we make use of the admin.addPeer method, and the argument to this is the URI of the second node, which we had just copied over. We can see that the port on which that node is listening also appears in this URI. So once we execute this, we get a value of true, which shows that the addition of the peer node has been a success, but we can confirm that by checking admin.peers once more. And on this occasion, we get an array containing one JSON data structure, and this represents the newly added node. So at this point, we have a private Ethereum network with two nodes running on it. It is now time for us to run some transactions on this, and we will be initiating an Ether transfer. However, before we do that, we can check the Ether balance in the first account on this particular node. And this shows us that there are a total of 59 Ethers available. This is expressed in the units of Wei. We will now switch over to the second node. So I'm going to bring up that tab here. And then you can see that some log statements have appeared in the console. However, let us create a new account associated with this node. So we call personal.newAccount and set a password of 123. And a new account with an address ending in 9B60 has been created here. We can check the balance in this account. And as expected, there is zero balance available for now. We can fix this by transferring over some Ether from the account belonging to the first node. But for that to happen, we will need the account address of this particular account. So let us copy that over and then head back to the console on our first node. From here, before we initiate any transaction, we will need to unlock the account. So we run personal.unlockAccount. And once this account has been unlocked, we can initiate a transaction by running eth.sendTransaction. So the to field represents the account address which we created on the new node, which ends in 9B60, and we're transferring a total of 1 Ether. So once we run this, it means the transaction has been submitted, but it hasn't been mined yet. We can confirm that by checking the balance in this account on this node, and that still has 59 Ethers in all. And we can now begin the mining process on this node. So once we run mining.start, we let this run for a few blocks and then run miner.stop. At this point, we can expect that the Ether transfer has taken place and that several blocks have now been successfully written to the blockchain. We check the Ether balance in the account on our first node, which has likely gone up from 59 since new blocks have been mined and the mining rewards will have been credited to this account. And in fact, a total of 113 Ether are now available in this account. Switching over to the other console window where we have the second node running, we check the balance in Ether in the main account over here, and this now has a total of 1 Ether. So we have now successfully performed a transfer of Ether from the address belonging to one node to an account belonging to one more Ethereum node, which is on the same network. In this exercise, you will use the get CLI in order to create a new blockchain. The get client allows us to work with any existing Ethereum network or to create one on our own. If we do wish to choose the second option and create our own Ethereum network, we will first need to perform some setup operations and then run a get command. You will need to recall exactly what those are. Next, you will list down some of the get management APIs which are available in order for us to work with an Ethereum network. We have covered in this course that there are many different ways for us to work with an Ethereum network, and there are a number of different management APIs which Get provides for us in order to perform these operations. You will need to identify some of the important ones here. And finally, you will recall a command which can be executed from the Get console in order to transfer 5 Ether from account X to account Y. Each of these topics were covered during this course, so please pause this video and then take some time to perform these tasks on your own. For the first task, you needed to run a get command in order to create a new blockchain. The command to execute for this is a get init command, and this is what it looks like. Get --datadir followed by a location for your data directory, followed by init, and then the location of a JSON file which contains the definition for the genesis block of your blockchain. So let us break up this command in order to understand what each of the components signifies. The get init command is the one which is used in order to initiate a new blockchain. And one of the options which we need to make use of is the datadir option. And here we specify a directory in which all of the data related to the blockchain can be stored. This directory effectively serves as a database for a node in an Ethereum network. This will store not only the blockchain data, but also the state information of the Ethereum network. And finally, another required argument when creating a new blockchain using getInit is the definition of the genesis block for your blockchain. In this example, we have called this genesis.json, and this genesis block definition can include a number of fields, including a chain ID. You can also specify an initial allocation of Ether into a number of accounts. You can set the mining difficulty level, and also a number of other configuration options for your blockchain. For the next task, you needed to list down some of the get management APIs which are available in order to work with an Ethereum network. One of these is the admin module, and it allows us to perform various tasks related to node management. For example, we can add peers to our nodes and access all the node related data. There is also the miner API, and this is useful when we wish to perform mining operations from our node. In this course, we covered the use of miner.start in order to start mining operations, and then miner.stop in order to cease mining. There is also the personal API, and this is used in order for us to work with accounts on Ethereum. There is the TX pool or transaction pool API, and this is used in order to work with transaction pools and then inspect the transactions within it. And within Get, we are also provided access to the Web3 API, And this allows us to perform a wide array of Ethereum-related tasks. This communicates with the node using RPC, and it includes, among other objects, the ETH object, which can be used for blockchain interactions. We saw, for example, that we use the ETH object to check the balances of Ether in any account and also to invoke transactions. For the final task, you needed to run commands from the get console in order to transfer Ether from one account to another. If you wish to initiate a transfer from an account X, then the first command you need to execute is personal.unlockaccount, which will decrypt the keys associated with a particular account. So the arguments to this include the account address followed by the password for the account. And then following that, you can invoke the transaction by running eth.sendTransaction. The argument to this includes a JSON object, which includes the sender's address in the from field, the recipient address in the to field, and the value of Ether being transferred in the value field. This value of Ether needs to be in the units of way, and we can make use of the web3.toWay function in order to convert 5 Ether to the corresponding way value. Previously in this course, we have created a private Ethereum network containing 2 nodes, and then we created an account which belonged to each of them. We also initiated a transaction in order to transfer Ether from one of those accounts to another. The true power of Ethereum, however, is in its ability to process smart contracts. Previously in the learning path, we have covered the deployment of a basic smart contract using the Ethereum Wallet application. While that is very useful in order to deploy simple contracts and then test them manually, in order to build more complex contracts and then automate various steps such as building, testing, and deployment, we will need a different set of tools. This is what we will explore right now, where we will make use of Node.js and the Solidity compiler in order to build out our smart contracts. So if you do not have Node.js already, you can navigate to nodejs.org, and then from here, select the installation for your own operating system. At the time of this recording, the latest long-term support version is 10.15.1. So I'm now going to download the installer for that. And once it has made its way to my file system, I can simply click it in order to begin the installation process. So I'm just going to click through the steps over here. So just hit continue, agree to the licensing terms. I'll select the standard installation and then hit install. And once the installation is complete, you can choose to keep or discard the installation file, and I'm just going to let it hang around. All right, so Node.js has now been installed successfully, and in order to test the installation, we can bring up a terminal session and can execute node-v in order to print out the version of Node which has been installed. And the output confirms that it's version 10.15.1 for me. In addition, we will need to make use of npm, which is the Node package manager. And this is a tool which will allow us to download various JavaScript packages. And it also speeds up the development of any JavaScript-based project by helping us initialize a project with a standard structure, which will speed up building, testing, and deployment, and also allows us to specify dependencies in our project and will automatically download the dependencies at the time of builds. So the version of npm which I have on my system is 6.4.1, and this can be obtained by running npm-v from the command line. npm comes packaged with Node.js, which is why you don't need to install it explicitly. All right, so now that we have Node and npm on our systems, we can go ahead and begin the development of our smart contract. For that, we will need to create a new JavaScript project, and I'm going to create a new project directory. This is going to be a hello world smart contract, and I'm going to call this greeter because this will greet us with a hello world message. So once a directory has been created called greeter, we can cd into it. And now in order to lay out a structure for the project, which will speed up building, testing, and deployment, we can simply make use of an npm command, which is npm init. And once this is executed, This will create a package.json file in the current directory. This is a project descriptor file, and if you have worked with Maven before, you can think of it as being somewhat similar to the pom.xml file. In addition to project metadata, this will also include the dependencies of the project, and we will add a few dependencies as we go along in this course. So running npm.init will prompt us to enter details for this package.json file, and I'm simply going to keep hitting enter in order to use the default values. Once that is done, we will be given a preview of the package.json, and then following that, we can confirm that the file has been created by running ls. We can take a look at its contents by using the cat utility, and this shows us exactly what was printed out in the output. So now that our package.json is ready, it is time for us to begin development. So you can use any IDE or text editor of your choice for this purpose, but I'm going to be making use of the Sublime text editor. So I have opened up the greeter directory in the Sublime text editor, and we can see from this file explorer menu on the left that it only contains a package.json file. If we click on that file, we will be able to view its contents, and it is possible for us to edit the file from here. Heading back to the greeter directory though, I am going to create a new source folder, and this is the one which will store the smart contract. So once this new folder has been created, I'm going to call this contracts, and then following that, can go ahead and create a new source file within it. So this will bring up a new empty file, and I'm now going to paste the code for the smart contract and then walk through it one step at a time. The contract will contain a single string variable which can be set using either the constructor or a setter method. The value can be retrieved using a get method. At the very top of the contract is a pragma directive which says pragma solidity *symbol 0.5.0. This will tell the build utility that this contract should not be compiled with any version of Solidity less than 0.5.0, and it should also not exceed 0.6.0. For the contract definition, we begin with the keyword contract, followed by the name of the contract, which is greetings. Note that we begin the contract name with an uppercase character, which is a convention, though it is not really required. This contract contains a single field which is of type string, and the name of the string variable is message. Do note here that we use a semicolon in order to terminate any line of code in the Solidity programming language. We now move along to the definition of the constructor for the smart contract, and to do this, we can make use of the keyword constructor. So this is a keyword which can be used in the newer versions of Solidity, and in the older versions, you may find that the constructor has the same name as the contract itself. This constructor takes in one argument, which is of type string, and this is called initial message. The memory keyword here implies that this variable's lifetime is just for the duration of this function call, and the public keyword implies that this function can be called from both within the contract and also from the outside, perhaps from a contract which references this one. And then within the constructor definition, we set the value of the message variable to the initial message which is passed as the constructor argument. We move along now to the next function definition, and this we begin with the keyword function, and this is called set greeting. This function definition is very similar to that of the constructor, where the message variable is set to the argument which is passed to the function. So now that we have defined the setter for this particular contract, we move along to the getter method, and this is called get greetings. This is also a public function, and this is also specified to be a view type. This keyword is effectively a promise that this particular function will not modify the state of the contract in any way. So this function takes in no arguments. However, it does have a return type, which we specify using the returns keyword, and this is of type string. And there is just one line of code within the function definition where we return the message variable. So with that, we have defined our hello world Solidity contract. The contract has a single string message, and this is something which can be initialized using a constructor, or the value can be set by calling the set greetings function. The message can also be retrieved by calling the getGreetings function. We can now go ahead and save the smart contract. So I'm going to call this greetings.sol, where SOL is the extension for any Solidity source file. So with that, our smart contract has been defined and saved. It is now time for us to build it, which is what we will do in the next clip. In the previous clip, we wrote out the code for our first smart contract in the Solidity programming language. We will now see how we can compile this code and then view the output of the compiler. So once we have saved this contract down, which I have called greetings.sol, I'm now going to bring up my terminal, and then from within the project directory, which contains the package.json file, as well as a contracts directory, we can cd into the directory which contains our smart contract code. So from within the contracts directory, I run an ls just to confirm that the source file does exist. And in order to compile the smart contract, we will need to download and install the solc compiler. So this is available as a JavaScript library, and in order to download it, we can make use of npm. So I'm going to run sudo npm install solc-g, which is going to install the Solidity compiler for all the users in my system. So I already had the Solidity compiler, which is why my package was merely updated. But if you do not have it already installed, you may see that this installation just takes a little longer. So with version 0.5.4 of the Solidity compiler, you should be able to compile smart contracts by running solc.js. However, if you would like to use the official Solidity compiler, and this is something which will give you the solc binary rather than solc.js, then you will need to get this from the Ethereum repo. On a Mac OS, you can do this by using the brew utility and by running brew install solidity. However, if you haven't added the Ethereum repo previously, you will need to run brew tap ethereum/ethereum prior to running the brew install step. Once the installation is complete, you can run solc from the terminal, and the output indicates that the compiler has been installed successfully. There are various options available when using the Solidity compiler, and if you'd like to view the syntax and the available parameters and options, you can always run solc from your shell in order to view what the options are. For the most basic compile operation, we can simply run solc followed by the location of our source file, which is exactly what we will do in just a little bit. But in case there are more advanced compile options which you need to specify, these can be found here. Alright, it's time for us to compile our smart contract. So I'm now going to clear out the terminal and then execute solc greetings.sol. This compile step should be quick given it's a rather small source file, and hopefully there are no compile errors which you run into. But the output here indicates that though the compilation was successful, there was no output which was generated. This is because we need to explicitly specify the kind of output we need from the compile step. So on this occasion, we rerun solc, but this time we include the option combine-json, and here we specify the types of output we need. So we will include an ABI file, the binary byte code, as well as some contract metadata. All three of these output formats will be available within a single JSON file. We also specify an output directory where the file should be generated, and we set this to the current directory. So once we have executed this statement, we see that the compiler run was once more successful, but on this occasion, some artifacts have been generated. We can confirm that by running ls, and the output shows us that in addition to our Solidity source file, there is also a combined.json file, and this includes the three different output formats which we had specified. Let us now take a look at the contents of that file. So we use the cat utility to view its data, and we can see that there is a JSON output here, and there are a number of different fields. There is the ABI output, which we can see here. This is effectively a descriptor of the functions and the data within a contract, which will allow us to interact with it. Then there is the binary byte code for the contract. And then finally, there is a metadata field, which includes various details about the contract itself. So clearly this output is not all that easy to read. It'll be easier for us to examine this output if we were to use some JSON formatter, which is exactly what I'm going to do by copying over this entire JSON output and then navigating in my browser to jsonformatter.curiousconcept.com. So this is one of the online JSON formatters which is available freely. And once we go into the main page, there is a field for us to enter the JSON data which needs to be formatted. So once I have pasted my JSON output here, I'm going to hit process, which should generate a formatted version of this data. And this is exactly what we get. You can see that there is an interface which allows us to collapse and expand certain fields in this contract. And there's also a full screen view available. So I'm going to make use of that. And we can see that right at the very top, there is a contracts field. And within that, there is a representation of our greetings.sol contract. So within this greetings contract, we have an ABI output. And then following that, there is the binary bytecode representation. Following that, there is the metadata for the contract. We can also see the version of Solidity which was used to compile this particular source file. So it is clear from this output that the Solidity compiler not only generates executable bytecode, but can also produce an ABI file which we can use in order to interact with the smart contract. That is something we will be doing later on in this learning path. But for now, we have learned how to write our first Solidity smart contract. And we have also made use of the Solidity compiler in order to build it out. And we have also seen some of the different output formats which can be generated using the Solidity compiler. Let us get out of the full screen view now and then view the JSON data once more. So we can just exit out of this and now move on to the next clip in this course. In the previous demos, we saw how we can write out a Solidity smart contract and then compile it using the solc command line interface. While this is adequate for a simple compilation, there will be occasions where you have a more complex compile step and you would like to define code for it. We will see exactly how that can be done, and we will also add some dependencies which we will use for our project in order to automate testing and deployment as well. So let us begin. I'm in the root directory of this smart contract project. So I'm running an ls. This shows us that there is a contracts directory where we have one source file. And then there is the package.json file, which is the project descriptor and includes all of the dependencies for the project. There are no dependencies yet, but now we will run one npm install command in order to install some packages which will be required by this application. These packages will be added as dependencies in the package.json file in the current directory. So we run npm install followed by the packages which we wish to install and add as dependencies. This includes the solc Solidity compiler, the Mocha testing framework, the Ganache CLI which will help us create a private network in which to deploy our smart contract, and also the Web3 package which will allow us to interact with our Ethereum network and the smart contract. The use of the save flag is not required if you have a newer version of npm which is greater than 5.0.0. In older npm versions, this ensures that these packages which are installed are added as dependencies in the package.json file in the current directory. So once we execute this, each of the dependencies will get downloaded and installed. And right at the very end, you can see that these 4 dependencies have now been added. We can confirm whether the package.json file has been updated by this particular step. So I'm going to bring up the project in the Sublime text editor and then head over to the package.json file. And towards the bottom in the dependencies field, we can see that these 4 packages have now been added to this file. In addition to this change, a new package log.json file has also been created, and there is also a node_modules directory. Since we have installed 4 new packages, the dependencies of those will be present here along with those packages themselves. With that done, it is now time for us to define our compile procedure. To do that, we head over to the root directory of this app. So within the greeter folder, I'm now going to create a new file, and this is going to be called compile.js. Following that, I'll first paste the entire contents of that file and then walk through each of the blocks. Right at the very top, we include each of the modules which we will require in this compile script. This includes the path, fs, and solc modules, and each of these will be imported using the require function. Following that, we will reference them by using three different constants: path, fs, and solc. So now that we have constants referencing the imported modules, we will define one more constant to reference the path to our Solidity source file. We can do this by making use of the path module and specifically its resolve method, and the arguments to this include all of the directories which make up the path to our source file. The _dir name variable references the directory in which this particular compile.js file is present, and then from here, our source file can be found at contracts/greetings.sol. Following that, we define the input to our compiler as a JSON object. This is called compiler input, and within the JSON object, there are various fields. There is the language of the source file, which is Solidity, and all of our sources can be defined within the sources object. We only have one called greetings, and the value of this is the path to our greetings.sol source file. Note that we make use of the file system's read file sync method here. So following the location of our source file, we also need to define what the output is going to be. So within the settings and within that the output selection object, we specify that we would like the compiler to produce an ABI output as well as the EVM bytecode of the smart contract. And finally, we will compile the source file by calling solc.compile, and the input to this is going to be the JSON version of our compiler input definition. The output of the compile step will be printed out to the console. So once we have defined our compile script, we can simply invoke it by running node compile.js from the terminal. So this will execute our JavaScript compiler step, and we can see the output which has been generated. Just as before, when we use the solc command line interface, this output is rather large and difficult for us to view over here. So I'm now going to copy over this JSON output and then head over to the JSON formatter page once more. So this still displays the previous compiler output. So I'm going to get rid of it by refreshing the page. And this takes us back to the home page. So I'm going to click on JSON formatter. And then in this field which is available, I'm going to paste the output of our most recent compile step and then hit process. All right, this output is much easier to view, and we can see that the output is kind of similar to what it was before. However, I'm going to expand this to a full screen view so that we can view it in more detail. And we can see that the structure is broadly the same, so this output is in fact a little cleaner. Within the ABI definition, we can see that the fields are laid out in a much more readable manner this time, and it is possible to expand and contract each of these individual objects. Moving further down, we can see the EVM bytecode here, and this includes not only the binary output, but also the opcodes. So while the binary bytecode is available within evm.object here, evm.opcodes gives us the full opcodes of the smart contract. The opcodes field is rather large, and if you'd like to view all of them, you can scroll all the way over to the right. So we have now seen how we can automate various steps in a build by making use of a compile script. In the next clip, we will see how we can make use of the Mocha testing framework in order to perform automated testing of a Solidity smart contract. Previously in this learning path, any testing which we did on our smart contracts have been manual. This, of course, is not a scalable solution, especially once your contracts grow very large in size and include a lot of features. So we will now see how we can make use of the Mocha testing framework in order to perform some automated testing. Any testing which is performed we'll need to make use of the output of the compile step in order to run the Solidity code. So for that, we will make a modification to our compiler script first. So rather than simply printing out the compiler output to the console, we will export the compiler output so that it can be used by our testing script. We won't be using these in the initial test we will perform on a smart contract, but it will get used later on. Adding the compiler output to module.exports will ensure that another JavaScript file which we create will be able to reference the compiler output by making use of the require function. So once we make this change and save the file, we can run the compiler once more. So we run node compile.js. So this will not produce any output on this occasion since we are not writing anything out to the console. But after this, let us go ahead and write our first test script. To do that, let us head back to Sublime Text, and then from here create a new directory called test within the Greeter project directory. So I'm going to right click, create a new folder, and then name this test. Within that test directory, we will now create a test script. So I'm going to add a new file to this. And then I'm first going to paste the contents and then save this as greetings.test.js. And then we can walk through the code. We begin by importing all of the packages which we require. This includes assert, Ganache CLI, and also the Web3 package. In our first test, however, only the first package, assert, will be in use. The others will be used a little later on once we add more tests to our test script. The test script we're going to run right now, in fact, does not reference our smart contract at all. It is just a general test on an object which we will create right here. This is just to demonstrate how exactly the Mocha testing framework can be integrated with Solidity. So here we are going to define a simple class called car, which includes two methods, park and drive. Each of these simply returns a single string, stop and vroom respectively. Following that, we will define a variable called car, which will be used to store an object of type car. Following that, we come across our first Mocha specific function. This is the before each method, and within this we define an operation which needs to be performed before each of the individual tests which we wish to perform. In our case, we wish to initialize a new car object before each of the tests, and this is exactly what we define within the body of the before each method. And where exactly do we define the tests to perform? Well, this is where the describe method comes in, which is another Mocha function, and this allows us to group various tests together. This group of tests will be called car class, and this includes a number of different test cases, and each individual test case definition can be found within the it functions. So the car class grouping includes two test cases. The first one is called can park, and this checks that the value returned by the car.park method is equal to stop. Similarly, the next test case checks whether car.drive returns a value vroom. Before each of these individual test cases are executed, a new car object will be created as defined in the before each function. So this concludes the definition of our test script. So we will now head over to the package.json file, and then here we need to ensure that Mocha will be the framework which is used in order to execute the test script. So you can see that this package.json includes a number of details, and within the scripts field, we can define the type of tests which need to be performed. However, before doing that, let us ensure that within the dependency section, the Mocha package has been included. So once that is done, we can head over to the test field over here within scripts and then set the value to Mocha. So now we have configured our test script to use the Mocha testing framework in order to execute its tests. And in order to execute the test script, we can head over to the shell, and then from the root project directory, we simply need to run npm test. If an argument is not explicitly specified, it will look for any scripts within the test directory and run them. So when we run this, our test script has been executed, and then soon enough, we get the result that both of the test cases which we had defined have passed. So the individual test cases, can park and can drive, have green check marks next to them, which shows that they have passed. And we can also see that they have been grouped together under a car class category. So we now know how we can make use of the Mocha testing framework and integrate it with our Solidity project. But before we test out our smart contract, let us do a quick sanity check. So heading back to the text editor, I'm going to close out the package.json, and then this time make sure that one of the test cases will fail. So within the test script, I'm going to make sure that the can park test case will fail by asserting that the can park method of the car object should return a value stopped rather than stop, which it will actually return. So once this change has been made and the test script has been saved, we can head back to our shell and execute npm test once more. So the test script has started running, but on this occasion, the test cases both do not pass. We can see that the can drive test case has passed, but can park did not. The output also shows us where exactly the test case failed and gives us the expected and actual outputs of the can park test case. As a result of the single test case failure, the overall result of the tests is failed. So we now have some idea of how the Mocha testing framework will work. With that done, let us head back to our test script and make sure that it will pass the next time it is executed. So I'm changing the can park test case to what it was previously. In the previous demo, we made use of the Mocha testing framework in order to implement a test in our Solidity project. That test, however, was merely to demonstrate how we can integrate Mocha with Solidity, and the test had no relation with either our smart contract specifically or even Ethereum in general. In this demo, we will take a look at how we can integrate our test with Ethereum, and for that we will be making use of the Web3 package. The Ethereum network we will be working with will be a private network which has been provisioned using the Ganache framework. So on the screen in front of you is the test script which we have been using, and at the very top there are a few require function calls which import the Ganache CLI and also initializes the Web3 interface with a private network which will be spun up by Ganache. So following that, let us now get rid of these tests which we had defined previously. Since these tests have no relation with either Ethereum or with our smart contract, we don't need them anymore now that we understand how exactly Mocha works, and specifically the use of the before each, describe, and it functions. Once that code has been cleaned up, I'm going to paste some new code and walk you through each of the steps here. We once again make use of the before each function, and in this case, we fetch all of the accounts which are available via Ganache. So these are the accounts which have been created on the private network provisioned by Ganache, and then we can access these accounts by using the Web3 interface. So if you run web3.eth.getAccounts, this will retrieve all of the accounts available from the Ganache network, and then we print out all of the account addresses which have been retrieved. In order to synchronize the fetching of the account addresses and their printing out, we make use of promises in JavaScript. That is, we first run web3.eth.getAccounts, following which we call the then method in order to print out the account addresses. Since JavaScript is by default asynchronous, in order to ensure that the account information is retrieved before they're printed out, we need to make use of this syntax. We then move along to the test cases now, and within this we have a grouping of test cases called greetings. This is specified within the describe function, and within that there is just a single test case. This is called deploy a contract, and you can see that this contains no body. The effect is that when this test case is executed, all that will actually run is what is defined in the before each function. So we will expect to see all of the retrieved accounts from Ganache in the output. So this concludes our test script. Let us now go ahead and execute this. So we can just save down this file and head back to our shell. And then from the project root, we simply execute npm test. So the execution of the test script has begun and once again uses Mocha. And in the output, we can see the 10 account addresses which have been retrieved from Ganache. When Ganache spins up its private network, it creates 10 different accounts, and each of them are loaded with 100 Ether. It is the addresses of those 10 accounts which you will see in your output here. And we can also confirm that the deploy a contract test case has passed. This is unsurprising given that the body of the test case contained nothing at all, and what we see in the output is just what was defined in the before each function. But now we can go ahead and modify our test script just a little bit so that it produces the same output, but we will move around the code just a little bit. So going back to the IDE or text editor, we can get rid of all of the Mocha related code over here. And then I'm going to paste some new code and then walk through each of the steps. So I've created a new variable called accounts. And then within the before each definition, we are making a call to web3.eth.getAccounts once more. And the return value is assigned to this accounts variable. Do note, however, that we're making use of the await keyword. This will ensure that the code execution will not proceed until this function call has returned. This is one more way to implement synchronization in JavaScript, where we ensure that the execution environment waits for a particular line of code to finish executing completely before it moves ahead to the next line of code. So within this before each function, we have the list of accounts, and then this list can be printed out within our test case. So once again, we make use of the describe and it functions, and within our it function, we simply print out the list of accounts using the console.log function. So at this point, we can save the changes to this file, and then let us see how exactly the output varies compared to our previous run. So heading back to the shell, we once again execute npm test, and this time the output is somewhat similar, but if you notice closely, you will see that the account addresses are all different from what they were previously. This is because for this test run, Ganache has provisioned a new network which contains 10 new accounts. One more subtle change from the previous run is that on this occasion, the console output with all of the account addresses appears before the marking of the test case as passed. This is because we have moved the console.log statement which prints out these account addresses into our test case definition rather than within the before each function. In this exercise, you will first identify the purpose of the pragma directive which is used in a Solidity source file. There are two types of pragma directives in Solidity, one of which is the version pragma, and that is the one we have covered in this course. You will need to remember why exactly one might consider using this in a Solidity source file. For the next task, you will make use of the solc command line interface in order to generate both the application binary interface or ABI and the byte code for a smart contract. The solc compiler for Solidity can be used in order to generate multiple types of outputs. And for one to interact with a smart contract, they often need both the byte code as well as a JSON interface, which is what the ABI provides to us. So if we wish to generate both of these outputs with a single command from the command line, how exactly could we do it using solc? And finally, you summarize the purposes of the describe, IT, and before each functions in the Mocha test framework. We saw during this course how the Mocha test framework can be integrated with a Solidity project, and we also covered how tests can be executed in a specific manner by using describe, IT, and before each. You will need to identify the specific reasons for using each of these. All of these topics were covered during this course, so please pause this video and then take some time to perform these tasks on your own. For the first task, you needed to identify the reason for using a pragma directive, specifically a version pragma, when defining a smart contract using Solidity. Very simply put, the version pragma will allow us to define the acceptable compiler versions which can be used in order to compile our Solidity smart contract. And this is best explained with an example. So if we make use of the directive pragma followed by a caret symbol followed by a specific version, and consider that this version we have specified is 0.5.2. This means that Solidity will enforce the use of specific compiler versions. The versions must fall into a range where the number is greater than or equal to 0.5.2 and is less than 0.6.0. And why exactly might we specify such a range of compiler versions? Well, a minimum compiler version may be necessary if our Solidity code makes use of certain features which have been introduced in version 0.5.2. Any version older than that will not work with our smart contract and our compile step will fail. And if we try to compile our smart contract using a version of the Solidity compiler which is greater than or equal to 0.6.0, then the directive will fail. The reason one might enforce an upper bound of the compiler version is because the next major version may include certain changes which breaks our code. When using some more mature programming languages such as Java or Python, the newer versions of the compiler are often backward compatible and will be able to compile code written in older versions of that language. Solidity, on the other hand, is very much in the early stages of its adoption, and there are several major changes which are being made to the compilers, and these changes can be incompatible with Solidity contracts which have been written in older versions of the language. For the next task, you needed to write down a solc command which can be used in order to generate both the ABI and the binary forms of a smart contract. If you would like both the ABI and the binary to appear within a single file, then you can run the first of these commands which you see on screen, which is solc followed by the option combined JSON, where you specify that the combined JSON file should include the ABI as well as the binary versions of the smart contract. You can specify an output directory where this combined JSON file will be generated, followed by the name of the smart contract which you wish to compile. Alternatively, if you want the ABI and the binary files to be in separate files, you can make use of the second command. So you invoke solc by specifying the ABI and bin flags, and then you also specify the output directory followed by the name of the contract. And for the final task, you needed to identify the purposes of the three different Mocha functions which we used during the course. One of these was the describe function, and this is used in order to describe a test suite. A test suite is simply a grouping of individual test cases. And these test cases are defined by using the it function. So a single it function defines an individual test case. Most test scripts for any application will involve not just a single test case, but a number of them, and may in fact even contain a number of different test suites. It is likely that a number of these test cases or test suites will have some common operations which need to be executed before the test is run. And these are the operations which we can define within before each. Within Mocha, before each effectively serves as a hook which is run before each describe or it function. Previously in this learning path, we have developed a test script and then included that as part of our smart contract project. We have also included a compile script, and we have seen how compiling and testing can be automated. In this demo though, we will focus on automating the deployment of our contract onto an Ethereum network. We will write the code for our deployment within our test script itself. So for that, we navigate to the test directory within our project directory, and then bring up the greetings.test.js we have been working with so far. I'm now going to clear out the contents of this file over here, and then replace it with some new code. So now going through each block of code, at the very top, we have all of the packages which have been imported, and this includes Assert, Ganache CLI, and Web3. The Web3 object can be used to interact with an Ethereum network, And the network we wanted to work with is a private network which will be provisioned by Ganache, which is why when we initialize the Web3 object, we specify Ganache.provider as the constructor argument. So following our require statements, we define some of the variables we will require for our contract deployment. And here, we import all of the outputs which are generated by the compiler. We capture the entire compiler output in the output variable. As we have seen, this is in the JSON format. And then we pass that JSON object in order to retrieve both the ABI and the EVM bytecode for the contract. This we assign to the variables ABI and EVM. Here we make use of the require function in order to import the output of our compiler, and we assign it to a variable called output. So how exactly is the output of the compiler available here? Well, going back to our compile.js, we can head right to the bottom where we specify that the compiler output should be available in the module.exports. This will ensure that we are able to import the output of the compiler in any of the other source files within our project. This import is possible if we make use of the require function in our other source file and pass this compile.js file as argument to the require function, which is exactly what we have done in our test file. Moving back to the greetings.test.js file, we proceed with defining the steps involved in our deployment, and we will be using the Mocha framework in order to automate the steps. So within the before each function definition, we first retrieve all of the accounts which have been created by Ganache, and we do this using the await keyword just as we did previously in order to synchronize this step. Once the account addresses have been printed out, we will also print out to the console both the ABI as well as the EVM bytecode of our contract, which we have extracted from the output of the compile step. So once we have printed those out, it is then that we move ahead to the definition of our deployment. So we once again make use of the await keyword to ensure that this deployment happens completely before we move along to the next step. And in order to deploy a contract, we first need to initialize a contract object. We do that by calling the constructor for web3.eth.contract, and this object can be initialized using the ABI for the contract. So following that, we will call the deploy method of the contract in order to deploy this contract to the blockchain. The blockchain it will get deployed to is of course the private blockchain which has been provisioned by Ganache. The argument to the deploy method is a JSON object which includes two fields. One of these is called data, and this includes the EVM bytecode of the contract which we wish to deploy. Do note here that we are prepending the bytecode with 0x, and the bytecode data itself can be accessed from evm.bytecode.object. We also need to provide the arguments for the constructor of our smart contract, and this is the initial value for the message variable in our smart contract. So we are setting this to a value of hello world, and do keep in mind that if your constructor in your contract takes in more than one argument, you will need to specify all of them in this list. So we only have one argument, which is why this particular list contains just a single element. The contract's deploy method returns a transaction object, and then we use that object and specifically its send method in order to send the transaction to the transaction pool of our Ethereum network. Since we are sending over a transaction, there are a few arguments which we can specify, and out of these, only the from argument is necessary. Here we need to specify which Ethereum account we are using in order to invoke this transaction. In my case, I'm using one of the accounts which has been provisioned by Ganache and which we retrieved into the accounts data structure. The optional arguments to the send method include the gas price, the value of ether which needs to be sent over, and also the gas limit, which is defined by the gas field. So I have set a gas limit of 100,000 Wei. With that done, we have finished the definition of our before each function, which will deploy a smart contract to our Ethereum network. What happens after deployment is something which we define within the describe and it methods here. When we submit a contract for deployment using the send method, what is returned to us is the address of the smart contract. this address has been captured in the greetings variable. So here we simply print out to the console the address of the contract, and then following that, we check that this is not a null value by invoking the assert.ok method. Alright, so with that, we have now successfully defined a deployment process for our smart contract, and we have done that using the Mocha framework. Just to confirm what is going to happen, we have specified in the contract deployment that the constructor for the contract should be passed along the argument hello world. If we switch over to the contract definition, we can see that this is the initial message argument, which will be assigned to the message field of the smart contract. Alright, with that done, let us go ahead and kick off this deployment. And since the deployment has been defined using Mocha, we simply need to run npm test from the root of our project. So the deployment process has begun, and within a few seconds, you should see a large output. So as defined within our before each function, the ABI for our contract has been printed out to the console, as has the EVM bytecode. And then right at the bottom, we can see that the test case has passed and that the account address for the contract has been printed out. So in this demo, we have seen how we can automate the build, test, and deployment of a smart contract using the Mocha framework. In the previous demo, we saw how we can make use of the Mocha testing framework in order to automate the deployment of a smart contract to an Ethereum network. However, given that Mocha is in fact a test framework, we should also include some tests of the contract once we have deployed it to the network. That is precisely what we will do in this demo. So for that, I'm going to bring up the greetings.test.js file we have been working with, and then clear out the definitions for the before each, describe, and it functions over here. So once that is done, I'm going to paste over some new code, and this in effect deploys the very same contract, but after the contract has been deployed, it checks whether the getGreeting method in the smart contract returns hello world. So at the very top, we define what greeting we expect from the smart contract when we invoke the getGreeting method. And then following that, we define the deployment steps in the before each function. One way it varies from the previous definition of before each is that we are not printing out anything to the console. This is because we are now confident that the deployment process works, and we know what the ABI and byte code looks like. Do note here, however, that within the argument to the deploy method, we have specified the argument to the constructor using the variable default greeting rather than the literal hello world which we used previously. So once our before each has been defined, we move along and define test cases. And on this occasion, we define two separate test cases. The first one verifies the deployment process and checks that the returned contract address is in fact a valid one. That is, it is not null. In the second test case, which we have labeled has a default argument, we are checking that the value which we assign to the greeting in the constructor call has not been modified. So for that, we first call the getGreetings method, and we do this by using the greetings object, which was returned when we sent the transaction over for the contract deployment. The method is invoked by calling greetings.methods.getGreetings.call. The return value is assigned to the constant getGreetings, and we make sure that this call to the function returns completely before we proceed to the next step. The next step, of course, is where we check that the greeting which has been returned is equal to hello world, and then following that, we print out the return greeting. So with that, we have now defined the code in order to deploy a smart contract and then executed a test on that deployed contract by invoking one of the functions. It is now time for us to run this test, and for that, we head over back to the shell and then execute npm test. And once we have the full output, we can see that both of the test cases have passed. The first one, where a contract was deployed, has been a success, and the value returned by the getGreetings method when we invoked it on the deployed contract is equal to hello world, which is why the second test case has also passed. So now that we have successfully written a test to check the working of the getGreeting method, we can add one more test case to our test script, and this will check the working of the setGreeting method. So let us now head back to our test script, and then within the describe method, we add one more test case. So this is called canChangeGreetings. And since we will be changing the state of the smart contract by invoking the setGreetings method, this will invoke a transaction. To do that, we will be calling the greetings.methods.setGreetings and then pass it an argument. So we will change the greeting to hi there instead of hello world. And following that, we will need to send the transaction over to the blockchain network. Just as with the contract deployment, we need to specify a JSON object to the send method. And on this occasion, we only include a single argument, which is the from field. And this is the account from which the transaction will be triggered. Once the setGreeting method has been invoked, we need to verify that it worked exactly as we intended it to. So for that, we need to call the getGreetings method once more, and then check that the message which is returned is equal to hi there. So we call the getGreetings method just as we did in the previous test case, except this time the value of the greeting has been set by a call to setGreetings. With these changes now made to our test script, where we have added a third test case, we can head back to the shell and then perform the deployment and tests once more. So we execute npm test, and then all the three test cases have passed. So just as before, the deployment step has passed, as has the call to getGreetings, and finally, the greeting has changed from hello world to hi there after we made a call to the setGreetings method. So each of the functions which we have defined within our smart contract, the constructor, getGreetings, as well as setGreetings, seem to work correctly. And we have automated the testing of each of these methods using the Mocha framework. Previously, we have performed a deployment of a smart contract and also tested out its methods by using a single test script which we wrote using the Mocha framework. However, it will often help to split up the deployment and the testing, especially when there are a number of different tests and your deployment itself can be complicated. In this demo, we will create a new deployment script where we will define all of the steps needed in order to deploy our smart contract to the Ethereum network. So we have seen within the test script that all of the steps which we need for deployment are present here, followed by all of the test cases we run once the contract has been deployed. Well, let us now create a similar script file, but this is going to be in the root directory of the project. So I'm creating a new source file over here, and this is going to be called deployment.js. I'll just go ahead and paste the code once more and then go through each of the steps. So this, broadly speaking, is very similar to what we had in the greetings.test.js previously. At the top, we make use of the require method in order to import the assert and Ganache CLI packages. We also import the Web3 package, and we initialize a Web3 object so that it works with a private Ethereum network which is provisioned by Ganache. Following that, we capture the output of the compiler and then pass the JSON object which it produces as output. From that JSON object, we will extract the ABI and the EVM byte code of our smart contract. And then following that, we will create variables called accounts and greetings. The accounts variable will store the 10 account addresses which will be created when we spawn a new Ethereum network using Ganache. The greetings variable will store the hash of the transaction which will be invoked when we deploy the contract to the blockchain network. Following that, we define a constant which will contain the value of the greeting we will initialize the smart contract with. Following that, we will define a deploy method which will print out all of the account addresses in the Ethereum private network. And then following that, it will deploy a smart contract to that private network. The deployment step should now be familiar to you, where we will call web3.eth.contract and then initialize it with the ABI of our smart contract. Following that, we invoke the deploy method, to which we pass along the EVM byte code for our contract, along with the argument for its constructor. This will return a transaction object for the contract deployment. With that, we will invoke the send method, and this is where we can specify the details for the transaction, such as the account which will be used in order to trigger the transaction. And then we also set a gas limit. The use of the await keyword will ensure that this contract deployment will take place before we proceed to the next line in this code, where we print out to the console the address of our newly deployed contract. So this defines the deploy method, and at the very end, we will simply call it in order for the contract deployment to occur. So we have now finished defining our deployment script. It is now time for us to trigger it, and for that we head back to the project workspace directory, and then from there run node deployment.js. You should see within a few seconds that the contract deployment has taken place successfully, and the address of the contract is now available. With that done, we now know how to define a deployment script in order to deploy a smart contract to an Ethereum network. One issue with this deployment, however, is that the network which was provisioned in the code is now gone. That was only valid for the scope of the deployment script, which makes it rather useless unless we simply wish to deploy the contract to the network and then execute some tests as we did previously. If you'd like to deploy the smart contract to a more permanent network, well, that is something we will take a look at in the next demo. So far in this course, we have performed a number of smart contract deployments. However, on each of those occasions, the deployments were to private Ethereum networks, which were only valid for the scope of the deployment or test script. In this demo, we will see how we can deploy a smart contract to a private Ethereum network, which is a little more permanent. While we previously made use of the Ganache CLI package in order to provision a private network, on this occasion, we will download the Ganache Framework and then use that to provision a private network and then deploy a smart contract to that. So let us now head over to google.com or any search engine of your choice and then search for download Ganache. Once you do that, the first search result should guide you to the home page of the Truffle Suite. This is truffleframework.com, and then within the Truffle Suite, there are 3 different frameworks available. One of these is called the Truffle Framework, and this allows us to automate the building, testing, and deployment of smart contracts. Then there is the Drizzle framework, which includes a lot of UI libraries. This will help us develop the user interfaces for distributed applications. And then finally, the one we are interested in right now is the Ganache framework, which will help us provision private Ethereum networks on which we can deploy smart contracts during the development phase and then get quick feedback on what we have worked on. So we navigate to truffleframework.com/Ganache. And then from here, there will be options to download Ganache for both Windows as well as macOS. In my case, since I'm using macOS, I'm going to look for the installer for that. But do note that Ganache is also available for Windows. So scrolling further down on this page, I have located the macOS installer. But before using that, we can scroll a little further down to get an idea of what Ganache looks like. I'm now going to head straight over to the installer, however. So I'm going to download the macOS DMG file in order to perform the installation. Once it has been downloaded to my file system, I'm just going to click on it. This will bring up the installer, and you can just click along with me if you're using macOS. Or if you're on Windows, then your installation procedure might be a little different. But towards the end of the installation phase, you will be prompted to drag the Ganache icon into the applications directory. And once that is done, the installation should be complete. In order to bring up the application, I'm going to bring up the Launchpad, and then from there, access Ganache by double-clicking on it. Since this is the first time you'll be bringing up Ganache, you will be issued a warning. I'm just going to say that this is safe to open up. And now the Ganache application is up and running. So spinning up a private Ethereum network was just that simple. We simply installed Ganache and then brought it up. And now we have a private network which includes 10 different accounts, and each of the account addresses are visible here. We can also see various details related to the private Ethereum network, including the fact that the current block is 0, which means that we are still on the Genesis block. There is also a default gas price and gas limit. My network also has an ID of 5777, and there is also a URL for the RPC server. This is something we will require later on in this demo, so just keep an eye out on it. By default, the mining status for this network is set to auto mining. So there are 10 different Ethereum accounts created over here, but in case you lose their addresses and their keys, you can recover them by making use of this seed phrase or mnemonic. So do make a note of this as well if you plan to hang on to this private network for long. Following that, we can take a look at each of the accounts which have been created. So there are 10 in total, and their addresses are visible here. And you will also notice that each of these accounts has a total of 100 Ether as balance. So this is enough Ether in each of the accounts for us to perform a number of different transactions. We can also view, for example, the number of transactions associated with each address. And then following that, if you'd like to view the private key corresponding to each account, well, that is also available from this interface. So if we click on the key icon over here, this will bring up the private key, and you can back this up if you need to. So we can click out of this now. And then following that, we continue exploring this Ganache interface. So moving on from the Accounts tab, we head over to Blocks. And at the moment, this private Ethereum network contains just a single block, which is the Genesis block. We move along now to the Transactions tab. And as you'd expect, there are no transactions on this network just yet. We can view the logs which are available for this network in the Logs tab. And once more, there is not much to speak of, but you can see the log statements from the initialization of this private network and the fact that Ganache has started up successfully. Let us now head back to the Accounts tab. And remember, I mentioned that we will be making use of this RPC server endpoint here. Well, in order to deploy a smart contract to this network, we will need to make use of this URL. So just copy this over, and this will likely be running in your local host at port 7545. We can now make changes to our deployment script so that the smart contract gets deployed to this Ganache network. So for that, we head over to the deployment.js file, which we have worked with previously, and we just make a few minor modifications to the code. I have removed the reference to the assert as well as the Ganache CLI packages, which we had included earlier, but we continue working with the Web3 package, which we need to interact with the Ethereum network. Following that, when we initialize the Web3 object, we make use of the setProvider method, and the provider this time is going to be the private Ethereum network spawned by the Ganache framework. So the argument to web3.setProvider is a new instance of web3.providers.http provider, and this is initialized with the RPC endpoint of our private Ethereum network. The rest of the deployment steps remains pretty much the same. We get the output of the compiler, specifically the ABI and the EVM byte code. We will need to access the accounts as well as the transaction hash of the deployment. Following that, we set the default greeting value over here and then define the deployment steps. This includes the initialization of the smart contract using the ABI and then deploying the EVM bytecode to the Ethereum network. We will then invoke the transaction for this deployment. We then print out the contract address to the console, and finally, we will call the deploy method. So that concludes our deployment definition. So we can save this file now and then head over to the shell in order to trigger this deployment, for which we run node deployment.js. The output confirms that the contract deployment is now successful, And the contract is now accessible at the address ending in 9E26. To verify the deployment, let us head back to the Ganache application, and then from there, head over to the Blocks tab. We can now see that a second block has been added to this private Ethereum network, and that this block includes one transaction. We can click on this block in order to view more details. So we can see, for example, the total gas used, when this was mined, as well as the block hash, and the details for the transactions in this block are also available here. We can see the transaction hash, as well as the account which initiated this transaction in the from address. And then the contract which was created, well, the address is exactly what we saw in the shell. This is one ending in 9E26. This does confirm that our deployment script did indeed deploy the smart contract to this Ethereum network on Ganache. To view all of the transactions available on this network, we head over to the Transactions tab, and we can see the same details of the transaction here as we did in the block view. Now, in order to view the bytecode for the transaction, we can head over back to the Blocks tab and then click on the latest block. From there, we expand the transaction within this block, and we can view the transaction data in the form of bytecode. In the previous demo, we were able to deploy our smart contract to the private network which was provisioned by the Ganache framework. However, now that the contract has been deployed, it is of little use for us unless we can interact with it. In order to interact with a deployed contract, we will need at least two things. One is the EVM bytecode for the contract so that it can be executed. And along with that, we will also need a JSON interface, such as the Application Binary Interface or ABI for the contract. The EVM bytecode for a smart contract will be available at the contract address, and we can gather that address for our deployed contract in the logs of the Ganache framework. So this is at the address ending in 9E26. So we will be writing a JavaScript source file in order to interact with a smart contract, and we will be using this contract address along with the ABI of the contract to do so. So before we proceed with that, let us take a quick look at the state of our Ethereum network. Heading over to the Transactions tab, we can see that there is just a single transaction, and this was when we deployed our smart contract at this address. Clicking on this will give us some more information about the transaction. Following that, we head over to the Blocks tab, where we can see that this blockchain currently only has 2 blocks in total. Heading over now to Accounts, we see that all of the accounts have a total of 100 Ether as balance, except for the first one, and this is because there was some gas which was consumed in order to deploy the contract using this account. We can also see, for example, that there is one transaction linked with this account, and that is for the contract deployment. So now that we know what our Ethereum network looks like, we can begin writing some code in order to interact with the smart contract which has been deployed on it. But as mentioned, we will need to make use of the ABI of the contract. So for that, we can head over to our shell and then make use of the Solidity compiler in order to generate the ABI in a separate file. To do that, we run solc followed by the path to our Solidity source file. We then specify the ABI flag so that the ABI output is generated, and using the -o option, we say that we want the ABI to be output in a separate file. Finally, there is a dot at the very end of this command, and this says that the output ABI should be in the current directory. So once we run this, it says that the compiling was successful and that the artifact has been generated. To view that, we can head over to our text editor, where you should be able to view this greetings.abi file in the project root directory. And when you click on it, you can see exactly what this looks like. So this is the JSON interface which will be used in order for us to interact with the contract. So now let us move on to writing the code for the contract interaction. For that, I'm going to create a new source file within the project root directory. and I'm going to call this interact.js. Just as before, I've pasted all of the code, and let us walk through each of the blocks. We import the FS or the file system package along with the Web3 package as well. We initialize Web3 to work with our private network on Ganache. So we specify the RPC endpoint. And then following that, we define a couple of variables. One of these is the address of our smart contract. This will be required in order to invoke the byte code of the smart contract. And then we also specify the from address, which represents the account from which all of the transactions will be invoked. Since we will need the ABI to interact with the contract, we extract it from the greetings.abi file, and for that we make use of the fs.readFileSync method, and we extract the ABI contents in the form of a UTF-8 string. We then convert the JSON string in the ABI file into a JavaScript JSON object by running json.parse. We then initialize an object which represents our deployed smart contract, and this is going to be a new object of type web3.eth.contract, which we initialize using both the ABI as well as the contract address. Following that, within the code, we call the send transaction method, whose definition is a little further down. That function will invoke each of the methods in our smart contract in order to test them out. However, once all of those methods have done executing, we print out to the console that we are done. And in case there is some error which is thrown when interacting with the contract, well, we print out the error to the console. Moving along now to the definition of the send transaction function, we define this to be an async or asynchronous function. And within the function, we are effectively making 3 calls to our smart contract. We first invoke getGreetings, and we then print out the value which is returned to the console. Following that, we invoke the setGreetings method, where we set the value of the greeting to be hi there. And since the setGreeting method will change the state of the contract, this will trigger a transaction, and we need to call the send method in order to send the transaction to the blockchain network. And finally, in order to confirm that the setGreetings call did work, we call getGreetings once more and then print out the returned value to the console to confirm that the greeting message has changed to hi there. So over here, we are interacting with our smart contract by calling each of its methods. So we can now save this file and then run it by heading over to the shell and then running node interact.js. And the output includes the 3 log statements which we had sent to the console. The first call to get greetings shows us that the value of the greeting is hello world. After we invoked the setGreetings method, we published out the result of that operation to the console, which we can see here in this JSON data structure. And finally, we invoked getGreetings once more, which confirms that the call to setGreetings did work and that the message has now changed to hi there. So using both the ABI of the contract and the contract deployment address, we have been able to interact with our smart contract. It is now time for us to take a look at the state of our Ethereum network once more, for which we head over to the Ganache application, and we can see that each of the first 2 accounts has 1 transaction associated with it. So there is now 1 more transaction than there was previously. Heading over to the blocks tab, there is also an additional block, and the latest block with the index of 2 also has 1 transaction in it. The gas used, however, is very different for both blocks 1 and 2, and this is because the second block includes the transaction involving the call to the setGreetings method, which consumed far less gas than the previous transaction in block number 1, which involved a contract deployment. This is in fact evident when we head back to accounts and see that the contract deployment which used this first account used up about 0.01 ether. On the other hand, it was the second account which was used in our latest transaction, and the ether consumption for this was low enough that it does not affect the ether balance when rounded to 2 decimal places. We now head over to the blocks tab and then examine our latest transaction in more detail by clicking on the latest block. And this gives us the transaction hash as well as some additional details for the transaction. We can click on that to view a little more information. And then following that, we head over to the Transactions tab, where both of our transactions are visible. We can see that the first one is for a contract creation, and the second one is a contract call. Clicking on this will give us the same information which we saw previously from the block view. And finally, when we head over to the logs, we can see the details of the transaction over here as well. Previously in this course, we have created a private Ethereum network using the Ganache Framework and then deployed a smart contract to that, following which we interacted with it. Deploying to a private network and then interacting with it immediately and then performing a number of tests is very useful during the development phase of a smart contract, where you can get very quick feedback on any of the updates you have made to the smart contracts or on any new features you have added to it. However, there will come a point where you will need to deploy and then test out your smart contract in an environment which is much more similar to the main Ethereum network. This is where you would use one of the public test networks for Ethereum. And in this demo, we will see how you can deploy a smart contract to the Rinkaby test network and then work with it from there. For that to happen, we will need to add our machines as nodes to the Rinkaby test network. And the way to do that is to make use of the get client. The exact command to execute for that is get followed by a number of options. The Rinkaby option will tell get to connect to the Rinkaby test network. The RPC flag will enable the RPC endpoint, which we will use in another terminal session in order to connect to the Rinkaby network using get. Following that, we can specify all of the RPC APIs which we want available over the HTTP RPC interface. So here, we are specifying that we would like the ETH, Net, Web3, Personal, and TX Pool APIs available to us when we bring up the get console from our node which is connected to the Rinkaby test network. And finally, we specify the sync mode for this node, and we set this to light so that only the current state of the blockchain network is retrieved. So when we run this, we will have started a process which has connected our machines to the Rinkaby test network, and we have now become a node on Rinkaby. In order to interact with the Rinkaby network, we will need to make use of this HTTP endpoint which has been enabled. So you can just copy this over, and then we can open up a new terminal session. So I'm now going to open up a new window over here, and then from there, I'm going to establish a connection to the Rinkaby test network, once again using get. So the command to execute is get attach followed by the HTTP endpoint which has been created for us. And this will create an interactive session which we can use in order to work with the Rinkaby test network, including invoking transactions on it. This is similar to the get console we have worked with previously, except on this occasion we are connected to the Rinkaby test network. Before we invoke any transactions, let us see if there are any accounts available for us, and this can be accessed using personal.list accounts. This returns a list of all of the accounts which have been set up, and in my case, I had provisioned an account earlier on in this learning path using Ethereum Wallet. So this is the account which is visible for me. And in case you do not have an account on Rinkaby, you can refer to some of the earlier labs in this learning path to see how that can be done. We can now check the balance for the account using the eth.getBalance method. So we call that and we pass in as argument the address of the account we have set up on Rinkaby. And I have just under 1 Ether in balance in this account. If you would like to load more Ether into your Ethereum account on Rinkaby, you can make use of the Rinkaby faucet. This will require you to make a social media post on either Google+, Facebook, or Twitter, which contains the account address which you would like loaded with Ether, and then make use of faucet.rinkaby.io, where you can pass in the URL of your social media post, and the account which is listed in it will be populated with some test ether. So once we have checked the balance in our account, before we can invoke any transactions though, we will need to unlock the account. We can do that by running personal.unlockAccount, whose argument include the account address as well as the password for that account. And if your password is correct, you should see true being returned by the method. So now that we have connected as a node to the Rinkaby network, it is possible for us to deploy a smart contract to it. And in order to do that, I'm going to bring up the deployment script which we developed earlier on. And within that, there is just one thing which needs to change. When we initialized the provider for the Web3 interface, we had set this to the private Ethereum network which we had provisioned from Ganache. This is what was available on our local host at port 7545. But instead of connecting to the private network on Ganache, we need to connect to the Rinkaby public test network, and the HTTP endpoint for that is available at port 8545. This is what we saw in the output when we used get in order to connect as a node to the Rinkaby test network. So that is the only change we need to make to deployment.js. So we can now go ahead and save this file and then head back to our shell. In order to run the deployment process, I'm going to open up a new terminal window. I'll first cd into the directory where the script is located, and then from there, execute node deployment.js. So you'll soon see that the contract deployment has been successful. The address of the contract is now available here, so you can make a note of this and then head over to the connection which we established to the Rinkaby network using get. So from that tab, you should be able to see a log message that a contract creation transaction has been submitted to the network. And the address of the contract is exactly what we saw when we triggered our deployment process. So now that we have deployed our contract to a publicly available test network, let us copy over the contract address, and we can now view its details on the publicly available Rinkaby Etherscan website. So you can search for Rinkaby Etherscan, and then the first search result should direct you to rinkaby.etherscan.io. Once you get there, there is a field at the very top of the page where you can enter the ID of any transaction or the address of any contract or an externally owned account in order to view its details. Do note, however, that we are on the Etherscan website for Rinkaby, so we will only have Rinkaby specific information available here. So I'm now going to paste in the contract address of our newly deployed contract here and then hit go. And this takes us to the page where the details of the contract are available. In my case, I can see, for example, that this was deployed just 41 seconds ago. The block which includes the transaction for the contract deployment is also available here. And if you would like to view additional details, we can click on this transaction hash, and this gives us a lot more information. There is also a note here that this is a transaction which is only valid on the Rinkaby testnet and is not on a main Ethereum network. Heading back to the transaction page though, we can click on the block, and this gives us details for the block which included the transaction to deploy this contract. We can also see, for example, which account performed the mining of this block, and if we click on it, we can view all of the transactions associated with that account. Heading back to our block though, we can now take a look at the transactions which are included in the block. So I'm going to click on this link over here, and then all of the transactions in that block can be visible. Heading back to the block and then back to the contract address on Etherscan, we can click on the from account. So this is the Rinkaby account which we used in order to deploy this contract. In fact, if we switch over to the shell and view the full address of this contract, which ends in 0EFB, and then heading back to Etherscan, we can see that this is exactly the same address. And we can also see the Ether balance in this account, which is just a shade under 1 Ether. So we have now seen how we can deploy our smart contract to the Rinkaby test network using our own deployment process. Throughout this learning path, we have adopted a few different approaches to smart contract development. We have seen how we can develop and then deploy smart contracts using Ethereum Wallet, which also provides us with an interface to interact with our deployed contract. We have also made use of JavaScript in order to automate the deployment of a contract, and we have also performed tests on a deployed contract. And in each of these cases, we have seen how we can deploy the smart contract to the Rinkaby test network. In this demo, we will focus on making use of the Remix IDE, which is a cloud-based development environment for smart contracts. We will see how we can develop, compile, deploy, and then interact with smart contracts using the Remix interface. And we can access this online IDE by navigating in our browsers to remix.ethereum.org. So once you are there, you should see an interface which looks something like this. In my case, in a previous session, I was coding up a smart contract, and that contract is still visible here. If you're accessing Remix for the first time though, you will see empty space where I have smart contract code. In any case, we will need to paste the code for our own greeting smart contract here. To do that, I'm now going to bring up my Sublime text editor where I have the greeting smart contract defined. Head over to greetings.sol, and then from here, copy the contents of this entire contract and then paste it in the Remix IDE. So once that is done, we can begin compiling the contract, and for that you can navigate to the right. But before we hit start to compile here, we will need to select which compiler we will be using in order to compile this code. So we can click on this drop-down list here, which allows us to select a compiler version, and you will see a number of different versions available. Most of these are nightly builds, and I'm going to select the latest version, which is not 1. So this is 0.5.4. This should start the compile process automatically and will only take a few seconds. And then following that, in order to deploy the smart contract, you can head over to run. And before we can invoke any kind of transaction, which includes deployment of the contract, we will need to specify an environment. This environment determines how we will connect to a blockchain network. So we can click on this drop-down menu in order to view the options. And the one we will be using is the injected Web3 environment. Since Remix is a browser-based IDE, if we happen to have any application which injects Web3 into the browser, that can be used in order to interact with the Ethereum network. One such application is the Metamask client, and this is what we had set up earlier on in the learning path. This will inject a Web3 object into every page which is loaded in the browser. And then if there is any Ethereum-enabled application running on that page, it can make use of that injected Web3 in order to interact via Metamask to an Ethereum network. By specifying the environment in the Remix IDE to injected Web3, we are telling it that Remix should make use of the Metamask client in order to connect to an Ethereum network. So I'm now going to click on this Metamask logo over here and then log into Metamask with my password. So this shows that I'm connected to the Rinkaby test network and I have a shade under 2 Ether in my account. Since we have configured Remix to work with injected Web3, it means that any deployment which we do of this contract or any transactions which we invoke will be on the Rinkaby test network. And the accounts which will be used for any of these transactions will be among those available via Metamask. So the account which I have in Metamask has an address ending in 58FF. So closing out of Metamask and then heading back into Remix. So once we have selected the environment to be injected Web3, from the next field, we can select the account which will be used in order to invoke a transaction. Since I only have a single account on Metamask, I'm going to select that one with the address ending in 58FF, which has a shade under 2 ethers in balance. For any transaction, we can also specify the gas limit and the value of ether which needs to be transferred, which we can specify using this interface. And then following that, in the fields below, we can specify whether to deploy this contract, in which case we will need to specify an argument for the constructor, which is initial message. Alternatively, we can load a contract which has been deployed already, and we can load that by specifying the contract address. In fact, that is exactly what we're going to do. And for that, let us head over to the shell, where we have the address of the deployed contract on Rinkaby from an earlier lab, and then paste this into this interface. Earlier on in this course, we saw how we can interact with an already deployed smart contract by using a combination of its contract address and the ABI. In this case, we are using a combination of the contract address and the entire code of the smart contract itself. And we are able to do this because the Remix IDE will compile the code of the contract in order to generate the ABI. So just to summarize what we have done so far, we have established a connection from the Remix IDE to the Rinkaby test network via Metamask. We have then specified the address of the smart contract we wish to interact with, and along with that, generated its ABI by pasting the code of the smart contract in the interface. So thanks to the ABI, we should see the deployed contract interface available in this deployed contract section. And when you expand it, each of the methods which are available for us to invoke from the contract will be available. We are now in a position to interact with the contract which was deployed to the Rinkaby test network, and we have done this by specifying the contract address in the Remix IDE, along with the code of the contract itself, which has been compiled to produce an ABI file. From the definitions in the ABI file, we now see that our deployed contract has two methods, setGreetings and getGreetings. Methods which do not alter the state of the contract will not invoke a transaction, and these will be highlighted in blue like the getGreetings method here. So let us run this method by clicking on the button, and this returns the greeting to us, which is hello world. Moving along to the other function, which is setGreetings, because this will alter the state of the contract and will invoke a transaction, this button appears in red. So we're now going to change the message to hi there, and then in order to invoke the transaction, we hit set greetings. And what happens when we invoke this transaction? Well, since we are hooked in via Metamask to the Rinkaby test network, triggering this transaction will bring up the Metamask interface, which we can use in order to complete the details for this transaction. So we can view the data, and then if we wish, we can go ahead and confirm the transaction, or we can head over to the details tab and then play around with the details. So this is what has been set in terms of the gas fee. If you would like to edit this, we can click on the edit button here. And then there are a few options available for us here where we can set the gas price. To simplify things for us, Metamask gives us three different options depending on how long we're willing to wait for the transaction to go through. Setting a low gas price can involve a wait of over 18 minutes. On the other hand, a higher gas price will make the transaction process in about 35 seconds. However, if you would like to be a little more precise in terms of setting the gas price, we can head over to the Advanced tab, and there is a line graph available over here which will allow us to estimate how much time will be taken in order to process the transaction for various values of gas price. So a gas price of about 4.395 will involve a long wait, but one which is nearly 10 will result in the transaction being processed much sooner. One benefit of such a line visualization is that it shows us that there is this somewhat optimal point where an increase in gas price does not really contribute to a significant decrease in processing time. For my transaction, this translates to a gas price of a little over 5 gigaway. So I'm now going to select that value and then confirm that I want the transaction to go through. So once that is done, you can keep a track of the log statements using the Remix interface. And you can see that this has integrated with the Rinkaby Etherscan page, and the link to the transaction on Rinkaby Etherscan is available here. So I'm just going to click on that, and this shows that this transaction is still pending. However, I'm just going to fast forward a little bit, at which point the transaction has now been confirmed and has been added to the Rinkaby blockchain. So with this transaction having been processed, the greeting in a smart contract has changed from hello world to hi there. The full details for this transaction are not yet available on Etherscan, but after waiting a minute or so, one can just hit refresh and all of the transaction information will be available. At this point, let us head back to our Remix IDE, where we have the confirmation in the console that the transaction was added to the blockchain. We can expand this in order to view all of the transaction information. And all of the details which we see here is in fact exactly what we see on Etherscan. The from address for this transaction is an address ending in 58FF, and this is in fact exactly the same as our Metamask account address. In the to field, we can see the contract address which appears, and then when we click on that, we will be taken to the page for the contract on Etherscan. In my case, I have exactly two transactions associated with the smart contract. The first of these was the contract deployment, and the second one was the latest call to the contract, specifically the set greetings method. The block in the blockchain on which the contract can be found is also available here. Heading back now to our Remix IDE, we will perform one more check, and this is to confirm that the greeting has indeed been updated on our smart contract. So for that, we simply make a call to the getGreeting method, and this will not invoke a transaction. And the return result confirms that our setGreeting call was a success. One thing about working with Ethereum networks, which we have come across during this learning path, is the fact that there are a number of different tools available. From Metamask to the Ethereum Wallet, to Get, to the Solidity compiler, and also the Remix IDE, a lot of the tools have many overlapping features, but each of them are also pretty well suited to specific tasks. Given that fact, it can often get confusing when deciding what tool to use for which purpose when using Ethereum. In this demo, we will make use of a number of the different tools which we have come across so far in order to interact with our deployed smart contract. The file which you see on screen in front of you is a deployment script which we defined using JavaScript, and we use Node in order to run this. We also wrote some code in order to interact with the deployed smart contract, and this is something we will now use to work with our smart contract deployed on Rinkaby. We had previously used this in order to interact with our smart contract deployed on a private Ethereum network, which was provisioned by Ganache. In order to interact with the smart contract, there are a few details which we need to provide, including the address of the smart contract on the Ethereum network. Currently, this source file has the contract address for the private network. So let us now go ahead and grab the address of the contract which has been deployed on Rinkaby. Once we have that, we can paste this into our interact.js file. And we will also need to alter the Web3 provider so that it's not pointing to the private Ethereum network anymore, but it's pointing to port 8545 from where the Rinkaby network is accessible. One additional change we will make is to change the call to set greetings so that the greeting value is set to hello instead of hi there. This is because in our previous interaction with the smart contract on Remix, we have set the message value to hi there. So once this change has been made, there is one more alteration required for this particular interact.js file, where we need to specify the account which will be used in order to invoke transactions. So this is currently making use of an account which was provisioned on our private Ethereum network, and we will now set this to use the address of our account on Rinkaby. I still have this address available on my get console, and I'm going to copy that over and paste it into this interact.js file, and this account address is going to be the value of the from address variable. Just to ensure we don't run into any issues, I'm now going to unlock this account using get. So from the get console, we simply need to run personal.unlock account, where we pass in the account address and password. And once this account has been unlocked, It is now time for us to execute our interact.js script. So once that file has been saved, we can bring up a new shell and then run node interact.js. So once this begins, we can see the results of the first call to get greetings, which shows us that the value is initially high there. Following that, the call to the set greetings method will take place, and then this is what the output will produce, which includes details of the transaction which was invoked. And then at the bottom, we see the result of our second call to the get greetings method, which was performed after we called set greetings and then changed the message to hello. And this confirms that our call to set greetings was a success. When we head over to the get console where we have our node process running, we can see the details of this transaction, including the fact that the recipient of the transaction was this smart contract address. We can copy over that smart contract address and then view its details on the Rinkaby Etherscan. So I'm now going to paste over this address in this field here and hit go. And this shows us our latest transaction invocation for that smart contract. And finally, let us confirm that the same contract is also accessible from the Remix IDE. So we head over to that. And then from this interface, we make a call to get greetings. And this also shows us a value of hello. So in this demo, we have seen how we can make use of JavaScript in order to modify the state of the contract and then view that modification using a number of other tools. We have covered previously in this learning path that in order to interact with a smart contract which has been deployed to an Ethereum network, there are two pieces of details which we require. One of these is the address of the smart contract on the Ethereum network, and this is required for us to be able to execute the smart contract because the EVM bytecode of the contract will be available at the contract address. So while the execution of the contract can happen in the Ethereum network once we provide the contract address, in order to know which methods in the contract to invoke and what their arguments are, we will need to make use of an interface which includes all of those details. This is exactly what an application binary interface or ABI file will contain. In this demo, we will be using the Ethereum Wallet application in order to interact with a smart contract which has been deployed on the Rinkaby test network. And we will be doing that by supplying the contract address as well as the ABI file for it. So once the wallet application is up, we can navigate to the Contracts tab. And here, I have a previously deployed contract still visible. However, in order to work with the contract which we have deployed to Rinkaby, we won't be creating a new contract, but we will simply be watching an already deployed one. And for that, we can click on Watch Contract, and then we will be prompted for some details. The first of these is the address of the contract which we wish to watch. So I'm now going to go ahead and retrieve that information from one of the JavaScript source files we have been working with. So after pasting that information here, the other detail which we need is a JSON interface, and this is in fact the ABI file. So heading back to the text editor, there is a greetings.abi file which was generated previously in this learning path by using the Solc compiler. So copying over this JSON of the ABI file, we can head back to Ethereum Wallet and then paste the JSON data into this field. With that done, we now only need to provide a name which we will use in order to reference this contract, and I'm going to call this greeter. And with these details provided, we can just hit OK, and we now have another contract available in our Ethereum Wallet interface. In order to work with it though, we can just click on it, and we now have an interface which we can use in order to invoke the various functions available in our contract. The results of get greetings is available here, and this will refresh automatically when we modify the greeting message. And then to change the greeting, we will need to invoke the set greetings method, and that is available using this drop down on the right. So we can then expand this drop down and select set greetings, following which we will be prompted for the argument for this method. Since we are now approaching the end of this course, I'm going to change this method from hello to buy. And since this will be invoking a transaction, we need to specify which account to use in order to trigger this. But once that is done, we can just hit execute. We will then be prompted to enter a password because this is going to invoke a transaction. But once we do that, we just hit send transaction, and then we simply wait for a few seconds. So we can see that get greetings is still returning hello, and this is because our transaction has not yet been written to the blockchain. However, if you just wait a few seconds, you may notice at the top that a new block has now been received, and within a few moments, you will see that the get greetings field has now updated with our new message. So the use of the contract address and the ABI has now allowed us to interact with the smart contract using Ethereum Wallet. For a final check though, let us bring back the Remix IDE and let us execute get greetings once more, just to ensure that the greeting message has indeed been updated and is visible from here. So when we click on this button, we get the value of the latest message in our smart contract. In this exercise, you'll write some code in order to integrate your JavaScript script file with an Ethereum network which can be accessed at an HTTP endpoint. During this course, we made use of JavaScript in order to connect to Ethereum networks. One of these networks was a private one which was provisioned using the Ganache Framework, and the other was the Rinkaby testnet. You will need to recollect how exactly we established this connection. Next, you will make use of get and specifically the command line interface in order to establish a connection to the Rinkaby test network. In this case, your host can serve as a node on Rinkaby, but in order to work with the Rinkaby network, you will need to enable a few options. One of these is the HTTP RPC service, which will create an HTTP endpoint which we can use in order to connect to the network using JavaScript, for example. We can also specify that certain management APIs should be available when we connect to the network, and you will specifically enable ETH and Web3. And finally, you will ensure that our host connects to the Rinkaby network as a light node. For the last task, you will recall the steps which are involved in order to interact with a deployed contract using the Ethereum wallet. While it is possible for us to create a brand new contract and deploy it on a network before interacting with it, we saw in this course how it is possible for us to work with a contract which has already been deployed to a network. You will need to identify the specific steps involved and the pieces of information which you will need. All of these topics were covered during this course, so please pause this video and then take some time to perform this exercise on your own. For the first task, you needed to write some JavaScript code in order to establish a connection to an Ethereum network which is accessible from an HTTP endpoint. Well, in order to do this, we will need to make use of the Web3 module. So once that has been imported into your code using the require function, you can create a new Web3 object, and then following that, you will run web3.setProvider, and the argument to this is an instance of type web3.providers.http provider, and this HTTP provider can be initialized with the HTTP endpoint which we wish to connect to. Once this connection has been established, we can make use of the Web3 module in order to interact with the network we have connected to. For the next task, you needed to write a get CLI command in order to connect as a node on the Rinkaby test network. The command, of course, will begin with get, followed by specific options. In order to connect to the Rinkaby network, we can specify the Rinkaby flag. In order to enable an HTTP RPC endpoint, we can set the RPC flag. And in order to enable the ETH and Web3 APIs, we use the RPC API option followed by ETH and Web3 separated by commas. This comma separated list can include any of the other APIs which you wish to enable. And finally, in order to work as a light node on the network, we set the value of the sync mode argument to light. The other options for the sync mode argument are full if you want to run as a full node, and the syncing in that case could take several hours or even a few days. And the other option is to perform a fast sync where some of the more recent blocks are obtained from the blockchain. For the final task in the exercise, you needed to recollect the steps involved to interact with an already deployed contract using the Ethereum Wallet app. The first step here is to establish a connection to the Ethereum network where the contract has been deployed. Within the wallet application, there is a watch contract option which we can use. And once we make that selection, we will be prompted for two pieces of information. One of these is the address of the contract which has been deployed. The address will include, among other details, the EVM bytecode of the smart contract, which is required in order to execute it. And in order for the Ethereum wallet application to know what functions and fields are included in the smart contract, we will need to specify a JSON interface for it. The application binary interface or ABI file is an example of such an interface. So once these pieces of information have been supplied, the Ethereum wallet application will allow us to interact with the smart contract. This means that we can perform read operations in order to view the values of the various fields in the contract and also invoke contract functions which perform reads. We can also invoke functions which perform write operations and change the state of the smart contract. However, these will invoke a transaction and we will need to pay some ether in order to trigger them.